Hello everyone, and welcome to this Neural Network Full Course Video 2022 by Simplilearn. Deep learning is a field of artificial intelligence that is rapidly growing and has several applications to offer. Deep learning is being used to build self-driving cars, virtual assistants, face recognition systems, machine translation systems, as well as in healthcare to detect diseases at an early stage. Artificial neural networks form the core of deep learning and works based on the structure and functions of a human brain. Neural networks are used to build deep learning models with vast volumes of data. It consists of several layers that process data, find hidden information, and give the desired output. Now, as per marketsandmarkets.com, the deep learning market is expected to reach $18.16 billion by 2023, that is growing at a CAGR of 41.7% from 2018 to 2023. According to another report by alliedmarketresearch.com, the global neural network market was valued at $14.35 billion in 2020, and it is projected to reach $152.61 billion by 2030, that is growing at a CAGR of 26.7% from 2021 to 2030. Now, my colleague Chinmay will introduce the topic that we'll be covering in our Neural Network Full Course video. So over to Chinmay now.
Neural networks typically used in deep learning are computing systems inspired by the structure and function of a human brain. It is used to find solutions to those problems for which the algorithmic method is expensive or does not exist. Neural networks learn by example, so we do not need to program it in depth. Hi guys, welcome to the complete neural network tutorial by Simplilearn. But before we begin, make sure to subscribe to our channel and hit the bell icon to never miss an update. First, we'll understand the basics of neural networks and see its practical implementation. Then, we'll learn how backpropagation and gradient descent works. Finally, we'll understand the concepts and practical implementation of convolutional and recurrent neural networks. Let's first look at a small animated video to understand neural networks better.
Last summer, my family and I visited Russia. Even though none of us could read Russian, we did not have any trouble in figuring our way out, all thanks to Google's real-time translation of Russian boards into English. This is just one of the several applications of neural networks. Neural networks form the base of deep learning, a subfield of machine learning where the algorithms are inspired by the structure of the human brain. Neural networks take in data, train themselves to recognize the patterns in this data, and then predict the outputs for a new set of similar data. Let's understand how this is done. Let's construct a neural network that differentiates between a square, circle, and triangle. Neural networks are made up of layers of neurons. These neurons are the core processing units of the network. First, we have the input layer, which receives the input. The output layer predicts our final output. In between exist the hidden layers which perform most of the computations required by our network. Here's an image of a circle. This image is composed of 28 by 28 pixels, which make up for 784 pixels. Each pixel is fed as input to each neuron of the first layer. Neurons of one layer are connected to neurons of the next layer through channels. Each of these channels is assigned a numerical value known as weight. The inputs are multiplied to the corresponding weights, and their sum is sent as input to the neurons in the hidden layer. Each of these neurons is associated with a numerical value called the bias, which is then added to the input sum. This value is then passed through a threshold function called the activation function. The result of the activation function determines if the particular neuron will get activated or not. An activated neuron transmits data to the neurons of the next layer over the channels. In this manner, the data is propagated through the network. This is called forward propagation. In the output layer, the neuron with the highest value fires and determines the output. The values are basically a probability. For example, here, our neuron associated with square has the highest probability. Hence, that's the output predicted by the neural network. Of course, just by a look at it, we know our neural network has made a wrong prediction. But how does the network figure this out? Note that our network is yet to be trained. During this training process, along with the input, our network also has the output fed to it. The predicted output is compared against the actual output to realize the error in prediction. The magnitude of the error indicates how wrong we are, and the sign suggests if our predicted values are higher or lower than expected. The arrows here give an indication of the direction and magnitude of change to reduce the error. This information is then transferred backward through our network. This is known as backpropagation. Now, based on this information, the weights are adjusted. This cycle of forward propagation and backpropagation is iteratively performed with multiple inputs. This process continues until our weights are assigned such that the network can predict the shapes correctly in most of the cases. This brings our training process to an end. You might wonder how long this training process takes. Honestly, neural networks may take hours or even months to train. But time is a reasonable trade-off when compared to its scope. Let us look at some of the prime applications of neural networks. Facial recognition. Cameras on smartphones these days can estimate the age of the person based on their facial features. This is neural networks at play, first differentiating the face from the background and then correlating the lines and spots on your face to a possible age. Forecasting. Neural networks are trained to understand the patterns and detect the possibility of rainfall or a rise in stock prices with high accuracy. Music composition. Neural networks can even learn patterns in music and train itself enough to compose a fresh tune. So, here's a question for you. Which of the following statements does not hold true? A. Activation functions are threshold functions. B. Error is calculated at each layer of the neural network. C. Both forward and back propagation take place during the training process of a neural network. D. Most of the data processing is carried out in the hidden layers. Leave your answers in the comments section below. With deep learning and neural networks, we are still taking baby steps. The growth in this field has been foreseen by the big names. Companies such as Google, Amazon, and Nvidia have invested in developing products such as libraries, predictive models, and intuitive GPUs that support the implementation of neural networks. The question dividing the visionaries is on the reach of neural networks. To what extent can we replicate the human brain? We'd have to wait a few more years to give a definite answer. But if you enjoyed this video, it would only take a few seconds to like and share it. Also, if you haven't yet, do subscribe to our channel and hit the bell icon, as we have a lot more exciting videos coming up. Fun learning till then.
I hope you're excited to learn more about neural networks. Now we have Richard who will take you through the remaining part of the course and make you understand neural networks in detail. With that, over to you, Richard.
What is a neural network? Welcome to today's lesson. My name is Richard Kirshner. I'm with the Simplilearn team. Today we want to discuss the very basics of a neural network and what that is. So, what's in it for you today? What is deep learning? What is artificial neural network? How does neural network work? Advantages of a neural network, applications of a neural network, and the future of neural networks. Let's start with a brief history of the artificial intelligence. Hello, I am the human brain. This one's seeking enlightenment and has sat and meditated. I am the most complex organ in the human body, and I help you to think, understand, and make decisions. And the secret behind all my power is a neuron. I'll get back to that in some time. Ever since the 1950s, scientists have been trying to mimic the functioning of a neuron and use it to build smarter robots. After a lot of trial and error, humans finally designed a computer that can recognize human speech. It was only after 2000 that humans were able to give birth to deep learning that was able to see and distinguish between different images and videos. So looking at that, let's dive into what is deep learning. Now your first thought might be it's the opposite of shallow learning. No, deep learning I liken to a magic box. And let's go in there and just take a look as to why it's kind of a magic box. So what exactly is deep learning? These are the images of dogs. Deep learning is a machine learning technique that teaches computers to do what comes naturally to humans, learn by example. The robot gets trained with photos as example. Now, this is very different than hardwiring a computer program so that it recognizes something. It actually learns. And that's where it's a magic box, because you don't really control how it learns, you control the aspects that go in. The computer comes back and says, wait, I know what you are. It looks at the photograph of the dog and it's able to identify that it saw in the images. It says, you are a dog. Woof woof. So that's an example of deep learning. You'll notice we'll go into actually how it works behind the scenes for a neural network. But there's a bit of feeling of magic, and that's where the term deep learning comes in. And that's also the term where I like to call it a magic box. You put these things in here into the program and it starts running the deep learning, and you have to understand those settings, but you don't have to follow exactly what's going on in the deep learning model. That brings us to the question, how does deep learning do it? Remember the neuron? Scientists managed to build an artificial form of it that powers any deep learning based machine. So let's talk about artificial neural networks. What is an artificial neural network? To understand how an artificial neuron works, we need to understand how the real one works. First, we have a dendrite, input to the neuron. And you can see these little hairs that come in and they receive information. Then we have the cell body. Information processing happens here. So it takes all these different dendrite and information coming in from the different dendrites, and it looks at that information. And then you have your axon, which is the output to the neuron. So there goes your axon, and you see it goes all the way out, and at the very end it flanges out, and each one of those little flanges connects to the dendrite or the hairs on the next one. Now let's see what an artificial neural network looks like. So in an artificial neural network, we have an input layer. So that could be an array of data. Each one of those white dots in the yellow bar would represent, say, a pixel in a picture. Then you have the lines that connect it to the hidden layers, which are your weights, and they add all those up on the hidden layers, and each one of those dots, kind of like a cell, does something with all the inputs, and then it puts an output into the next hidden layer, and so on into the output layer. So information processing happens here. Input to the neuron, output to the neuron. So you can see how they are similar. We have an input, which is our yellow bar coming in, and then you liken each of the hidden layers to being a neuron, and it passes it to the next one, and so on, and then you have an output to the next neuron, or an output to the real world. A neural network is a system of hardware and or software patterned after the operation of neurons in the human brain. Neural networks, also called artificial neural networks, is a way of achieving deep learning. How does artificial neural networks work? Let us find out, how does an artificial neural network work? Hey Siri, what is the time now? It's 12:30 in the morning. Thanks. Let's find out how she recognizes speech. Here is a neural network and the different layers on it. So we have our input layer, our hidden layers, and the output layer. This is the sentence that needs to be recognized by the network. What is the time? So when it comes in, each one comes in as a pattern of sound. So what is the time? First, let's consider the word what. And you have W-H-A-T. And you can see each one of those in the sound bar, probably looks a little different than that, just a representation, comes in as a different pattern. Now we will split the sound wave for the letter W into smaller segments. So we split off W, and then we take W and we analyze just W. As the amplitude is varying in the sound wave for W, we collect the values at different intervals and form an array. So we have 0.5, 1.5, 1.7, 1.9, that might be the different amplitudes coming in, and we feed the array of amplitudes to the input layer. So each one of those goes into its own box on the input layer. Random weights are assigned to each interconnection between input and hidden layer. So remember all those little lines? I said those are special weights. Now we're going to start by doing it randomly. We always start with random because if you start with some kind of preset identical pattern, like if you set them all to 3, it takes forever to train it and you're less likely to get a good result, where random works really well in this. The weights are multiplied with the inputs and a bias is added to form the transfer function. So we make a sum of all the weights times the value. So you take 0.5, which is your x coming in, and we're going to multiply that by W1, W2, W3, so on. And then when we get to the next level, we're going to add those together coming in, what's coming in. So we add the weight times x. And there's always a bias added in. If you ever build your own neural network, don't forget to add the bias in. Otherwise, it tends to not work quite as well. You need that extra layer in there to help it. Weights are assigned to the interconnection between the hidden layers. The output of the transfer function is fed as an input to the activation function. So the output from one hidden layer becomes the input to the next hidden layer. Acoustic model contains the statistical representation of each distinct sound that makes a word. And so we start building these acoustical models, and as these layers separate them out, they'll start learning what the different models are for the different letters. Lexicon contains the data for different pronunciations of every word. So we have the lexicon at the end, where we end up with the A, B, C, D, and it identifies the different letters in there. Now, the term acoustic model and the term lexicon are specific to this domain, the domain of understanding speech. Certainly when you're doing photographs and other things, you'll have different labels on here, but the process is going to be the same. And finally, we get our output layer. Following the same process for every word and letter, the neural network recognizes the sentence you said. What is the time? So it identifies the W-H-A-T and then identifies that that's one word. What is the time? And so on. It's 12:30. That way Siri can look up the time and read it back to you. So let's look at the advantages of an artificial neural network. So gentlemen, could you tell me the advantages of an artificial neural network? It's amazing how many times I've been in that situation where I have to explain to the people making the decisions in the company. It's amazing how many times I've been in that space where I have to explain to the owner of the company what the artificial intelligence and the neural network actually do. What are the advantages of an artificial neural network and what it can do for them and how it works. So, an artificial neural network, outputs aren't limited entirely by inputs, and results given to them initially by an expert system. This ability comes in handy for robotics and pattern recognition systems. Artificial neural networks have the potential for high fault tolerance. Artificial neural networks are capable of debugging or diagnosing a network on their own. Very common use these days is to go through all the log files and sort them out. Thousands of log files if you're working as an admin. Nonlinear systems have the capability of finding shortcuts to reach computational expensive solutions. So we see this in banking where by hand they have an Excel spreadsheet and then they start building codes around that Excel spreadsheet, and over 20 years they might build a repertoire of all these functions, and the neural network comes up with the same answers done in days, weeks, or even a month for a huge bank. So let's take a look a little bit more, because I mentioned a couple applications of artificial intelligence there, but let's dig deeper into the applications of artificial intelligence. Let's look at some of the real life. This is stuff going on right now in our world. And we're in such an exciting time with the neural networks and the machine learning and the artificial intelligence development. So let's take a little look at some of the current applications going on in real life. And you can use your imagination to dig for some new ones that we don't have listed here, because it's so limitless, the amount of applications that are being worked on right now or being implemented. Handwriting recognition. Neural network is used to convert handwritten characters into digital characters that the system can recognize. Stock exchange prediction. If you've ever worked with stock exchange, which I have, it is so fickle to track. I mean, it is really hard to understand. There are many factors that affect the stock market. Neural network can examine a lot of factors and predict the prices on a daily basis, helping the stockbrokers. So right now, it's still at the intro phase where it helps them, and they really have to look closely at it. When you realize that we generate over 3 terabytes a day just from the stock exchange here in the United States, that's a lot of data to dig through, and you have to sort it out before you even start focusing on even one stock. Traveling salesman problem. It refers to finding the optimal path to travel between all cities in an area. Neural network helps solve the problem, providing higher revenue at a minimal cost. Logistics is huge. Just the logistics that we talk about, a salesman traveling from town to town. Logistics are used by Amazon. Amazon loves to ship their packages, and they have empty space on their trucks. So they'll pre-ship packages and fill that empty space on who they think will buy it. Saves them a lot of time, and people are a lot happier because they get it tomorrow instead of having to wait 3 weeks. Image compression. Idea behind data compression neural network is to store, encrypt, and recreate the actual image again. So we can optimize our compression in data. Images are the biggest one, but it's used in all kinds of data. Wonderful application to save hard drive and to optimize being able to read it back out again. Those are just a few, and like I said, use your mind to dig deeper. And let's take it even further. We're going to go a step further here, and let's look at the future of deep learning. And here we are. That's not me, thank goodness. A wonderful person there reading her crystal ball. I'll tell you what I see in the future. More personalized choices for users and customers all over the world. I certainly like that when I go in there and whatever online ordering system starts referring stuff to me. Local company here where I live that uses this where you can take a picture and it starts looking for what you want based on your picture. So if you see a couch you like, it starts looking for furniture like that, or clothing. I think it's mainly clothing. Hyper intelligent virtual assistants will make life easier. If you played with Google Assistant or Siri or any of those, you can see how they're slowly evolving, and they're just now getting over that hump where a virtual assistant can do all kinds of things, even pre-write your email response for you. New forms of algorithm for learning methods would be discovered. There's always something rolling out, and they've had some really cool research in this area. Again, this stuff is we're just in the infant stage of artificial intelligence and neural networks and actually applying them to the real world. Wonderful time to jump in. Neural networks will be a lot faster in the future. Neural network tools will be embedded in every design surface. We already see that you can buy a little mini neural network that plugs into a really cheap processing board or into your laptop. So the hardware is starting to come out that goes right in there where you can dump it on there, and that makes it also faster. So because it's on the hardware instead of the software side. Neural networks will be used in the field of medicine, agriculture, physics, discoveries, just everything you can imagine. We see this today where it's going from a PhD student in medicine trying to understand T cells and understand the statistic analysis of that to cure people, to help keep them healthy, to help find out how we heal, to something that anybody can go access and process the data on. They're working on shared data systems. This concept of it being used in these different fields and these different domains is huge. The world's wide open for anybody jumping out there to start exploring them and start learning neural networks. Let's dive in and say, how does a neural network work? So now we've come far enough to understand how neural network works. Let's go ahead and walk through this in a nice graphical representation. They usually describe a neural network as having different layers. And you'll see that we've identified a green layer, an orange layer, and a red layer. The green layer is the input. So you have your data coming in. It picks up the input signals and passes them to the next layer. The next layer does all kinds of calculations and feature extraction. It's called the hidden layer. A lot of times there's more than one hidden layer. We're only showing one in this picture, but we'll show you how it looks like in a more detail in a little bit. And then finally we have an output layer. This layer delivers the final result. So the only two things we see is the input layer and the output layer. Now let's make use of this neural network and see how it works. Wonder how traffic cameras identify vehicles' registration plate on the road to detect speeding vehicles and those breaking the law? They got me going through a red light the other day. Well, last month. That's like the horrible thing. They send you this picture of you and all your information because they pulled it up off of your license plate and your picture. I shouldn't have gone through the red light. So here we are, and we have an image of a car, and you can see the license plate on there. So let's consider the image of this vehicle and find out what's on the number plate. The picture itself is 28 by 28 pixels, and the image is fed as an input to identify the registration plate. Each neuron has a number called activation that represents the grayscale value of the corresponding pixel range. And we range it from 0 to 1. 1 for a white pixel and 0 for a black pixel. And you can see down here we have an example where one of the pixels is registered as like 0.82, meaning it's probably pretty dark. Each neuron is lit up when its activation is close to 1. So as we get closer to black on white, we can really start seeing the details in there. And you can see again the pixel shows us one up there. It's like part of the car, and so it lights up. So pixels in the form of arrays are fed to the input layer. And so we see here the pixel of a car image fed as an input, and you're going to see that the input layer, which is green, is 1 dimension, while our image is 2 dimension. Now when we look at our setup that we're programming in Python, it has a cool feature that automatically does the work for us. If you're working with an older neural network pattern package, you then convert each one of those rows so it's all one array. So you'd have like row 1 and then just tack row 2 onto the end. You can almost feed the image directly into some of these neural networks. The key is though, is that if you're using a 28 by 28 and you get a picture that's 30 by 30, shrink the 30 by 30 down to fit the 28 by 28. So you can't increase the number of input, in this case green dots. It's very important to remember when you work on neural networks. And let's name the inputs x1, x2, x3 respectively. So each one of those represents one of the pixels coming in. And the input layer passes it to the hidden layer. And you can see here we now have 2 hidden layers in this image, in the orange, and each one of those pixels connects to each one of those hidden layers. And the interconnections are assigned weights at random. So they get these random weights that come through. If x1 lights up, then it's going to be x1 times this weight going into the hidden layer. And we sum those weights. The weights are multiplied with the input signal, and a bias is added to all of them. So as you can see here, we have x1 comes in, and it actually goes to all the different hidden layer nodes, or in this case, whatever you want to call them, network setup, the orange dots. And so you take the value of x1, you multiply it by the weight for the next hidden layer. So x1 goes to hidden layer 1, x1 goes to hidden layer 2, x1 goes to hidden layer 1 node 2, hidden layer 1 node 3, and so on. And the bias, a lot of times they just put the bias in as like another green dot or another orange dot, and they give the bias a value 1, and then all the weights go in from the bias into the next node. So the bias can change. We always just remember that you need to have that bias in there. There's things that can be done with it. Generally, most of the packages out there control that for you, so you don't have to worry about figuring out what the bias is. But if you ever dive deep into neural networks, you got to remember there's a bias, or the answer won't come out correctly. The weighted sum of the input is fed as an input to the activation function to decide which nodes to fire and for feature extraction. As the signal flows within the hidden layers, the weighted sum of inputs is calculated and is fed to the activation function in each layer to decide which nodes to fire. So here's our feature extraction of the number plate. And you can see these are still hidden nodes in the middle. And this becomes important. We're going to take a little detour here and look at the activation function. So we're going to dive just a little bit into the math, so you can start to understand where some of the games go on when you're playing with neural networks and you're programming. So let's look at the different activation functions before we move ahead. Here's our friendly red tag shopping robot. And so one is the sigmoid function. And the sigmoid function, which is 1 over 1 plus e to the minus x, takes the x value, and you can see where it generates almost a 0 and almost a 1 with a very small area in the middle where it crosses over. And we can use that value to feed into another function. So if it's really uncertain, it might have a 0.1 or 0.2 or 0.3, but for the most part it's going to be really close to 1 and really close to, in this case, 0 to 1. The threshold function. So if you don't want to worry about the uncertainty in the middle, you just say, oh, if x is greater than or equal to 0, if not, then x is 0. So it's either 0 or 1. Really straightforward. There's no in between in the middle. And then you have what they call the ReLU function. And you can see here where it puts out the value, but then it says, well, if it's over 1, it's going to be 1. And if it's less than 0, it's 0. So it kind of just dead ends it on those two ends, but allows all the values in the middle. And again, this, like the sigmoid function, allows that information to go to the next level. So it might be important to know if it's a 0.1 or a minus 0.1. The next hidden layer might pick that up and say, oh, this piece of information is uncertain, or this value has a very low certainty to it. And then the hyperbolic tangent function. And you can see here it's 1 minus e to the minus 2x over 1 plus e to the minus 2x. And it's very much along the same theme. A little bit different in here in that it goes between minus 1 and 1. So you'll see some of these, they go 0 to 1, but this one goes minus 1 to 1. And if it's less than 0, it's, it doesn't fire. And if it's over 0, it fires. And it also still puts out a value. So you still have a value that you can get off of that, just like you can with the sigmoid function and the ReLU function. Very similar in use. And I believe originally used to be everything was done in the sigmoid function. That was the most commonly used. And now they just kind of use more the ReLU function. The reason is, one, it processes faster because you already have the value and you don't have to add another compute the 1 over 1 plus e to the minus x for each hidden node. And the data coming off works pretty good as far as putting it into the next level if you want to know just how close it is to 0. How close is it not to functioning? Is it minus 0.1, minus 0.2? Usually they're float values. You get like minus 0.00138 or something. So, important information, but the ReLU is most commonly used these days as far as the setup we're using. But you'll also see the sigmoid function very commonly used also. Now that you know what an activation function is, let's get back to the neural network. So finally, the model would predict the outcome of applying a suitable activation function to the output layer. So we go in here, we look at this, and we have the optical character recognition, OCR, is used on the images to convert it into a text in order to identify what's written on the plate. And as it comes out, you'll see the red node, and the red node might actually represent just the letter A. So there's usually a lot of outputs when you're doing text identification. We're not going to show that on here, but you might have it even in the order. It might be what order the license plate's in. So you might have A, B, C, D, E, F, G, the alphabet plus the numbers, and you might have the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places. So it's a very large array that comes out. It's not a small amount of, we show 3 dots coming in, 8 hidden layer nodes, 2 sets of 4. We just show 1 red coming out. A lot of times this is, 28 times 28. If you did 30 times 30, that's 900 nodes. So 28 is a little bit less than that just on the input. And so you can imagine the hidden layer is just as big. Each hidden layer is just as big, if not bigger. And the output is going to be, there's so many digits. It's a lot. It's a huge amount of input and output. But we're only showing you just, it'd be hard to show in one picture. And so it comes up, and this is what it finally gets out on the output, is it identifies a number on the plate. And in this case, we have 08-D-03858. Error in the output is backpropagated through the network, and weights are adjusted to minimize the error rate. This is calculated by a cost function. When we're training our data, this is what's used. And we'll look at that in the code when we do the data training. So we have stuff we know the answer to, and then we put the information through, and it says, yes, that was correct, or no. Because remember, we randomly set all the weights to begin with. And if it's wrong, we take that error. How far off are you? Are you off by, if it was like -1, you're just a little bit off. If it's like -300 was your output, remember when we're looking at those different options? Hyperbolic or whatever, and we're looking at the REL. The REL doesn't have a limit on top or bottom. It actually just generates a number. So if it's way off, you're going to have to adjust those weights a lot. But if it's pretty close, you might adjust the weights just a little bit. And you keep adjusting the weights until they fit all the different training models you put in. So you might have 500 training models, and those weights will adjust using the backpropagation. It sends the error backward. The output is compared with the original result, and multiple iterations are done to get the maximum accuracy. So not only does it look at each one, but it goes through it and just keeps cycling through the data, making small changes in the network until it gets the right answers. With every iteration, the weights at every interconnection are adjusted based on the error. We're not going to dive into that math because it is a differential equation and it gets a little complicated. But I will talk a little bit about some of the different options they have when we look at the code. So we've explored a neural network. Let's look at the different types of artificial neural networks. And this is like the biggest area growing, is how these all come together. Let's see the different types of neural network. And again, we're comparing this to human learning. So here's a human brain. I feel sorry for that poor guy. So we have a feed-forward neural network. Simplest form of they call it an ANN, a neural network. Data travels only in one direction, input to output. This is what we just looked at. So as the data comes in, all the weights are added, it goes to the hidden layer, all the weights are added, it goes to the next hidden layer, all the weights are added, and it goes to the output. The only time you use the reverse propagation is to train it. So when you actually use it, it's very fast. When you're training it, it takes a while because it has to iterate through all your training data. And you start getting into big data because you can train these with a huge amount of data. The more data you put in, the better trained they get. The applications, vision and speech recognition, actually they're pretty much everything we talked about. Almost all of them use this form of neural network at some level. Radial basis function neural network. This model classifies the data point based on its distance from a center point. What that means is that you might not have training data, so you want to group things together and you create central points, and it looks for all the things, some of these things are just like the other. If you've ever watched the Sesame Street as a kid, that dates me. So it brings things together. And this is a great way, if you don't have the right training model, you can start finding things that are connected you might not have noticed before. Applications, power restoration systems. They try to figure out what's connected, and then based on that, they can fix the problem if you have a huge power system. Cohonen self-organizing neural network. Vectors of random dimensions are input to discrete map comprised of neurons. So they basically find a way to draw, and they say dimensions, or vectors, or planes, because they actually chop the data in 1 dimension, 2 dimension, 3 dimension, 4, 5, 6. They keep adding dimensions and finding ways to separate the data and connect different data pieces together. Applications used to recognize patterns in data, like in medical analysis. The hidden layer saves its output to be used for future prediction. Recurrent neural networks. So the hidden layers remember its output from last time, and that becomes part of its new input. You might use that especially in robotics or flying a drone. You want to know what your last change was and how fast it was going to help predict what your next change you need to make is to get to where the drone wants to go. Applications, text-to-speech, conversation model. So, I talked about drones, but, just identifying on Lexus or Google Assistant or any of these, they're starting to add in, I'd like to play a song on my Pandora, and I'd like it to be at volume 90%. So you now can add different things in there and it connects them together. The input features are taken in batches, like a filter. This allows a network to remember an image in parts. Convolution neural network. Today's world in photo identification and taking apart photos and trying to, have you ever seen that on Google where you have 5 people together? This is the kind of thing separates all those people so then it can do a face recognition on each person. Applications used in signal and image processing. In this case, I used facial images or Google picture images as one of the options. Modular neural network. It has a collection of different neural networks working together to get the output. So, wow, we just went through all these different types of neural networks, and the final one is to put multiple neural networks together. And I mentioned that a little bit when we separated people in a larger photo, individuals in the photo, and then do the facial recognition on each person. So one network is used to separate them, and the next network is then used to figure out who they are and do the facial recognition. Applications still undergoing research. This is the cutting edge. You hear the term pipeline, and there's actual in Python code and in almost all the different neural network setups out there, they now have a pipeline feature usually. And it just means you take the data from one neural network and maybe another neural network, or you put it into the next neural network, and then you take 3 or 4 other neural networks and feed them into another one. So how we connect the neural networks is really just cutting edge, and it's so experimental. I mean, it's almost creative in its nature. There's not really a science to it because each specific domain has different things it's looking at. So if you're in the banking domain, it's going to be different than the medical domain, than the automatic car domain. And suddenly figuring out how those all fit together is just a lot of fun and really cool. So we have our types of artificial neural network. We have our feed-forward neural network. We have our radial basis function neural network. We have our Cohennon self-organizing neural network, recurrent neural network, convolution neural network, and modular neural network where it brings them all together. And the colors on the brain do not match what your brain actually does, but they do bring it out that most of these were developed by understanding how humans learn. And as we understand more and more of how humans learn, we can build something in the computer industry to mimic that, to reflect that. And that's how these were developed. So, exciting part, use case, problem statement. So this is where we jump in. This is my favorite part. Let's use the system to identify between a cat and a dog. If you remember correctly, I said we're going to do some Python code, and you can see over here my hair is kind of sticking up over the computer, a cup of coffee on one side, and then a little bit of old school, a pencil and a pen on the other side. Yeah, most people now take notes. I love the stickies on the computer. That's great. That is my computer. I have sticky notes on my computer in different colors. So not too far from today's programmer. So the problem is we want to classify photos of cats and dogs using a neural network. And you can see over here we have quite a variety of dogs in the pictures and cats, and just sorting out it is a cat is pretty amazing. And why would anybody want to even know the difference between a cat and a dog? Okay, why? Well, I have a cat door. It'd be kind of fun that instead of having like a little collar with a magnet on it, which is what my cat has, the door would be able to see, oh, that's the cat. That's our cat coming in. Oh, that's the dog. We have a dog too. That's the dog I want to let in. Maybe I don't want to let this other animal in because it's a raccoon. So you can see where you could take this one step further and actually apply this. You could actually start a little startup company idea, a self-identifying door. So this use case will be implemented on Python. I am actually in Python 3.6. It's always nice to tell people the version of Python because that does affect sometimes which modules you load and everything. And we're going to start by importing the required packages. I told you we're going to do this in Keras. So we're going to import from Keras models, a sequential from the Keras layers, conversion 2D or CONV 2D, max pooling 2D, flatten, and dense. And we'll talk about what each one of these do in just a second. But before we do that, let's talk talk a little bit about the environment we're going to work in. And in fact, let me go ahead and open the website, Keras' website, so we can learn a little bit more about Keras. So here we are on the Keras website, and it's keras.io. That's the official website for Keras. And the first thing you'll notice is that Keras runs on top of either TensorFlow, CNTK, and I think it's pronounced Thano or Theano. What's important on here is that TensorFlow, and the same is true for all these, but TensorFlow is probably one of the most widely used currently packages out there with the Keras. And of course, tomorrow this is all going to change. It's all going to disappear and they'll have something new out there. So make sure when you're learning this code that you understand what's going on and also know the code. I mean, when you look at the code, it's not as complicated once you understand what's going on. The code itself is pretty straightforward. And the reason we like Keras, and the reason that people are jumping on it right now and it's such a big deal is if we come down here, let me just scroll down a little bit, they talk about user friendliness, modularity, easy extensibility, work with Python. Python's a big one because a lot of people in data science now use Python, although you can actually access Keras other ways. If we continue down here is layers. And this is where it gets really cool. When we're working with Keras, you just add layers on. Remember those hidden layers we were talking about? And we talked about the ReLU activation. You can see right here. Let me just up that a little bit in size. There we go. That's big. I can add in an ReLU layer, and then I can add in a softmax layer in the next instance. We didn't talk about softmax. So you can do each layer separate. Now, if I'm working in some of the other kits I use, I take that and I have one setup, and then I feed the output into the next one. This one I can just add hidden layer after hidden layer with the different information in it, which makes it very powerful and very fast to spin up and try different setups and see how they work with the data you're working on. And we'll dig a little bit deeper in here. And a lot of this is very much the same, so when we get to that part, I'll point that out to you also. Now, just a quick side note, I'm using Anaconda with Python in it, and I went ahead and created my own package, and I called it the Keras Python 3.6 because I'm in Python 3.6. Anaconda is cool that way. You can create different environments real easily. If you're doing a lot of different experimenting with these different packages, you probably want to create your own environment in there. And the first thing is you can see right here, there's a lot of dependencies. A lot of these you should recognize by now if you've done any of these videos. If not, kudos for you for jumping in today. Pip install numpy, scipy, the scikit-learn, pillow, and h5py are both needed for the TensorFlow and then putting the Keras on there. And then you'll see here, and pip is just a standard installer that you use with Python. And you'll see here that we did pip install TensorFlow since we're going to do Keras on top of TensorFlow. And then pip install, and I went ahead and used the GitHub. So git plus git, and you'll see here github.com. This is one of their releases, one of the most current release on there that goes on top of TensorFlow. And you can look up these instructions pretty much anywhere. This is for doing it on Anaconda. Certainly you'd want to install these if you're doing it in Ubuntu server setup. You'd want to get, I don't think you need the h5py in Ubuntu, but you do need the rest in there because there are dependencies in there, and it's pretty straightforward. And that's actually in some of the instructions they have on their website. So you don't have to necessarily go through this. Just remember their website on there. And then when I'm under my Anaconda navigator, which I like, you'll see where I have environments, and on the bottom I created a new environment and I called it Keras Python 36, just to separate everything. You can say I have Python 30.5 and Python 3.6. I used to have a bunch of other ones, but I kind of cleaned house recently. And of course, once I go in here, I can launch my Jupyter Notebook, making sure I'm using the right environment that I just set up. This, of course, opens up my, in this case I'm using Google Chrome, and in here I could go and just create a new document in here. And this is all in your browser when you use the Anaconda. Do you have to use Anaconda in Jupyter Notebook? No. You can use any kind of Python editor, whatever setup you're comfortable with and whatever you're doing in there. So let's go ahead and go in here and paste the code in. And we're importing a number of different settings in here. We have import sequential. That's under the models because that's the model we're going to use as far as our neural network. And then we have layers, and we have conversion 2D, max pooling 2D, flatten, dense, and you can actually just kind of guess at what these do. We're working in a 2D photograph, and if you remember correctly, I talked about how the actual input layer is a single array. It's not in 2 dimensions, it's 1 dimension. All these do is these are tools to help flatten the image, so it takes a 2-dimensional image and then it creates its own proper setup. You don't have to worry about any of that. You don't have to do anything special with the photograph photograph, you let the Keras do it. And we're going to run this, and you'll see right here they have some stuff that is going to be depreciated and changed, because that's what it does. Everything's being changed as we go. You don't have to worry about that too much. If you have warnings, if you run it a second time, the warning will disappear. And this has just imported these packages for us to use. And Jupyter's nice about this, that you can do each thing step by step. And I'll go ahead and also zoom in there. A little Control Plus. That's one of the nice things about being in a browser environment. So here we are back. Another sip of coffee. If you're familiar with my other videos, you notice I'm always sipping coffee. I always have in my case, latte next to me, an espresso. So the next step is to go ahead and initialize, we're going to call it the CNN, or classifier neural network. And the reason we call it a classifier is because it's going to classify it between two things. It's going to be cat or dog. So when you're doing classification, you're picking specific objects. You're specific, it's a true or false, yes, no, it is something or it's not. So first thing, we're going to create our classifier, and it's going to equal sequential. So their sequential setup is the classifier. That's the actual model we're using. That's the neural network. So we call it a classifier. And the next step is to add in our convolution. And let me just do let me shrink that down in size so you can see the whole line. And let's talk a little bit about what's going on here. I have my classifier and I add something. What am I adding? Well, I'm adding my first layer. This first layer we're adding in is probably the one that takes the most work to make sure you have it set correct. And the reason I say that is this is your actual input. And we're going to jump here to the part that says input shape equals 64 by 64 by 3. What does that mean? Well, that means that our picture's coming in, and there's these pictures. Remember we had like the picture of the car was 128 by 128 pixels? Well, this one is 64 by 64 pixels. And each pixel has 3 values. That's where these numbers come from. And it is so important that this matches. I mentioned a little bit that if you have like a larger picture, you have to reformat it to fit this shape. If it comes in as something larger, there's no input nodes. There's no input neural network there that will handle that extra space. So you have to reshape your data to fit in here. Now, the first layer is the most important, because after that, Keras knows what your shape is coming in here, and it knows what's coming out. And so that really sets the stage. Most important thing is that input shape matches your data coming in. And you'll get a lot of errors if it doesn't. You'll go through there and picture number 55 doesn't match it correctly. And guess what it does? It usually gives you an error. And then the activation, if you remember, we talked about the different activations on here. We're using the ReLU model. Like I said, that is the most commonly used now because, one, it's fast. It doesn't have the added calculations in it. It just says, here's the value coming out based on the weights and the value going in, and from there, you know, it's if it's over 1, then it's good, or over 0, it's good. If it's under 0, then it's considered not active. And then we have this conversion 2D. What the heck is conversion 2D? I'm not going to go into too much detail in this because this has a couple of things it's doing in here. A little bit more in-depth than we're ready to cover in this tutorial. But this is used to convert from the photo, because we have 64 by 64 by 3, and we're just converting it to two-dimensional kind of setup. So it's very aware that this is a photograph and that different pieces are next to each other. And then we're going to add in a second convolutional layer. That's what the CONV stands for, 2D. So these are hidden layers. So we have our input layer and our 2 hidden layers, and they are two-dimensional because we're dealing with a two-dimensional photograph. And you'll see down here that on the last one we add a max pooling 2D, and we put a pool size equals 2, And so what this is that as you get to the end of these layers, one of the things you always want to think of is what they call mapping and then reducing. Wonderful terminology from the big data. We're mapping this data through all these layers, and now we want to reduce it to only 2 sets. In this case, it's already in 2 sets because it's a 2D photograph. But we had, 2 dimensions we actually have 64 by 64 by 3. So now we're just getting it down to a 2 by 2, just the two-dimensional instead of having the third dimension of colors. And we'll go ahead and run these. We're not really seeing anything on our run script because we're just setting up. This is all set up. And this is where you start playing, because maybe you'll add a different layer in here to do something else to see how it works and see what your output is. That's what makes Keras so nice, is I can, with just a couple flips of code, put in a whole new layer that does a whole new processing and see whether that improves my run or makes it worse. And finally, we're going to do the final setup, which is to flatten. classifier add a flatten setup, and then we're going to also add a dense layer, and then we're going to add in another dense layer, and then we're going to build it. We're going to compile this whole thing together. So let's flip over and see what that looks like. And we've even numbered them for you, so we're going to do the flattening. And flatten is exactly what it sounds like. We've been working in a two-dimensional array of picture, which actually is in 3 dimensions because of the pixels. The pixels have a whole other dimension to it of 3 different values. And we've kind of resized those down to 2 by 2, but now we're just going to flatten it. I don't want to have multiple dimensions being worked on by tensor and by Keras. I want just a single array, so it's flattened out. And then step 4, full connection. So we add in our final 2 layers, and you could actually do all kinds of things with this. You could actually leave out this some of these layers and play with them. You do need to flatten it. That's very important. Then we want to use the dense. Again, we're taking this and we're taking whatever came into it. So once we take all those the 2 dimensions or 3 dimensions as they are, and we flatten it to 1 dimension, we want to take that and we're going to pull it into units of 128. They got that. You're going to say, where did they get 128 from? You could actually play with that number and get all kinds of weird results. But in this case, we took the 64 plus 64 is 128. You could probably even do this with 64 or 32. Usually you want to keep it in the same multiple of whatever the data shape you're already using is in. And we're using the activation, the RELU, just like we did before. And then we finally filter all that into a single output. And it has how many units? 1. Why? Because we want to know whether true or false. It's either a dog or a cat. You could say 1 is dog, 0 is cat. Or maybe you're a cat lover and it's 1 is cat and 0 is dog. And if you love both dogs and cats, you're going to have to choose. And then we use the sigmoid activation. If you remember from before, we had the RELU and there's also the sigmoid. The sigmoid just makes it clear it's yes or no. We don't want any kind of in-between number coming out. And we'll go ahead and run this, and you'll see it's still all in setup. And then finally we want to go ahead and compile. And let's put the compiling our classifier neural network, and we're going to use the optimizer Atom. And I hinted at this just a little bit before. Where does Atom come in? Where does an optimizer come in? Well, the optimizer is the reverse propagation. When we're training it, it goes all the way through and says error, and then how does it readjust those weights? There are a number of them. Atom is the most commonly used, and it works best on large data. Most people stick with the Atom because when they're testing on smaller data, see if their model is going to go through and get all their errors out before they run it on larger data sets. They're going to run it on Atom anyway, so they just leave it on Atom, most commonly used. But there are some other ones out there. You should be aware of that you might try them if you're stuck in a bind, or you might explore that in the future. But usually Atom is just fine on there. And then you have 2 more settings. You have loss and metrics. We're not going to dig too much into loss or metrics. These are things you really have to explore Keras because there are so many choices. This is how it computes the error. There's so many different ways on your back propagation and your training. So we're using the Atom model, but you can compute the error by standard deviation squared. They use binary cross entropy. I'd have to look that up to even know what that is. There's so many of these. A lot of times you just start with the ones that look correct, that are most commonly used, and then you have to go read the Keras site and actually see what these different losses and metrics and what different options they have. So we're not going to get too much into them other than to reference you over to the Keras website to explore them deeper. But we are going to go ahead and run them, and now we've set up our classifier. So we have an object classifier, and if you go back up here you'll see that we've added in step 1, we added in our layer for the input. We added a layer that comes in there and uses the RELU for activation, and then it pulls the data. So this is, even though these are 2 layers, the actual neural network layer is up here, and then it uses this to pull the data into a 2 by 2. So into a 2-dimensional array from a 3-dimensional array with the colors. Then we flatten it. So there's our add or flatten. And then we add another dense, what they call dense layer. This dense layer goes in there and it downsizes it to 128. It reduces it. So you can look at this as we're mapping all this data down the 2-dimensional setup, and then we flatten it. So we map it to a flattened map, and then we take it and reduce it down to 128. And we use the RELU again. And then finally we reduce that down to just a single output, and we use the sigmoid to do that, to figure out whether it's yes, no, true, false, in this case cat or dog. And then finally, once we put all these layers together, we compile them. That's what we've done here. And we've compiled them as far as how it trains to use these settings for the training, back propagation. So if you remember, we talked about training our setup. And when we go into this, you'll see that we have two data sets. We have one called the training set and the testing set. And that's very standard in any data processing, is you need to have, that's pretty common in any data processing, is you need to have a certain amount of data to train it, and then you got to know whether it works or not. Is it any good? And that's why you have a separate set of data for testing it, where you already know the answer, but you don't want to use that as part of the training set. So in here we jump into part 2, fitting the classifier neural network to the images. And then from cross, and let me just zoom in there. I always love that about working with Jupyter notebooks. You can really see. We're going to come in here. We do the cross pre-processing an image, and we import image data generator. It's so nice of Keras. It's such a high-end product right now going out. And since images are so common, they already have all this stuff to help us process the data, which is great. And so we come in here. We do train data gen, and we're going to create our object for helping us train it, for reshaping the data so that it's going to work with our setup. And we use an image data generator, and we're going to rescale it. And you'll see here we have 1 point, which tells us it's a float value on the rescale over 255. Where does 255 come from? Well, that's the scale in the colors of the pictures we're using. Their value from 0 to 255. So we want to divide it by 255, and it'll generate a number between 0 and 1. They have shear range and zoom range. Horizontal flip equals true. And this, of course, has to do with if the photos are different shapes and sizes. Like I said, it's a wonderful package. You really need to dig in deep to see all the different options you have for setting up your images. For right now, though, we're going to just stick with some basic stuff here. And let me go ahead and run this code. And again, it doesn't really do anything because we're still setting up the pre-processing. Let's take a look at this next set of code. And this one is just huge. We're creating the training set. So the training set is going to go in here, and it's going to use our train data gen we just created, .flow from directory. It's going to access, in this case, the path, data set, training set. That's a folder. So it's going to pull all the images out of that folder. Now, I'm actually running this in the folder that the data set's in. So if you're doing the same setup and you load your data in there and you're doing this, make sure wherever your Jupyter notebook is saving things to that you create this path, or you can do the complete path if you need to, C:/, etc. And the target size, the batch size, and class mode is binary. So the classes, we're switching everything to a binary value. Batch size, what the heck is batch size? Well, that's how many pictures we're going to batch through the training each time. And the target size, 64 by 64. A little confusing, but you can see right here that this is just a general training, and you can go in there and look at all the different settings for your training set. And of course, with different data, we're doing pictures. There's all kinds of different settings depending on what you're working with. Let's go ahead and run that and see what happens. And you'll see that it found 800 images belonging to one classes. So we have 800 images in the training set. And if we're going to do this with the training set, we also have to format the pictures in the test set. Now, we're not actually doing any predictions. We're not actually programming the model yet. All we're doing is preparing the data. So we're going to prepare a training set and the test set. So any changes we make to the training set at this point also have to be made to the test set. So we've done this thing. We've done a train data generator. We've done our training set, and then we also have, remember, our test set of data. So I'm going to do the same thing with that. I'm going to create a test data gen, and we're going to do this image data generator. We're going to rescale 1 over 255. We don't need the other settings, just the single setting for the test data gen. And we're going to create our test set. We're going to do the same thing we did with the test set, except that we're pulling it from the test set folder. And we'll run that, and you'll see in our test set we found 2,000 images. That's about right. We're using 20% of the images as test and 80% to train it. And then finally we've set up all our data. We've set up all our layers, which is where all the work is cleaning up that data and making sure it's going in there correctly. And we are actually going to fit it. We're going to train our data set. And let's see what that looks like. And here we go. Let's put the information in here. And let's just take a quick look at what we're looking at with our fit generator. We have our classifier.fit generator. That's our backpropagation. So the information goes through forward with a picture, and it says, oh, you're either right or you're wrong, and then the error goes backward and reprograms all those weights. So we're training our neural network. And of course we're using the training set. Remember, we created the training set up here, and then we're going steps per epoch. So it's 8,000 steps. Epic means that's how many times we go through all the pictures. So we're going to rerun each of the pictures, and we're going to go through the whole data set 25 times. But we're going to look at each picture during each epic 8,000 times. So we're really programming the heck out of this and going back over it. And then they have validation data equals test set. So we have our training set, and then we're going to have our test set to validate it. So we're going to do this all in one shot. And we're going to look at that, and they're going to do 200 steps for each validation. And we'll see what that looks like in just a minute. Let's go ahead and run our training here. And we're going to fit our data. And as it goes, it says epic 1 of 25. You start realizing that this is going to take a while. On my older computer, it takes about 45 minutes. I have a dual processor. We're processing 10,000 photos. That's not a small amount of photographs to process. So if you're on your laptop, which I am, it's going to take a while. So let's go ahead and go get our cup of coffee and a sip and come back and see what this looks like. So I'm back. You didn't know I was gone. That was actually a lengthy pause there. I made a couple changes, and let's discuss those changes real quick and why I made them. So the first thing I'm going to do is I'm going to go up here and insert a cell above, and let's paste the original code back in there. And you'll see that the original thing was steps per epic 8,000, 25 epics, and validation steps 2,000. And I changed these to 4,000 epics, or 4,000 steps per epic, 10 epics, and just 10 validation steps. And this will cause problems if you're doing this as a commercial release. But for demo purposes, this should work. And if you remember, our steps per epic, that's how many photos we're going to process. In fact, let me go ahead and get my drawing pen out. And let's just highlight that right here. Well, we have 8,000 pictures we're going through. So for each epic, I'm going to change this to 4,000. I'm going to cut that in half. So it's going to randomly pick 4,000 pictures each time it goes through an epic. And the epic is how many processes. So this is 25, and I'm just going to cut that to 10. So instead of doing 25 runs through 8,000 photos each, which you can do the math of 25 times 8,000, I'm only going to do 10 through 4,000. So I'm going to run this 40,000 times through the processes. And the next thing I noted you'll want to notice is that I also changed the validation step. And this would cause some major problems in releasing because I dropped it all the way down to 10. What the validation step does is it says we have 2,000 photos in our trainings or in our testing set. And we're going to use that for validation. Well, I'm only going to use a random 10 of those to validate. So not really the best settings, but let me show you why we did that. Let's scroll down here just a little bit. And let's look at the output here and see what's going on there. So I've got my drawing tool back on, and you'll see here it lists a run. So each time it goes through an epic, it's going to do 4,000 steps. And this is where the 4,000 comes in. So that's where we have epic 1 of 10, 4,000 steps. So it's randomly picking half the pictures in the file and going through them. And then we're going to look at this number right here. That is for the whole epic. And that's 2,411 seconds. And if you remember correctly, you divide that by 60, you get minutes. If you divide that by 60, you get hours. Or you can just divide the whole thing by 60 times 60, which is 3,600. If 3,600 is an hour, this is roughly 45 minutes right here. And that's 45 minutes to process half the pictures. So if I was doing all the pictures, we're talking an hour and a half per epic times 36. Or no, 25. They had 25 up above. 25. So that's roughly a couple days of processing. Well, for this demo, we don't want to do that. I don't want to come back the next day. Plus, my computer did a reboot in the middle of the night. So we look at this and we say, okay, we're just testing this out. My computer that I'm running this on is a dual core processor, runs 0.9 gigahertz per second. For a laptop, it was good about 4 years ago, but for running something like this, it's probably a little slow. So we cut the times down. And the last one was validation. We're only validating it on a random 10 photos. And this comes into effect because you're going to see down here where we have accuracy, value loss, value accuracy, and loss. Those are very important numbers to look at. So the 10 means I'm only validating across 10 pictures. That is where, here we have value, this is ACC is for accuracy. Value loss, we're not going to worry about that too much, and accuracy. Now accuracy is while it's running, it's putting these two numbers together. That's what accuracy is. And value accuracy is at the end of the epic. What's our accuracy at the end of the epic? What is it looking at? In this tutorial, we're not going to go so deep, but these numbers are really important when you start talking about these two numbers. reflect bias. That is really important. I'll just put that up there. And bias is a little bit beyond this tutorial, but the short of it is if this accuracy, which is being our validation per step, is going down, and the value accuracy continues to go up, that means there's a bias. That means I'm memorizing the photos I'm looking at. I'm not actually looking for what makes a dog, what makes a cat. I'm just memorizing them. And so the more this discrepancy grows, the bigger the bias is. And that is really the beauty of the Keras neural network. It has a lot of built-in features like this that make that really easy to track. So let's go ahead and take a look at the next set of code. So here we are into part 3. We're going to make a new prediction. And so we're going to bring in a couple tools for that, and then we have to process the image coming in and find out whether it's an actual dog or cat, if we can actually use this to identify it. And of course the final step of part 3 is to print prediction. We'll go ahead and combine these, and of course you can see me there adding more sticky notes to my computer screen, hidden behind the screen, and last one was don't forget to feed the cat and the dog. So let's go ahead and take a look at that and see what that looks like in code and put that in our Jupyter notebook. All right, and let's paste that in here. And we'll start by importing NumPy as NP. NumPy is a very common package. I pretty much import it on any Python project I'm working on. Another one I use regularly is pandas. They're just ways of organizing the data. And then NP is usually the standard in most machine learning tools as a return for the data array. Although, you can use a standard data array from Python. And we have Keras pre-processing, import image. This should all look familiar because we're going to take a test image and we're going to set that equal to, in this case, cat or dog 1, as you can see over here. And let me get my drawing tool back on. So let's take a look at this. We have our test image we're loading, and in here we have test image 1, and this one data hasn't seen this one at all, so this is all new. Oh, let me shrink the screen down. Let me start that over. So here we have my test image, and we went ahead and the Keras processing has this nice image setup. So we're going to load the image and we're going to alter it to a 64 by 64 print. So right off the bat, Keras is nice that way. It automatically sets it up for us so we don't have to redo all our images and find a way to reset those. And then we use all those to set the image to an array. So again, we're all in pre-processing the data, just like we pre-processed before with our test information and our training data. And then we use the NumPy. Here's our NumPy. That's from our right up here, import NumPy as NP. Expand the dimensions, test image, axes equals 0. So it puts it into a single array. And then finally, all that work, all that pre-processing, and all we do is we run the result. We click on here and we go result equals classifier predict test image, and then we find out, well, what is the test image? And let's just take a quick look and just see what that is. And you can see when I ran it, it comes up dog, and if we look at those images, there it is, cat or dog, image number 1. That looks like a nice floppy-eared lab, friendly with his tongue hanging out. It's either that or a very floppy-eared cat. I'm not sure which. But according to our software, it says it's a dog. And we have a second picture over here. Let's just see what happens when we run the second picture. We can go up here and change this from dog image 1 to 2. We'll run that, and it comes down here and says cat. You can see me highlighting it down there as cat. So our process works. We are able to label a dog and a cat just from the pictures. There we go, cleared my drawing tool. And the last thing I want you to notice, when we come back up here to when I ran it, you'll see it has an accuracy of 1 and the value accuracy of 1. Well, the value accuracy is the important one because the value accuracy is what it actually runs on the test data. Remember, I'm only validating it on a random 10 photos. And those 10 photos just happen to come up 1. Now, when they ran this on the server, it actually came up about 86%. This is why cutting these numbers down so far for a commercial release is bad. So you want to make sure you're a little careful of that when you're testing your stuff, that you change these numbers back when you run it on a more enterprise computer other than your old laptop that you're just practicing on or messing with. And we come down here and again, we had the validation of cat. And so we have successfully built a neural network that could distinguish between photos of a cat and a dog. Imagine all the other things you could distinguish. Imagine all the different industries you could dive into with that, just being able to understand those two different pictures. What about mosquitoes? Could you find the mosquitoes that bite versus the mosquitoes that are friendly? It turns out the mosquitoes that bite us are only 4% of the mosquito population, if even that, maybe 2%. There's all kinds of industries that use this, and there's so many industries that are just now realizing how powerful these tools are. Just in the photos alone, there is a myriad of industries sprouting up. And I said it before, I'll say it again, what an exciting time to live in with these tools that we get to play with. Backpropagation and gradient descent, we're talking neural networks. So we talk about the neural network. This is a simple neural network which must be trained to recognize handwritten alphabets A, B, and C. And you can see here we have our input coming in. In this case, we'll look at the letter A written out on a 28 by 28 pixels. So the handwritten alphabets are presented as images of 28 by 28 pixels. And that image comes in this case we have 784 neurons, that's 28 times 28. And the initial prediction is made using random weights assigned to each channel. And so we have our forward propagation as you see here. So each node is then, their values are added up and so on going across. And our network predicts the input to be B with a probability of 0.5. The predicted probabilities are compared against the actual probabilities and the error is calculated. So the error is simply the actual minus predicted. And you can see here where we know it's not C, so it's a -2. We know it's not B, so it's a -0.5. But we do know that it is A, so we go ahead and adjust that by 0.6. The magnitude indicates the amount of change, while the sign indicates an increase or decrease in the weights. The information is transmitted back through the network. So here comes our back propagation. Weights throughout the network are adjusted in order to reduce the loss in prediction. So if we look at this setup right here, here comes our error. In this case, 0.6 minus 0.5 minus 0.2. That comes up and adjusts our 1.4, 0.9, all our multipliers. In this manner, we keep training the network with multiple inputs until it is able to predict with a high accuracy. And you can see here we have a different A, quickly switches from cursive A to maybe a more elongated A. Similarly, our network is trained with the images for B and C too. So let's take a look at this. Here's a straightforward data set. So let's build a neural network to predict the outputs given the inputs. And so we have an input 0, we expect an output of 0, we have an input of 1, we expect 6, 2 equals 12, 3 should come out as 18, and 4 as 24. And we're just doing multiples of 6 if you take the time to look at it. So in our example, we have our input, and it goes into our neural network. So this box represents our neural network. One of the cool things about neural networks is they're always this little black box that you kind of train to do what you want. And you really don't have to know exactly what the weights are, although there are some very high-end setups to start looking at those weights and how they work and what they do. And then you get your output, which is going to be, in this case, our input's going to be X and our output's going to be Y. And W is the weight. So we have value times the weight. So if we're doing, in this case, just a single neuron going through, we have X times W. The network starts training itself by choosing a random value for W. We're going to guess that W equals 3. Just roll the dice, randomly generate the number 3 for W. And then we put W equals 3 in here. We have our input 0 or output 0, W equals 3 equals 0. So we have no error on the first line. That actually comes out correct. And then we have 1 times, we put the 1 in. We're looking for a 6, but we get a 3 instead. And we put the 2 in, we're looking for a 12, and we get a 6 instead. So you can see here our predicted output doesn't match the output we're looking for. And then we take this, we have our W equals 3, and we come up with the second model where the W equals 6. Now we're going to look at how we figure out W equals 6 in just a minute. That is part of the math behind this. But you can see here when we put in W equals 6, and we build the W equals 6 chart, we end up with 0, 6, 12, 18, 24, which is the output we're looking for. And in that manner, we end up with the correct answer, but we'll go ahead and put in a third model where W equals 9. So at this point, this is one way of doing this is just to guess what W equals. And you can see with W equals 9, we get the incorrect answers. We get 9, 18, 27, 36. We as humans can know just by taking a look at the data that our weight should be 6. But how does the machine come to this conclusion? How do we program the computer to learn instead of waiting for us to tell it has the right answer or what the correct answer is? And you can imagine this is a very simple problem. If we're doing guessing W equals 3, we guess W equals 6, we guess W equals 9, and then we look at our results and we go, oh, it's got to be W equals 6. That's the best result. But as humans, we want to take that element out and have the computer do that for us. So with that, we're going to have a loss function. The loss function is a measure of error which defines the precision lost to comparing the predicted output to the actual output. And it's simply loss equals actual output minus predicted output, and then we square the whole thing. So let's apply the loss function to the input value 2. Loss for our actual output, predicted output squared. And our loss function for the input of 2, we end up with an actual output of 12. And you can see here with W equals 3, 12 minus 6 squared equals 36. So we end up with a loss of 36. W equals 6, 12. 12 times 12 squared equals, 12 minus 12 squared equals 0. Or 12 minus 18 squared equals 36. And so you can see we have a huge loss on W equals 3 and W equals 9. We now plot a graph for the weight versus loss. And it always helps to have a nice visual of what's going on here. So this graphical method of finding the minimal of a function is called gradient descent. And this is the logic behind this. You can see as we come in here and we go ahead and graph the loss, we have 36 for 3 and 36 for 9. We happen to guess 6, which was the correct answer right in the middle. And you can see right here it forms a nice little parabola. And you can see a nice mark right in the middle. And as a human being, we can look at that and we go, the answer is 6. A random point on this curve is chosen, and the slope at this point is calculated. So now we're getting away from the human aspect of just looking at it and saying what the answer is, and we look at what's going on with the math. And so if we have a positive slope, it indicates an increase in the weight, and a negative slope indicates a decrease in weight. This time the slope is negative, hence another random point towards its left is chosen. And you can see here we're actually kind of just playing a little high-low game going back and forth with the gradient descent. We continue checking slopes at various points in this manner. So we have our input, actual output, W3, W6, W9. We found our positive slope increase in weight. A negative slope indicates a decrease in weight. A zero slope indicates the appropriate weight. So our aim is to reach a point where the slope is 0. And when we talk about neural networks, you're usually processing a massive amount of information and data. So you're not going to have all your data nice and neat where it's just a multiple of 6. It's going to be messy. And so we're going to keep approaching that number, but you'll never get everything to fit at 0. You're going to get stuff all over the place, and so you're really looking for the minimum value. You're not looking for an absolute 0 because you're not going to get it. And so we're talking about gradient descent. That's what we're talking about on there, is finding the bottom of that curve even if it doesn't go all the way to 0. So how do we apply that to our neural network? Well, we use backpropagation. Backpropagation is a process of updating weights of the network in order to reduce the error in prediction. And so the magnitude of loss of any point on our graph combined with the slope is fed back to the network. And you can see here, here's our simple model with just one node of x times w. The input comes in, we have our x times w, the output, and then we're going to propagate that loss going the other way. A random point on the graph gives a loss value of 36 with a positive slope, and we continue checking slopes at various points in this manner. So a random point on the graph gives a loss value of 36 with a positive slope. 36 is quite a large number. This means our current weight needs to change by a large number. A positive slope indicates that the change of the weight must be positive. Similarly, another random point on the graph gives a loss value of 10 with a negative slope. 10 is a small number, hence the weight requires to be tuned quite less. A negative slope indicates that the weight needs to be reduced rather than increased. After multiple iterations of backpropagation, our weights are assigned the appropriate value. And you can see here we have our input we just looked at, x times 6, and our output. And eventually we get it that the weight is 6 for the single node problem that we're working on right now. At this point, our network is trained and can be used to make predictions. Let's now get back to our first example and see where the backpropagation and gradient descent fall into place. And you can see here we're not looking at a single node anymore. Now we have 28 by 28 grid, or 784 inputs coming into the first level, which has 784 nodes. Depending on how you build your neural network, the next layer might also have 784 nodes, or it might continually smallen depending on what you need and what's needed for that to work. So as mentioned earlier, our predicted output is compared against the actual output. And you can see our error over here, actual minus prediction, and then we go ahead and compute our loss. So the loss of A is 0.7 squared equals 0.49. Loss of B is 0.5 squared or 0.25, and so on. So now we have our first iteration on there. So weights throughout the network are adjusted in order to reduce the loss in prediction. And of course we do that by doing a second iteration coming through with our different losses on there. And then weights throughout the network are adjusted in order to reduce the loss in prediction again underneath the second. And we do a third iteration. And we just keep doing these iterations going back until we get the right value. Now you got to remember that when we're doing a reverse propagation, we're not looking at just one letter A. We're looking at hundreds of letter A's. And usually when we propagate that loss going backwards, we only take a small piece of it. So our adjustments are very small because one of them is not correct. We don't want to create a bias. So when we talk about backpropagation, we're talking about going through over and over and over this data until we get minimal loss for our letter A. So let's focus on the minimal loss for our variable A. And you can see here, when we look at that, we end up, we'll assume for below to be our graph for the loss of prediction with the variable A as compared to the weights continuing it from the second layer. And we have our loss of A for 49, for 16, for 0.04. And you can see it makes this nice curve where we can guess where the bottom of this curve is. And I like it on this graph that they show that the curve doesn't rest, on the x-axis. It doesn't rest at where y equals 0 because you usually don't get that. You don't get a perfect fit on anything, or very rarely do you ever get a perfect fit. And so the random points chosen on the graph is now backpropagated through the network in order to adjust the weights. So we're able to go back through the network and readjust those weights until we find that minimal value. The network is run once again with the new weights. This process is repeated multiple times till it provides accurate predictions. The weights are further adjusted to identify B and C too. And this is interesting because you actually do them at the same time. So as the error goes back, you kind of find the overall error for all the inputs coming in, and then that's what gets propagated going back, or the overall loss. Kind of have to step away from that word error because it's not just about the error, it's about the loss. The weights are further adjusted to identify B and C too. And so a lot of times you actually do them all at the same time, but you'll adjust those weights A, B, and C, as I was just saying. Thus, through gradient descent and backpropagation, our network is completely trained. And we've taught it to identify A, B, and C coming forward. One of the interesting things about neural networks is the training process takes a lot longer than the predicting process. So you can plan one of these training neural networks doing the backpropagation to significantly longer because you're going over thousands of data points. And then when you actually run it forward, it's very quick, which makes these things very useful and just really part of today's world in computing. Today we're going to be covering the convolutional neural network tutorial. Do you know how deep learning recognizes the objects in an image? And really, this particular neural network is how image recognition works. It's very central, one of the biggest building blocks for image recognition. It does it using convolution neural network. And over here we have the basic picture of a hummingbird. Pixels of an image fed as input. You have your input layer coming in. So it takes that graphic and puts it into the input layer. You have all your hidden layers. And then you have your output layer, and your output layer, one of those is going to light up and say, oh, it's a bird. We're going to go into depth. We're going to actually go back and forth on this a number of times today. So if you're not catching all the image, don't worry, we're going to get into the details. So we have our input layer accepts the pixels of the image as input in the form of arrays. And you can see up here where they've actually labeled each block of the bird in different arrays. So we'll dive into deep as to how that looks like and how those matrices are set up. Your hidden layer carry out feature extraction by performing certain calculations and manipulations. So this is the part that kind of reorganizes that picture multiple ways until we get some data that's easy to read for the neural network. This layer uses a matrix filter and performs convolution operation to detect patterns in the image. And if you remember that convolution means to coil or to twist. So we're going to twist the data around and alter it and use that operation to detect a new pattern. There are multiple hidden layers like convolution layer. ReLU is how that is pronounced. And that's the rectified linear unit. That has to do with the activation function that's used. Pooling layer also uses multiple filters to detect edges, corners, eyes, feathers, beak, etc. And just like the term says, pooling is pooling information together. And we'll look into that a lot closer here. So if it's a little confusing now, we'll dig in deep and try to get you squared away with that. And then finally, there is a fully connected layer that identifies the object in the image. So we have these different layers coming through in the hidden layers, and they come into the final area, and that's where we have, say, one node or one neural network entity that lights up that says it's a bird. What's in it for you? We're going to cover an introduction to the CNN, what is convolution neural network, how CNN recognizes images. We're going to dig deeper into that and really look at the individual layers in the convolutional neural network. And finally, we do a use case implementation using the CNN. We'll begin our introduction to the CNN by introducing the pioneer of convolutional neural network, Yann LeCun. He was the director of Facebook AI Research Group. Built the first convolutional neural network called LeNet in 1988. So these have been around for a while and have had a chance to mature over the years. It was used for character recognition tasks like reading zip code digits. Imagine processing mail and automating that process. CNN is a feed-forward neural network that is generally used to analyze visual images by producing data with a grid-like topology. A CNN is also known as a convnet. And very key to this is we are looking at images. That was what this was designed for, and you'll see the different layers as we dig in mirror some of them are actually now used since we're using TensorFlow and Keras in our code later on. You'll see that some of those layers appear in a lot of your other neural network frameworks. But in this case, this is very central to processing images and doing so in a variety that captures multiple images and really drills down into their different features. In this example here you see flowers of two varieties, orchid and a rose. I think the orchid is much more dainty and beautiful, and the rose smells quite beautiful. I have a couple rose bushes in my yard. They go into the input layer. That data is then sent to all the different nodes in the next layer, one of the hidden layers, based on its different weights and its setup. It then comes out and gives those a new value. Those values then are multiplied by their weights and go to the next hidden layer, and so on. And then you have the output layer, and one of those nodes comes out and says it's an orchid, and the other one comes out and says it's a rose, depending on how well it was trained. What separates the CNN, or the convolutional neural network, from other neural networks is a convolutional operation. Forms the basis of any convolutional neural network. In a CNN, every image is represented in the form of arrays of pixel values. So here we have a real image of the digit 8. That then gets put onto its pixel values, represented in the form of an array. In this case, you have a two-dimensional array. And then you can see in the final end form, we transform the digit 8 into its representational form of pixels of zeros and ones, where the ones represent, in this case, the black part of the 8, and the zeros represent the white background. To understand the convolution neural network, or how that convolutional operation works, we're going to take a sidestep and look at matrices. In this case, we're going to simplify it, and we're going to take two matrices, A and B, of one dimension. Now, kind of separate this from your thinking as we learn that you want to focus just on the matrix aspect of this. And then we'll bring that back together and see what that looks like when we put the pieces for the convolutional operation. Here we've set up two arrays. We have, in this case, they're a single dimension matrix. And we have A equals 5, 3, 7, 5, 9, 7. And we have B equals 1, 2, 3. So in the convolution, as it comes in there, it's going to look at these two, and we're going to start by multiplying them, A times B. And so we multiply the arrays element-wise, and we get 5, 6, 6, where 5 is the 5 times 1, 6 is 3 times 2, and then the other 6 is 2 times 3. And since the two arrays aren't the same size, they're not the same setup, we're going to just truncate the first one, and we're going to look at the second array multiplied just by the first three elements of the first array. Now that's going to be a little confusing. Remember, a computer gets to repeat these processes hundreds of times, so we're not going to just forget those other numbers later on. We'll bring those back in. And then we have the sum of the product. In this case, 5 plus 6 plus 6 equals 17. So in our A times B, our very first digit in that matrix of A times B is 17. And if you remember, I said we're not going to forget the other digits. So we now have 3, 2, 5. We move one set over, and we take 3, 2, 5, and we multiply that times B. And you'll see that 3 times 1 is 3, 2 times 2 is 4, and so on and so on. We sum it up, so now we have the second digit of our A times B product in the matrix. And we continue on with that same thing, so on and so on. So then we would go from 375 to 759 to 597. This short matrix that we have for A, we've now covered all the different entities in A that match three different levels of B. Now, in a little bit, we're going to cover where we use this math at, this multiplying of matrices and how that works. But it's important to understand that we're going through the matrix and multiplying the different parts to it to match the smaller matrix with the larger matrix. I know a lot of people get lost at is, what's going on here with these matrices? Ooh, scary math. Not really that scary when you break it down. We're looking at a section of A and we're comparing it to B. So when you break that down in your mind like that, you realize, okay, so I'm just taking these two matrices and comparing them, and I'm bringing the value down into one matrix, A times B. We're reducing that information in a way that will help the computer see different aspects. Let's go ahead and flip over again back to our images. Here we are back to our images. Talking about going to the most basic two-dimensional image you can get to. Consider the following two images. The image for the symbol backslash. When you press the backslash, the above image is processed. And you can see there for the image for the forward slash is the opposite. So when we click the forward slash button, that flips. Very basic. We have 4 pixels going in. Can't get any more basic than that. Here we have a little bit more complicated picture. We take a real image of a smiley face. Then we represent that in the form of black and white pixels. So if this was an image in the computer, it's black and white. And like we saw before, we convert this into the zeros and ones. So where the other one would have just been a matrix of just 4 dots, now we have a significantly larger image coming in. So don't worry, we're going to bring this all together here in just a little bit. Layers in convolutional neural network. When we're looking at this, we have our convolution layer. And that really is the central aspect of processing images in the convolutional neural network. That's why we have it. And then that's going to be feeding in. And you have your ReLU layer, which is, as we talked about, the rectified linear unit. We'll talk about that a little bit later. The ReLU is how that layer is activated, is the math behind it, what makes the neurons fire. You'll see that in a lot of other neural networks. When you're using it just by itself, it's for processing smaller amounts of data, where you use the atom activation feature for large data coming in. Now, because we're processing small amounts of data in each image, the ReLU layer works great. You have your pooling layer. That's where you're pooling the data together. Pooling is a neural network term. It's very commonly used. I like to use the term reduce. So if you're coming from the map and reduce side, you'll see that we're mapping all this data through all these networks, and then we're going to reduce it. We're going to pool it together. And then finally we have the fully connected layer. That's where our output's going to come out. So we have started to look at matrices. We've started to look at the convolutional layer and where it fits in and everything. We've taken a look at images. So we're going to focus more on the convolution layer, since this is a convolutional neural network. A convolution layer has a number of filters and perform convolution operation. Every image is considered as a matrix of pixel values. Consider the following 5x5 image whose pixel values are only 0 and 1. Now, obviously, when we're dealing with color, there's all kinds of things that come in on color processing, but we want to keep it simple and just keep it black and white. And so we have our image pixels, so we're sliding the filter matrix over the image and computing the dot product to detect the patterns. And right here, you're going to ask, where does this filter come from? This is a bit confusing because the filter is going to be derived later on. We build the filters when we program or train our model. So you don't need to worry what the filter actually is, but you do need to understand how a convolution layer works, is what is the filter doing. Filter, and you'll have many filters. You don't have just one filter. You'll have lots of filters that are going to look for different aspects. And so the filter might be looking for just edges. It might be looking for different parts. We'll cover that a little bit more detail in a minute. Right now, we're just focusing on how the filter works as a matrix. Remember earlier we talked about multiplying matrices together? And here we have our two-dimensional matrix. And you can see we take the filter and we multiply it in the upper left image, and you can see right here 1 times 1, 1 times 0, 1 times 1. We multiply those all together, then sum them, and we end up with a convolved feature of 4. We're going to take that and sliding the filter matrix over the image and computing the dot product to detect patterns. So we're just going to slide this over. We're going to predict the first one and slide it over 1 notch, predict the second one, and so on all the way through until we have a new matrix. And this matrix, which is the same size as the filter, has reduced the image, and whatever filter, whatever that's filtering out, is going to be looking at just those features reduced down to a smaller matrix. So once the feature maps are extracted, the next step is to move them to the ReLU layer. So the ReLU layer, the next step, first is going to perform an element-wise operation. So each of those maps coming in, if there's negative pixels, so it sets all the negative pixels to 0. And you can see this nice graph where it just zeroes out the negatives, and then you have a value that goes from 0 up to whatever value is coming out of the matrix. This introduces nonlinearity to the network. So up until now, we say linearity. We're talking about the fact that the feature has a value. So it's a linear feature. This feature came up and it has, let's say the feature is the edge of the beak. It's like, or that backslash that we saw. It'll look at that and say, okay, this feature has a value from -10 to 10 in this case. If it was 1, it'd say, yeah, this might be a beak. It might not. It might be an edge right there. A -5 means, no, we're not even going to look at it. It's a 0. And so we end up with an output, and the output takes all these filtered features. Remember, we're not just running one filter on this, we're running a number of filters on this image. And so we end up with a rectified feature map that is looking at just the features coming through and how they weigh in from our filters. So here we have an input of it looks like a toucan bird. Very exotic looking. Real image is scanned in multiple convolution and the ReLU layers for locating features. And you can see up here, it's turned it into a black and white image. And in this case, we're looking in the upper right-hand corner for a feature, and that box scans over. A lot of times it doesn't scan 1 pixel at a time. A lot of times it will skip by 2 or 3 or 4 pixels to speed up the process. That's one of the ways you can compensate if you don't have enough resources on your computation for large images. And it's not just one filter that slowly goes across the image. You have multiple filters that have been programmed in there. So you're looking at a lot of different filters going over the different aspects of the image and just sliding across there and forming a new matrix. One more aspect to note about the ReLU layer is we're not just having one ReLU coming in. So not only do we have multiple features going through, but we're generating multiple ReLU layers for locating the features. That's very important to note. So we have quite a bundle. We have multiple filters, multiple ReLU, which brings us to the next step, forward propagation. Now we're going to look at the pooling layer. The rectified feature map now goes through a pooling layer. Pooling is a downsampling operation that reduces the dimensionality of the feature map. That's all we're trying to do. We're trying to take a huge amount of information and reduce it down to a single answer. This is a specific kind of bird. This is an iris. This is a rose. So you have a rectified feature map. And you see here we have a rectified feature map coming in. We set the max pooling with a 2x2 filters and a stride of 2. And if you remember correctly, I talked about not going 1 pixel at a time. Well, that's where the stride comes in. We end up with a 2x2 pooled feature map, but instead of moving 1 over each time and looking at every possible combination, we skip a few there. We go by 2. We skip every other pixel. We just do every other one. And this reduces our rectified feature map, which as you can see over here, 16 by 16 to a 4 by 4. So we're continually trying to filter and reduce our data so that we can get to something we can manage. And over here you see that we have the max 3, 4, 1, and 2. And in the max pooling, we're looking for the max value. A little bit different than what we were looking at before. So coming from the rectified feature, we're now finding the max value and then we're pooling those features together. So instead of thinking of this as image of the map, think of this as how valuable is a feature in that area? How much of a feature value do we have? And we just want to find the best or the maximum feature for that area. They might have that one piece of the filter of the beak said, oh, I see a 1 in this beak in this image, and then it skips over and says, I see a 3 in this image, and it says, oh, this one is rated as a 4. We don't want to sum it together because then you might have like 5 1s and it'll say 5, but you might have 4 zeros and 1 10, and that 10 says, well, this is definitely a beak, where the 1s will say probably not a beak. A little strange analogy since we're looking at a bird, but you can see how that pooled feature map comes down, and we're just looking for the max value in each one of those matrices. Pooling layer uses different filters to identify different parts of the image, like edges, corners, body, feathers, eyes, beak, etc. I know I focus mainly on the beak, but obviously each feature could be a different part of the bird coming in. So let's take a look at what that looks like. Structure of a convolution neural network so far. This is where we're at right now. We have our input image coming in, and then we use our filters and there's multiple filters on there that are being developed to kind of twist and change that data. And so we multiply the matrices. We take that little filter, maybe it's a 2 by 2, we multiply it by each piece of the image. And if we step 2, then it's every other piece of the image. That generates multiple convolution layers. So we have a number of convolution layers we have set up in there that is looking at that data. We then take those convolution layers, we run them through the ReLU setup, and then once we've done through the ReLU setup, and we have multiple ReLUs going on, multiple layers that are ReLU, then we're going to take those multiple layers and we're going to be pooling them. So now we have the pooling layers, or multiple poolings going on. Up until this point, we're dealing with, sometimes it's multiple dimensions. You can have 3 dimensions. Some strange data setups that aren't doing images but looking at other things, they can have 4, 5, 6, 7 dimensions. So right now we're looking at 2D image dimensions coming into the pooling layer. So the next step is we want to reduce those dimensions, or flatten them. So flattening. Flattening is a process of converting all of the resultant 2-dimensional arrays from pooled feature map into a single long continuous linear vector. So over here you see where we have a pooled feature map. Maybe that's the bird wing, and it has values 6, 8, 4, 7. And we want to just flatten this out and turn it into 6, 8, 4, 7, or a single linear vector. And we find out that not only do we do each of the pooled feature maps, we do all of them into one long linear vector. So now we've gone through our convolutional neural network part, and we have the input layer into the next setup. All we've done is taken all those different pooling layers and we've flattened them out and combined them into a single linear vector going in. So after we've done the flattening, we have just a quick recap because we've covered so much, so it's important to go back and take a look at each of the steps we've gone through. The structure of the network so far is we have our convolution where we twist it and we filter it and multiply the matrices. We end up with our convolutional layer, which uses the ReLU to figure out the values going out into the pooling. As you have numerous convolution layers that then create numerous pooling layers, pooling that data together, which is the max value. Which one we want to send forward. We want to send the best value. And then we're going to take all of that from each of the pooling layers and we're going to flatten it. And we're going to combine them into a single input going into the final layer. Once you get to that step, you might be looking at that going, boy, that looks like the normal input to most neural network. And you're correct, it is. So once we have the flattened matrix from the pooling layer, that becomes our input. So the pooling layer is fed as an input to the fully connected layer to classify the image. And so you can see as our flattened matrix comes in this case we have the pixels from the flattened matrix fed as an input back to our toucan, or whatever that kind of bird that is. I need one of these to identify what kind of bird that is. It comes into our forward propagation network. And that will then have the different weights coming down across. And then finally it selects that that's a bird and that it's not a dog or a cat in this case. Even though it's not labeled, the final layer there in red is our output layer, our final output layer that says bird, cat, or dog. So, quick recap of everything we've covered so far. We have our input image, which is twisted and multiplied. The filters are multiplied times the two matrices multiplied all the filters to create our convolution layer. Our convolution layers, there's multiple layers in there because it's all building multiple layers off the different filters. Then goes through the ReLU as its activation, and that creates our pooling. And so once we get into the pooling layer, we then on the pooling look for who's the best, what's the max value coming in from our convolution. And then we take that layer and we flatten it. And then it goes into a fully connected layer, our fully connected neural network, and then to the output. And here we can see the entire process, how the CNN recognizes a bird. This is kind of nice because it's showing the little pixels and where they're going. You can see the filter is generating this convolution network, and that filter shows up in the bottom part of the convolution network. And then based on that, it uses the ReLU for the pooling. The pooling then find out which one's the best, and so on, all the way to the fully connected layer at the end, or the classification in the output layer. So that'd be a classification neural network at the end. So we covered a lot of theory up till now, and you can imagine each one of these steps has to be broken down in code. So putting that together can be a little complicated, not that each step of the process is overly complicated, but because we have so many steps. We have 1, 2, 3, 4, 5 different steps going on here with sub-steps in there. We're going to break that down and walk through that in code. So in our use case implementation using the CNN, we'll be using the CFAR10 dataset, from Canadian Institute for Advanced Research for classifying images across 10 categories. Unfortunately, they don't let me know whether it's going to be a toucan or some other kind of bird, but we do get to find out whether it can categorize between a ship, a frog, deer, bird, airplane, automobile, cat, dog, horse, truck. So that's a lot of fun. And if you're looking anything in the news at all of our automated cars and everything else, you can see where this kind of processing is so important in today's world and very cutting edge as far as what's coming out in the commercial deployment. I mean, this is really cool stuff. We're starting to see this just about everywhere in industry. So great time to be playing with this and figuring it all out. Let's go ahead and dive into the code and see what that looks like when we're actually writing our script. Before we go on, let's do one more quick look at what we have here. Let's just take a look at data batch 1 keys. And remember, in Jupyter Notebook, I can get by with not doing the print statement. If I put a variable down there, it'll just display the variable. And you can see under data batch 1 for the keys, since this is a dictionary, we have the batch 1 label, data, and file names. So you can actually see how it's broken up in our data set. So for the next step, or step 4 as we're calling it, we want to display the image using matplotlib. There's many ways to display the images. You could even, well, there's other ways to drill into it, but matplotlib is really good for this. And we'll also look at our first reshape setup, or shaping the data, so you can have a little glimpse into what that means. So we're going to start by importing our matplot, and of course, since I am doing Jupyter Notebook, I need to do the matplot inline command, so it shows up on my page. So here we go. We're going to import matplotlib.pyplot as PLT. And if you remember matplotlib, the pyplot is like a canvas that we paint stuff onto. And there's my %sign matplotlib inline, so it's going to show up in my notebook. And then of course we're going to import numpy as np for our numbers Python array setup. And let's go ahead and set x equals to data batch 1. So this will pull in all the data going into the x value. And then, because this is just a long stream of binary data, we need to go a little bit of reshaping. So in here we have to go ahead and reshape the data. We have 10,000 images. Okay, that looks correct. And this is kind of an interesting thing. It took me a little bit I had to go research this myself to figure out what's going on with this data. And what it is it's a 32 by 32 picture. And let me do this. Let me go ahead and do a drawing pad on here. So we have 32 bits by 32 bits, and it's in color. So there's 3 bits of color. Now, I don't know why the data is particularly like this. It probably has to do with how they originally encoded it. But most pictures put the 3 afterward. So what we're doing here is we're going to take the shape. We're going to take the data, which is just a long stream of information, and we're going to break it up into 10,000 pieces, and those 10,000 pieces then are broken into 3 pieces each, and those 3 pieces then are 32 by 32. You could look at this like an old-fashioned projector where they have the red screen, or the red projector, the blue projector, and the green projector, and they add them all together, and each one of those is a 32 by 32 bit. So that's probably how this was originally formatted, was in that kind of ideal. Things have changed, so we're going to transpose it, and we're going to take the 3, which was here, and we're going to put it at the end. So the first part is reshaping the data from a single line of bit data, or whatever format it is, into 10,000 by 3 by 32 by 32, and then we're going to transpose the color factor to the last place. So it's the image, then the 32 by 32 in the middle, that's this part right here, and then finally we're going to take this, which is 3 bits of data, and put it at the end. So it's more like we process images now. And then as type, this is really important that we're going to use an integer 8. You can come in here and you'll see a lot of these, they'll try to do this with a float or a float 64. What you got to remember though is a float uses a lot of memory. So once you switch this into something that's not integer 8, which goes up to 128, you are just going to, the amount of RAM, let me just put that in here, is going to go way up. The amount of RAM that it loads. So you want to go ahead and use this. You can try the other ones and see what happens if you have a lot of RAM on your computer. But for this exercise, this will work just fine. And let's go ahead and take that and run this. So now our X variable is all loaded and it has all the images in it from the batch 1, data batch 1. And just to show what we were talking about with the as type on there, if we go ahead and take X0 and just look for its max value, let me go ahead and run that. you'll see it doesn't, oops, I said 128, it's 255. You'll see it doesn't go over 255 because it's basically an ASCII character is what we're keeping that down to. We're keeping those values down. So they're only 255, 0 to 255 versus a float value, which would bring this up exponentially in size. And since we're using the matplot library, we can do, oops, that's not what I wanted. Since we're using the matplot library, we can take our canvas and just do a plt.im for image show, and let's just take a look at what x0 looks like. And it comes in, I'm not sure what that is, but you can see it's a very low grade image broken down to the minimal pixels on there. And if we did the same thing, let's see what 1 looks like. Hopefully it's a little easier to see. Run on there, not enter. Let's hit the run on that. And we can see this is probably a semi-truck. That's a good guess on there. And I can just go back up here instead of typing the same line in over and over. And we'll look at 3. That looks like a dump truck unloading, and so on. You can do any of the 10,000 images. We can just jump to 55. Looks like some kind of animal looking at us there, probably a dog. And just for fun, let's do just one more run on there, and we can see a nice car for our image number 4. So you can see we paste through all the different images. It's very easy to look at them, and they've been reshaped to fit our view and what the matplot library uses for its format. So the next step is we're going to start creating some helper functions. We'll start by a one-hot encoder to help us when we're processing the data. Remember that your labels, they can't just be words. They have to switch it, and we use the one-hot encoder to do that. And then we'll also create a class CFAR helper, so it's going to have an init and a setup for the images. And then finally we'll go ahead and run that code so you can see what that looks like. And then we get into the fun part where we're actually going to start creating our model, our actual neural network model. So let's start by creating our one-hot encoder. We're going to create our own here, and it's going to return an out. And we'll have our vector coming in and our values equal 10. What this means is that we have the 10 values, the 10 possible labels. And remember, we don't look at the labels as a number, because a car isn't one more than a horse. That'd be just kind of bizarre to have horse equals 0, car equals 1, plane equals 2, cat equals 3. So a cat plus a car equals what? So instead, we create a numpy array of zeros. And there's going to be 10 values, so we have 10 different values in there. So you have 0 or 1. 1 means it's a cat, 0 means it's not a cat. In the next line it might be that 1 means it's a car, 0 means it's not a car. So instead of having one output with a value of 0 to 10, you have 10 outputs with the values of 0 to 1. That's what the one-hot encoder is doing here. And we're going to utilize this in code in just a minute. So let's go ahead and take a look at the next helpers. We have a few of these helper functions we're going to build. And when you're working with a very complicated Python project, dividing it up into separate definitions and classes is very important. Otherwise, it just becomes really ungainly to work with. So let's go ahead and put in our next helper, which is a class. And there's a lot in this class, so we'll break it down here. And let's just start, oops, we can put a space right in there. There we go. Now this is a little bit more readable. Add a second space. So we're going to create our class, the Cipher Helper. And we'll start by initializing it. Now, there's a lot going on in here. So let's start with the init part. Self.I equals 0. That'll come in a little bit. We'll come back to that in the lower part. We want to initialize our training batches. So when we went through this, there was like a meta batch. We don't need the meta batch, but we do need the data batch 1, 2, 3, 4, 5, and we do not want the testing batch in here. This is just the self-all train batches. So we're going to make an array of all those different images. And then, of course, we left the test batch out, so we have our self.test batch. We're going to initialize the training images and the training labels, and also the test images and the test labels. So this is just to initialize these variables in here. Then we create another definition down here, and this is going to set up the images. And let's just take a look and see what's going on in there. Now we could have all just put this as part of the init part, since this is all just helper stuff, but breaking it up again makes it easier to read. It also makes it easier when we start executing the different pieces to see what's going on. So that way we have a nice print statement to say, hey, we're now running this and this is what's going on in here. We're going to set up the self-training images at this point, and that's going to go to a numpy array vstack. And in there we're going to load up, in this case, the data for D and self all train batches. Again, that points right up to here. So we're going to go through each one of these files, or each one of these data sets, because they're not a file anymore. We've brought them in. Data batch 1 points to the actual data. And so our self-training images is going to stack them all into a NumPy array. And then it's always nice to get the training length, and that's just the total number of self-training images in there. And then we're going to take the self-training images. And let me switch marker colors, because I am getting a little too much on the markers up here. Oops, there we go. Bring down our marker change so we can see it a little better. And at this point, this should look familiar. Where did we see this? Well, when we wanted to look at this above, and we wanted to look at the images in the Matplot library, we had to reshape it. So we're doing the same thing here. We're taking our self-training images, and based on the training length, total number of images, because we stacked them all together, so now it's just one large file of images, we're going to take and look at it as our 3 video cameras that are each displaying 32 by 32, and we're going to switch that around so that now we have each of our images, that stays the same place, and then we have our 32 by 32, and then by our 3. Our 3 different values for the color. And of course we want to go ahead and they run this where you say divide by 255. That was from earlier. It just brings all the data into 0 to 1. That's what this is doing. So we're turning this into a 0 to 1 array, which is all the pictures 32 by 32 by 3. And then we're going to take the self-training labels, and we're going to pump those through our one-hot encoder we just made, and we're going to stack them together. And again, we're converting this into an array that goes from, instead of having horse equals 1, dog equals 2, and then horse plus dog would equal 3, which would be cat. No, it's going to be an array of 10 where each one is 0 to 1. Then we want to go ahead and set up our test images and labels. And when we're doing this, you're going to see it's the same thing we just did with the rest of them. We just changed colors right here. This is no different than what we were doing up here with our training set. We're going to stack the different images. We're going to get the length of them so we know how many images are in there. You certainly could add them by hand, but it's nice to let the computer do it, especially if it ever changes on the other end and you're using other data. And again, we reshape them and transpose them, and we also do the one-hot encoder. Same thing we just did on our training images. So now our test images are in the same format. So now we have a definition which sets up all our images in there. And then the next step is to go ahead and batch them, or next batch. And let's do another breakout here for batches, because this is really important to understand. It tends to throw me for a little loop when I'm working with TensorFlow or Keras or a lot of these. We have our data coming in. If you remember, we had like 10,000 photos. Let me just put 10,000 down here. We don't want to run all 10,000 at once, so we want to break this up into batch sizes. And you also remember that we had the number of photos, in this case length of test or whatever number is in there. We also have 32 by 32 by 3. So when we're looking at the batch size, we want to change this from 10,000 to a batch of, in this case, I think we're going to do batches of 100. So we want to look at just 100, the first 100 of the photos. And if you remember, we set self-I equal to 0. So what we're looking at here is we're going to create X. We're going to get the next batch from the very initialize. We've already initialized it for 0. So we're going to look at X from 0 to batch size, which we set to 100. So just the first 100 images. And then we're going to reshape that into, and this is important to let the data know, that we're looking at 100 by 32 by 32 by 3. Now, we've already formatted it to the 32 by 32 by 3. This just sets everything up correctly so that X has the data in there in the correct order and the correct shape. And then the Y, just like the X, is our labels. So our training labels, again, they go from 0 to batch size. In this case, they do self-I plus batch size because the self-I is going to keep changing. And then finally, we increment the self-I because we have 0. So the next time we call it, we're going to get the next batch size. And so basically, we have X and Y. X being the photograph data coming in, and Y being the label. And that, of course, is labeled through one hot encoder. So if you remember correctly, if it was, say, horse is equal to 0, it would be 1 for the 0 position, since this is the horse, and then everything else would be 0 in here. Let me just put lines through there. There we go. There's our array. Hard to see that array. So let's go ahead and take that, and we're going to finish loading it, since this is our class. And now we're armed with all this, our setup over here. Let's go ahead and load that up. And so we're going to create a variable ch with the cfar helper in it. And then we're going to do ch.setupImages. Now we could have just put all of the setup images under the init, but by breaking this up into two parts, it makes it much more readable. And also, if you're doing other work, there's reasons to do that as far as the setup. Let's go ahead and run that. And you can see where it says setting up training images and labels, setting up test images. And that's one of the reasons we broke it up, is so that if you're testing this out, you can actually have print statements in there telling you what's going on, which is really nice. They did a good job with this setup. I like the way that it was broken up in the back. And then one quick note, you want to remember that batch, to set up the next batch, says we have to run batch equals ch next batch of 100, because we're going to use the 100 size. But we'll come back to that. We're going to use that. Just remember that that's part of our code we're going to be using in a minute from the definition we just made. So now we're ready to create our model. First thing we want to do is we want to import our TensorFlow as TF. I'll just go ahead and run that so it's loaded up. And you can see we got a warning here. That's because they're making some changes. It's always growing, and they're going to be depreciating one of the values from float64 to float type, or is treated as an NP float64. Nothing to really worry about, because this doesn't even affect what we're working on, because we've set all of our stuff to a 255 value, or 0 to 1. And do keep in mind that 0 to 1 value that we converted to 255 is still a float value, but it'll easily work with either the NumPy float64 or the NumPy D-type float. It doesn't matter which one it goes through, so the depreciation would not affect our code as we have it. And in our TensorFlow, we'll go ahead, let me just increase the size in there just a moment so you can get a better view of the what we're typing in. We're going to set a couple placeholders here. And so we're going to set x equals tf placeholder tf float32. We just talked about the float64 versus the NumPy float. We're actually just going to keep this at float32. More than significant number of decimals for what we're working with. And since it's a placeholder, we're going to set the shape equal to, and we've set it equal to none, because at this point we're just holding the place on there. We'll be setting up as we run the batches. That's what that first value is. And then 32 by 32 by 3, that's what we reshaped our data to fit in. And then we have our y true equals placeholder tf float 32, and the shape equals none, comma 10. 10 is the 10 different labels we have, so it's an array of 10. And then let's create one more placeholder. We'll call this hold prob, or hold probability. And we're going to use this. We don't have to have a shape or anything for this. This placeholder is for what we call dropout. If you remember from our theory before, we drop out so many nodes is looking at, or the different values going through, which helps decrease bias. So we need to go ahead and put a placeholder for that also. And we'll run this, so it's all loaded up in there. So we have our 3 different placeholders. And since we're in TensorFlow, when you use Keras, it does some of this automatically, but we're in TensorFlow direct. Keras sits on TensorFlow. We're going to go ahead and create some more helper functions. We're going to create something to help us initialize the weights, initialize our bias. If you remember that each layer has to have a bias going in. We're going to go ahead and work on our conversional 2D, our max pool, so we have our pooling layer, our convolutional layer, and then our normal full layer. So we're going to go ahead and put those all into definitions, and let's see what that looks like in code. And you can also grab some of these helper functions from the MNIST, the NIST setup. Let me just put that in there if you're under the TensorFlow. So a lot of these are already in there, but we're going to go ahead and do our own. And we're going to create our init weights. And one of the reasons we're doing this is so that you can actually start thinking about what's going on in the back end. So even though there's ways to do this with an automation, sometimes these have to be tweaked and you have to put in your own setup in here. Now we're not going to be doing that. We're just going to recreate them for our code. And let's take a look at this. We have our weights, and so what comes in is going to be the shape, and what comes out is going to be random numbers. So we're going to go ahead and just init some random numbers based on the shape with a standard deviation of 0.1. Kind of a fun way to do that. And then the TF variable, init random distribution. So we're just creating a random distribution on there. That's all that is for the weights. Now, you might change that. You might have a higher standard deviation. In some cases, you actually load preset weights. That's pretty rare. usually you're testing that against another model or something like that, and you want to see how those weights configure with each other. Now remember, we have our bias, so we need to go ahead and initialize the bias with a constant. In this case, we're using 0.1. A lot of times the bias is just put in as 1, and then you have your weights to add on to that. But we're going to set this as 0.1. So we want to return a convolutional 2D, in this case a neural network. This is would be a layer on here. What's going on with the conv2D is we're taking our data coming in, we're going to filter it. Strides, if you remember correctly, strides came from, here's our image, and then we only look at this picture here, and then maybe we have a stride of 1, so we look at this picture here, and we continue to look at the different filters going on there. The other thing this does is that we have our data coming in as 32 by 32 by 3. And we want to change this so that it's just, this is 3 dimensions, and it's going to reformat this as just 2 dimensions. So it's going to take this number here and combine it with the 32 by 32. So this is a very important layer here because it's reducing our data down using different means. And it connects down, I'm just going to jump down one here. It goes with the convolutional layer. So you have your kind of your pre-formatting and the setup, and then you have your actual convolution layer that goes through on there. And you can see here we have init weights by the shape, init bias shape of 3, because we have the 3 different, here's our 3 again. And then we return the TFNN ReLU with the convention 2D, so this convolutional has this feeding into it. Right there, it's using that as part of it, and of course the input is the XY plus B, the bias. So that's quite a mouthful, but these two are the keys here to creating the convolutional layers there. The convolutional 2D coming in, and then the convolutional layer, which then steps through and creates all those filters we saw. Then of course we have our pooling. So after each time we run it through the conventional layer, we want to pool the data. If you remember correctly on the pool side, and let me just get rid of all my marks, it's getting a little crazy there. And in fact, let's go ahead and jump back to that slide. Let's just take a look at that slide over here. So we have our image coming in. We create our convolutional layer with all the filters. Remember, the filters go, the filters coming in here, and it looks at these 4 boxes, and then if it's a step, let's say step 2, it then goes to these 4 boxes, and then the next step, and so on. So we have our convolutional layer that we generate, or convolutional layers. They use the ReLU function. There's other functions out there. For this, though, the ReLU is the the one that works the best, at least so far. I'm sure that will change. Then we have our pooling. Now, if you remember correctly, the pooling was max. So if we had the filter coming in, and they did the multiplication on there, and we have a 1, and maybe a 2 here, and another 1 here, and a 3 here, 3 is the max. And so out of all of these, you then create an array that would be 3, and if the max is over here 2 or whatever it is, that's what goes into the pooling of what's going on in our pooling. So again, we're reducing that data down. We're reducing it down as small as we can, and then finally we're going to flatten it out into a single array, and that goes into our fully connected layer. And you can see that here in the code. Right here we're going to create our normal full layer. So at some point we're going to take from our pooling layer, this will go into some kind of flattening process, and then that will be fed into the different layers going in down here. And so we have our input size. You'll see our input layer get shape, which is just going to get the shape for whatever's coming in. And then input size, initial weights is also based on the input layer coming in. And the input size down here is based on the input layer shape. So we're just going to already use the shape and already have our size coming in. And of course, you have to make sure you init the bias. Always put your bias on there. And we'll do that based on the size. So this will return tf.matmul input layer W plus B. This is just a normal full layer. That's what this means right down here. That's what we're going to return. So that was a lot of steps we went through. Let's go ahead and run that. So those are all loaded in there. And let's go ahead and create the layers. Let's see what that looks like. Now that we've done all the heavy lifting and everything, we get to do all the easy part. Let's go ahead and create our layers. We'll create a convolution layer 1 and 2 different convolutional layers, and then we'll take that and we'll flatten that out and create a reshape pooling in there for our reshape, and then we'll have our full layer at the end. So let's start by creating our first convolutional layer. Then we come in here, and let me just run that real quick. And I want you to notice on here the 3 and the 32. This is important because coming into this convolutional layer, we have 3 different channels and 32 pixels each. So that has to be in there. The 4 and 4 you can play with. This is your filter size. So if you remember, you have a filter and you have your image, and the filter slowly steps over and filters out this image depending on what your step is. For this particular setup, 4 is just fine. That should work pretty good for what we're doing and for the size of the image. And then of course at the end, once you have your convolutional layer set up, you also need to pool it, and you'll see that the pooling is automatically set up so that it would see the different shape based on what's coming in. So here we have max 2x2, and we put in the convolutional one that we just created, the convolutional layer we just created goes right back into it. And that right up here, as you can see, is the X. It's coming in from here, so it knows to look at the first model and set the data accordingly, set that up so it matches. And we went ahead and ran this already. I think I ran it. Let me go and run it again. And if we're going to do one layer, let's go ahead and do a second layer down here. And it's we'll call it Convo 2. It's also a convolutional layer on this. And you'll see that we're feeding convolutional 1 in, the pooling. So it goes from convolutional 1 into convolutional 1 pooling, from convolutional 1 pooling into convolutional 2, and then from convolutional 2 into convolutional 2 pooling. And we'll go ahead and take this and run this. So these variables are all loaded into memory. And for our flatten layer, let's go ahead and we'll do, since we have 64 coming out of here and we have 4x4 going in, let's do 8x8x64. So let's do 4096. This is going to be the flat layer. So that's how many bits are coming through on the flat layer. And we'll reshape this. So we'll reshape our Convo 2 pooling, and that will feed into here, the Convo 2 pooling. And then we're going to set it up as a single layer that's 4096 in size. That's what that means there. We'll go ahead and run this. So we've now created this variable, the Convo 2 flat, and then we have our first full layer. This is the final neural network where we have the flat layer going in. And we're going to again use the ReLU for our setup on there on a neural network for evaluation. And you'll notice that we're going to create our first full layer. Our normal full layer, that's our definition. So we created that. That's creating the normal full layer. And our input for the data comes right here from this goes right into it. The Convo 2 flat. So this tells it how big the data is. And we're going to have it come out. It's going to have 1024. That's how big the layer is coming out. We'll go ahead and run this. So now we have our full layer 1. And with the full layer 1, we want to also define the full 1 dropout to go with that. So our full layer 1 comes in, keep probability equals hold probability. Remember we created that earlier. And the full layer 1 is what's coming into it. And this is going backwards and training the data. We're not training every weight. We're only training a percentage of them each time, which helps get rid of the bias. So let me go ahead and run that. And finally, we'll go ahead and create a Y-predict, which is going to equal the normal full 1 dropout and 10, because we have 10 labels in there. Now, in this neural network, we could have added additional layers. That would be another option to play with. You can also play with, instead of 1024, you can use other numbers for the way that sets up on what's coming out and going into the next one. We're only going to do just the 1 layer and the 1 layer dropout. And you can see if we did another layer, it'd be real easy just to feed in the full 1 dropout into full layer 2. And then full layer 2 dropout would have full layer 2 feed into it. And then you'd switch that here for the Y prediction. For right now, this is great. This particular data set is tried and true, and we know that this will work on it. And if we just type in Y predict and we run that, we'll see that this is a tensor object, shape $10, D-type 32. A quick way to double check what we're working on. So now we've got all of our, we've done a setup all the way to the Y predict, which we just did. We want to go ahead and apply the loss function and make sure that's set up in there. Create the optimizer. And then train our optimizer and create a variable to initialize all the global TF variables. So before we dive into the loss function, let me point out one quick thing, or just kind of a rehab over a couple things. And that is, when we're playing with these setups, we pointed out up here we can change the 4-4 and use different numbers there, they change your outcome. So depending on what numbers you use here will have a huge impact on how well your model fits. And that's the same here with the 1024 also. This is also another number that if you continue to raise that number, you'll get possibly a better fit. You might overfit. And if you lower that number, you'll use less resources. And generally, you want to use this in the exponential growth. An exponential being 2, 4, 8, 16. And in this case, the next one down would be 5, 12. You can use any number there, but those would be the ideal numbers when you look at this data. So the next step in all this is we need to also create a way of tracking how good our model is. And we're going to call this a loss function. And so we're going to create a cross-entropy loss function. And so before we discuss exactly what that is, let's take a look and see what we're feeding it. We're going to feed it our labels, and we have our true labels and our prediction labels. So coming in here is where the two different variables we're sending in, or the two different probability distributions, is one that we know is true and what we think it's going to be. Now this function right here, when they talk about cross-entropy, in information theory, the cross-entropy between two probability distributions over the same underlying set of events measures the average number of bits needed to identify an event drawn from the set. That's a mouthful. Really, we're just looking at the amount of error in here. How many of these are correct and how many of these are incorrect? So how much of it matches? And we're going to look at that. We're just going to look at the average. That's what the mean, the reduced to the mean means here. So we're looking at the average error on this. And so the next step is we're going to take the error. We want to know our cross entropy or our loss function, how much loss we have. That's going to be part of how we train the model. So when you know what the loss is and we're training it, you feed that back into the backpropagation setup. And so we want to go ahead and optimize that. Here's our optimizer. We're going to create the optimizer using an atom optimizer. Remember, there's a lot of different ways of optimizing the data. Atom's the most popular used. So our optimizer is going to equal the TF train atom optimizer. If you don't remember what the learning rate is, let me just pop this back into here. Here's our learning rate. When you have your weights, you have all your weights in your different nodes that are coming out. Here's our node coming out, and it has all its weights. And then the error is being sent back through in reverse on our neural network. So we take this error and we adjust these weights based on the different formulas. In this case, the atom formula is what we're using. We don't want to just adjust them completely. We don't want to change this weight so it exactly fits the data coming through. Because if we made that kind of adjustment, it's going to be biased to whatever the last data we sent through is. Instead, we're going to multiply that by 0.001 and make a very small shift in this weight. So our delta W is only 0.001 of the actual delta W of the full change we're going to compute from the atom. And then we want to go ahead and train it. So our training, or set up a training variable or function. And this is going to equal our optimizer minimize cross entropy. And we make sure we go ahead and run this. So it's loaded in there. And then we're almost ready to train our model. But before we do that, we need to create one. And when we look at this, the TF global variable initializer, this is a TensorFlow object. It goes through there and it looks at all our different setup that we have going under our TensorFlow and then initializes those variables. So it's kind of like a magic wand because it's all hidden in the back end of TensorFlow. All you need to know about this is that you have to have the initialization on there, which is an operation, and you have to run that once you have your setup going. So we'll go ahead and run this piece of code, and then we're going to go ahead and train our data. So let me run this so it's loaded up there. And so now we're going to go ahead and run the model by creating a graph session. Graph session is a TensorFlow term. So you'll see that coming up. It's one of the things that throws me because I always think of GraphX and Spark and graph as just general graphing. But they talk about a graph session. So we're going to go ahead and run the model. And let's go ahead and walk through this, what's going on here. And let's paste this data in here. And here we go. So we're going to start off with a TF session as ses. So that's our actual TF session that we've created. So we're right here with the TF session. Our session we're creating, we're going to run TF global variable initializer. So right off the bat, we're initializing our variables here. And then we have for I in range 500. So what's going on here, remember 500, we're going to break the data up and we're going to batch it in at 500 points each. We've created our session run. So we're going to do with TF session as session right here. We've created our variable session. and then we're going to run and we're going to go ahead and initialize it. So we have our TF global variables initializer that we created. That initializes our session in here. The next thing we're going to do is we're going to go for I in range of 500, batch equals ch.next batch. So if you remember correctly, this is loading up 100 pictures at a time. And this is going to loop through that 500 times. So we are literally doing, 500 times 100 is 50,000. So that's 50,000 pictures we're going to process right there. And the first process is we're going to do a session run. We're going to take our train. We created our train variable or our optimizer in there. We're going to feed it the dictionary. We had our feed dictionary that we created, and we have x equals batch 0 coming in, y true, batch 1, hold the probability, 0.5. And then just so that we can keep track of what's going on, we're going to, every 100 steps, we're going to run a print. So currently on step, format, accuracy is, and we're going to look at matches equals tf argument y prediction 1, tf.arg max y true, comma 1. So we're going to look at this as how many matches it has. And here our ACC, all we're doing here is we're going to take the matches, how many matches they have, it generates a chart. We're going to convert that to float. That's what the TF cast does. And then we just want to know the average. We just want to know the average of the accuracy. And then we'll go ahead and print that out, print session run accuracy feed dictionary. So it takes all this and it prints out our accuracy on there. So let's go ahead and take this. Oops, flip screens there. Let's go ahead and take this and let's run it. And this is going to take a little bit to run. So let's see what happens on my old laptop. And we'll see here that we have our current, we're currently on step 0. It takes a little bit to get through the accuracy. And this will take just a moment to run. We can see that on our step 0 it has an accuracy of 0.1 or 0.1028. And as it's running, we'll go ahead, you don't need to watch it run all the way, but this accuracy is going to change a little bit up and down. So we've actually lost some accuracy during our step 2. But we'll see how that comes out. Let's come back after we run it all the way through and see how the different steps come out. I was actually reading that backwards. The way this works is the closer we get to 1, the more accuracy we have. So you can see here we've gone from a 0.1 to a 0.39, and we'll go ahead and pause this and come back and see what happens when we're done with the full run. Alright, now that we've prepared the meal, got it in the oven, and pulled out my finished dish here, if you've ever watched any of the old cooking shows, let's discuss a little bit about this accuracy going on here, and how do you interpret that? We've done a couple things. First, we've defined accuracy. The reason I got it backwards before is you have loss or accuracy. And with loss, you'll get a graph that looks like this. It goes, oops, that's an S, by the way. There we go. You get a graph that curves down like this. And with accuracy, you get a graph that curves up. This is how good it's doing. Now, in this case, 1 is supposed to be really good accuracy. That means it gets close to 1, but it never crosses 1. So if you have an accuracy of 1, that is phenomenal. In fact, that's pretty much unheard of. And the same thing with loss. If you have a loss of 0, that's also unheard of. And the 0 is actually on this axis right here as we go in there. So how do we interpret that? Because, if I was looking at this and I go, oh, 0.51, that's 51%. You're doing 50-50. No, this is not percentage. Let me just put that in there. It is not percentage. This is logarithmic. What that means is that 0.2 is twice as good as 0.1. And when we see 0.4, that's twice as good as 0.2. Real way to convert this into a percentage. You really can't say this is a direct percentage conversion. What you can do, though, is in your head, if we were to give this a percentage, we might look at this as 50%, we're just guessing, equals 0.1. And if 50% roughly equals 0.1, that's where we started up here at the top. Remember at the top here, here's our 0.1028. The accuracy of 50%, then 75% is about 0.2, and so on and so on. Don't quote those numbers because that doesn't work that way. They say that if you have 0.95, that's pretty much saying 100%. And if you have anywhere between, you'd have to go look this up. Let me go ahead and remove all my drawings there. So the magic number is 0.5. We really want to be over a 0.5 in this whole thing. And we have both 0.5004. Remember, this is accuracy. If we were looking at loss, then we'd be looking the other way. But 0.05, instead of how high it is, we want how low it is. But with accuracy, being over a 0.5 is pretty valid. That means this is pretty solid. And if you get to a 0.95, then it's a direct correlation. That's what we're looking for here in these numbers. You can see we finished with this model at 0.5135, so still good. And if we look at when they ran this in the other end, remember there's a lot of randomness that goes into it when we seed the weights. They got 0.5251, so a little better than ours. But that's fine. You'll find your own comes up a little bit better or worse depending on just that randomness. And so we've gone through the whole model. We've trained the model, and we've also gone through on every 100th run to test the model to see how accurate it is. We will start with, of course, the fundamentals. What is a neural network and popular neural networks? It's important to know the framework we're in and what we're going to be looking at specifically. Then we'll touch on why a recurrent neural network, what is a recurrent neural network, and how does an RNN work. One of the big things about RNNs is what they call the vanishing and exploding gradient problem. So we'll look at that. And then we're going to be using a use case study. It's going to be in Keras on TensorFlow. Keras is a Python module for doing neural networks in deep learning. And in there, there's what they call long short-term memory, lSTM. And then we'll use the use case to implement our lSTM on the Keras. So when you see that lSTM, that is basically the RNN network. And we'll get into that. The use case is always my favorite part. Before we dive into any of this, we're going to take a look at what is an RNN, or an introduction to the RNN. Do you know how Google's autocomplete feature predicts the rest of the words a user is typing? I love that autocomplete feature. As I'm typing away, it saves me a lot of time. I can just kind of hit the enter key and it autofills everything and I don't have to type as much. Well, first there's a collection of large volumes of most frequently occurring consecutive words. This is fed into a recurrent neural network. Analyzes the data by finding the sequence of words occurring frequently and builds a model to predict the next word in the sentence. And then Google, what is the best food to eat in Los, I'm guessing you're going to say Los, Mexico. No, it's going to be Las Vegas. So the Google search will take a look at that and say, hey, the most common autocomplete is going to be Vegas in there. And usually it gives you 3 or 4 different choices. So it's a very powerful tool. It saves us a lot of time, especially when we're doing a Google search or even in Microsoft Words has some people get very mad at it because it autofills with the wrong stuff. But you're typing away and it helps you autofill. I have that in a lot of my different packages. It's just a standard feature that we're all used to now. So before we dive into the RNN and getting into the depths, let's go ahead and talk about what is a neural network. Neural networks used in deep learning consist of different layers connected to each other and work on the structure and functions of a human brain. You're going to see that thread, human brain and human thinking throughout deep learning. The only way we can evaluate an artificial intelligence or anything like that is to compare it to human function. Very important note on there. And it learns from a huge volumes of data, and it uses complex algorithms to train a neural net. So in here we have image pixels of 2 different breeds of dog. One looks like a nice floppy-eared lab and one a German Shepherd. Both wonderful breeds of animals. That image then goes into an input layer. That input layer might be formatted at some point because you have to let it know, different pictures are going to be different sizes and different color content. Then it'll feed into hidden layers. So each of those pixels or each point of data goes in and then splits into the hidden layer, which then goes into another hidden layer, which then goes to an output layer. RNN, there's some changes in there which we're going to get into. So it's not just a straightforward propagation of data like we've covered in many other tutorials. And finally you have an output layer, and the output layer has 2 outputs. It has one that lights up if it's a German Shepherd and another that lights up if it's a Labrador. So it identifies the dog's breed. Such networks do not require memorizing the past output. So our forward propagation is just that. It goes forward and doesn't have to rememorize stuff. And you can see there, that's not actually me in the picture. Dressed up in my suit. I haven't worn a suit in years. So as we're looking at this, we're going to change it up a little bit. Before we cover that, let's talk about popular neural networks. First, there's the feed-forward neural network, used in general regression and classification problems. And we have the convolution neural network, used for image recognition. Deep neural network, used for acoustic modeling. Deep belief network, used for cancer detection. and recurrent neural network used for speech recognition. Now, taken a lot of these and mixed them around a little bit, so just because it's used for one thing doesn't mean it can't be used for other modeling. But generally this is where the field is, and this is how those models are generally being used right now. So we talk about a feed-forward neural network. In a feed-forward neural network, information flows only in the forward direction, from the input nodes through the hidden layers, if any, and to the output nodes. There are no cycles or loops in the network. And so you can see here we have our input layer. I was talking about how it just goes straight forward into the hidden layers, so each one of those connects and then connects to the next hidden layer, it connects to the output layer. And of course we have a nice simplified version where it has a predicted output, and they refer to the input as X a lot of times and the output as Y. Decisions are based on current input, no memory about the past, no future scope. Why recurrent neural network? Issues in feed-forward neural network. So one of the biggest issues is because it doesn't have a scope of memory or time, a feed-forward neural network doesn't know how to handle sequential data. It only considers only the current input. So if you have a series of things, and because 3 points back affects what's happening now, and what your output affects what's happening, that's very important. So whatever I put as an output is going to affect the next one. A feed-forward doesn't look at any of that. It just looks at this is what's coming in. And it cannot memorize previous inputs. So it doesn't have that list of inputs coming in. Solution to feed-forward neural network. You'll see here where it says recurrent neural network, and we have our X on the bottom going to H, going to Y. That's your feed forward. But right in the middle it has a value C, so there's a whole other process. So it's memorizing what's going on in the hidden layers, and the hidden layers, as they produce data, feed into the next one. So your hidden layer might have an output that goes off to Y, but that output goes back into the next prediction coming in. What this does is this allows it to handle sequential data. It considers the current input and also the previously received inputs. And if we're going to look at general drawings and solutions, we should also look at applications of the RNN. Image captioning. RNN is used to caption an image by analyzing the activities present in it. A dog catching a ball in midair. That's very tough. I mean, we have a lot of stuff that analyzes images of a dog and the image of a ball, but it's able to add one more feature in there that's actually catching the ball in midair. Time series prediction. Any time series problem like predicting the prices of stocks in a particular month can be solved using RNN. And we'll dive into that in our use case and actually take a look at some stock. One of the things you should know about analyzing stock today is that it is very difficult. And if you're analyzing the whole stock, the stock market at the New York Stock Exchange in the U.S. produces somewhere in the neighborhood, if you count all the individual trades and fluctuations by the second, it's like 3 terabytes a day of data. So we're only going to look at one stock. Just analyzing one stock is really tricky. In here, we'll give you a little jump on that, so that's exciting, but don't expect to get rich off of it immediately. Another application of the RNN is natural language processing. Text mining and sentiment analysis can be carried out using RNN for natural language processing. And you can see right here the term natural language processing, when you stream those 3 words together, is very different than if I said processing language naturally. So the time series is very important when we're analyzing sentiments. It can change the whole value of a sentence just by switching the words around. Or if you're just counting the words, you might get one sentiment where if you actually look at the order they're in, you get a completely different sentiment. When it rains, look for rainbows. When it's dark, look for stars. Both of these are positive sentiments, and they're based upon the order of which the sentence is going in. Machine translation. Given an input in one language, RNN can be used to translate the input into a different languages as output. I myself am very linguistically challenged. But if you study languages and you're good with languages, you know right away that if you're speaking English, you would say big cat. And if you're speaking Spanish, you would say cat big. So that translation is really important to get the right order, to get, there's all kinds of parts of speech that are important to know by the order of the words. Here this person is speaking in English and getting translated. And you can see here a person is speaking in English in this little diagram. I guess that's denoted by the flags. I have a flag. I own it. No. But they're speaking in English and it's getting translated into Chinese, Italian, French, German, and Spanish languages. Some of the tools coming out are just so cool. So somebody like myself who's very linguistically challenged, I can now travel into worlds I would never think of because I can have something translate my English back and forth readily, and I'm not stuck with a communication gap. So let's dive into what is a recurrent neural network. Recurrent neural network works on the principle of saving the output of a layer and feeding this back to the input in order to predict the output of the layer. Sounds a little confusing. When we start breaking it down, it'll make more sense. And usually we have a propagation forward neural network with the input layers, the hidden layers, the output layer. With the recurrent neural network, we turn that on its side. So here it is, and now our X comes up from the bottom into the hidden layers into Y, and they usually draw it very simplified, X to H with C as a loop, A to Y, where A, B, and C are the perimeters. A lot of times you'll see this kind of drawing in here, digging closer and closer into the H and how it works. Going from left to right, you'll see that the C goes in, and then the X goes in. So the X is going upward bound, and C is going to the right. A is going out. And C is also going out. That's where it gets a little confusing. So here we have X in, C in, and then we have Y out and C out. And C is based on HT minus 1. So our value is based on the Y and the H value are connected to each other. They're not necessarily the same value because H can be its own thing. And usually we draw this, or we represent it as a function. H of T equals a function of C, where H of T minus 1, that's the last H output, and X of T going in. So it's the last output of H combined with the new input of X, where HT is the new state, FC is a function with the parameters C, that's a common way of denoting it, HT minus 1 is the old state coming out, and then X of T is an input vector at time of step T. Well, we need to cover types of recurrent neural networks. And so the first one is the most common one, which is a one-to-one single output. One-to-one neural network is usually known as a vanilla neural network, used for regular machine learning problems. Why? Because vanilla is usually considered kind of just a real basic flavor. But because it's very basic, a lot of times they'll call it the vanilla neural network, which is not the common term, but it is, like kind of a slang term. People will know what you're talking about usually if you say that. Then we run one-to-many, so you have a single input, and you might have multiple outputs. In this case, image captioning, as we looked at earlier, where we have not just looking at it as a dog, but a dog catching a ball in the air. And then you have many-to-one network, takes in a sequence of inputs. Examples, sentiment analysis, where a given sentence can be classified as expressing positive or negative sentiments. And we looked at that as we were discussing, if it rains, look for a rainbow. So positive sentiment, where rain might be a negative sentiment if you were just adding up the words in there. And then, of course, if you're going to do a one-to-one, many-to-one, one-to-many, there's many-to-many networks, takes in a sequence of inputs and generates a sequence of outputs. Example, machine translation. So we have a lengthy sentence coming in English and then going out in all the different languages. Just a wonderful tool. Very complicated set of computations. If you're a translator, you realize just how difficult it is to translate into different languages. One of the biggest things you need to understand when we're working with this neural network is what's called the vanishing gradient problem. While training an RNN, your slope can be either too small or very large, and this makes training difficult. When the slope is too small, the problem is known as vanishing gradient. And you'll see here they have a nice image, loss of information through time. So if you're pushing not enough information forward, that information is lost, and then when you go to train it, you start losing the third word in the sentence or something like that, or it doesn't quite follow the full logic of what you're working on. Exploding gradient problem. Oh, this is one that runs into everybody. When you're working with this particular neural network, when the slope tends to grow exponentially instead of decaying, this problem is called exploding gradient. Issues in gradient problem: long training time, poor performance, bad accuracy. And I'll add one more in there. Your computer, if you're on a lower end computer testing out a model, will lock up and give you the memory error. Explaining gradient problem. Consider the following two examples to understand what should be the next word in the sequence. The person who took my bike and blank, a thief. The students who got into engineering with blank from Asia. And you can see in here we have our X value going in, we have the previous value going forward, and then you backpropagate the error like you do with any neural network. And as we're looking for that missing word, maybe we'll have the person took my bike and blank was a thief. And the student who got into engineering with a blank were from Asia. Consider the following example, the person who took the bike. So we'll go back to the person who took the bike was blank a thief. In order to understand what would be the next word in the sequence, the RNN must memorize the previous context, whether the subject was singular noun or a plural noun. So, was a thief is singular. The student who got into engineering, well, in order to understand what would be the next word in the sequence, the RNN must memorize the previous context, whether the subject was singular noun or a plural noun. And so you can see here the students who got into engineering with blank were from Asia. It might be sometimes difficult for the error to backpropagate to the beginning of the sequence to predict what should be the output. So when you run into the gradient problem, we need a solution, the solution to the gradient problem. First, we're going to look at exploding gradient, where we have three different solutions depending on what's going on. One is identity initialization. So the first thing we want to do is see if we can find a way to minimize the identities coming in instead of having it identify everything, just the important information we're looking at. Next is to truncate the backpropagation. So instead of having whatever information it's sending to the next series, we can truncate what it's sending. We can lower that particular set of layers, make those smaller. And finally is a gradient clipping. So when we're training it, we can clip what that gradient looks like and narrow the training model that we're using. When you have a vanishing gradient, the opposite problem, we can take a look at weight initialization, very similar to the identity, but we're going to add more weights in there so it can identify different aspects of what's coming in better. Choosing the right activation function. That's huge. So we might be activating based on one thing and we need to limit that. We haven't talked too much about activation functions, so we'll look at that just minimally. There's a lot of choices out there. And then finally there's long short-term memory networks, the lSTMs. And we can make adjustments to that. So just like we can clip the gradient as it comes out, we can also expand on that. We can increase the memory network, the size of it, so it handles more information. And one of the most common problems in today's setup is what they call long-term dependencies. Suppose we try to predict the last word in the text. The clouds are in the, and you probably said sky. Here we do not need any further context. It's pretty clear that the last word is going to be sky. Suppose we try to predict the last word in the text. I have been staying in Spain for the last 10 years. I can speak fluent. Maybe you said Portuguese or French. No, you probably said Spanish. The word we predict will depend on the previous few words in context. Here we need the context of Spain to predict the last word in the text. It's possible that the gap between the relevant information and the point where it is needed to become very large. lSTMs help us solve this problem. So the lSTMs are a special kind of recurrent neural network capable of learning long-term dependencies. Remembering information for long periods of time is their default behavior. All recurrent neural networks have the form of a chain of repeating modules, of neural network connections. In standard RNNs, this repeating module will have a very simple structure such as a single tangent H layer. lSTMs also have a chain-like structure, but the repeating module has a different structure. Instead of having a single neural network layer, there are 4 interacting layers communicating in a very special way. lSTMs are a special kind of recurrent neural network, capable of learning long-term dependencies. Remembering information for long periods of time is their default behavior. lSTMs also have a chain-like structure, but the repeating module has a different structure. Instead of having a single neural network layer, there are 4 interacting layers communicating in a very special way. As you can see, the deeper we dig into this, the more complicated the graphs get. In here, I want you to note that you have x at t minus 1 coming in, you have x at t coming in, and you have x at t plus 1. And you have h at t minus 1, and h at t coming in, and h at t plus 1 going out. And of course, on the other side is the output A. In the middle, we have our tangent H, but it occurs in 2 different places. So not only when we're computing the x at t plus 1 are we getting the tangent H from x at t, but we're also getting that value coming in from the x at t minus 1. So the short of it is that as you look at these layers, not only does the propagate through the first layer goes into the second layer back into itself, but it's also going into the third layer. So now we're kind of stacking those up. And this can get very complicated as you grow that in size. It also grows in memory too, and in the amount of resources it takes. But it's a very powerful tool to help us address the problem of complicated, long sequential information coming in, like we were just looking at in the sentence. And when we're looking at our long short-term memory network, there's 3 steps of processing in the lSTMs that we look at. The first one is we want to forget irrelevant parts of the previous state. a lot of times, like, is, as, in, a, unless we're trying to look at whether it's a plural noun or not, they don't really play a huge part in the language, so we want to get rid of them. Then selectively update cell state values. So we only want to update the cell state values that reflect what we're working on. And finally, we want to only output certain parts of the cell state. So whatever's coming out, we want to limit what's going out too. And let's dig a little deeper into this. Let's just see what this really looks like. So step 1 decides how much of the past it should remember. First step in the lSTM is to decide which information to be omitted from the cell in that particular time step. It is decided by the sigmoid function. It looks at the previous state, h at t minus 1, and the current input, x at t, and computes the function. So you can see over here we have a function of t equals the sigmoid function of the weight of f, the h at t minus 1, and then x at t, plus, of course you have a bias in there with any of our neural networks, so we have a bias function. So f at t equals forget gate, decides which information to delete that is not important from the previous time step. Considering an lSTM is fed with the following inputs from the previous and present time step. Alice is good in physics. John, on the other hand, is good in chemistry. So, previous output. John plays football well. He told me yesterday over the phone that he had served as a captain of his college football team. That's our current input. So as we look at this, the first step is the forget gate realizes there might be a change in context after encountering the first full stop. Compares with the current input sentence of x at t. So we're looking at that full stop and then compares it with the input of the new sentence. The next sentence talks about John, so the information on Alice is deleted. Okay, that's important to know. So we have this input coming in, and if we're going to continue on with John, then that's going to be the primary information we're looking at. The position of the subject is vacated and is assigned to John. And so in this one, we've seen that we've weeded out a whole bunch of information, and we're only passing information on John, since that's now the new topic. So step 2 is then to decide how much should this unit add to the current state. In the second layer, there are two parts. One is the sigmoid function, and the other is the tangent h. In the sigmoid function, it decides which values to let through, 0 or 1. Tangent h function gives the weightage to the values which are passed, deciding their level of importance, -1 to 1. And you can see the two formulas that come up. The I of t equals the sigmoid of the weight of I, h at t minus 1, x at t plus the bias of I. And the c of t equals the tangent of h of the weight of c of h at t minus 1, x at t plus the bias of c. So our I of t equals the input gate, determines which information to let through based on its significance in the current time step. If this seems a little complicated, don't worry, because a lot of the programming is already done when we get to the case study. Understanding, though, that this is part of the program is important when you're trying to figure out what to set your settings at. You should also note when you're looking at this, it should have some semblance to your forward propagation neural networks, where we have a value assigned to a weight plus a bias. Very important steps in any of the neural network layers, whether we're propagating into the information from one to the next, or we're just doing a straightforward neural network propagation. Let's take a quick look at this, what it looks like from the human standpoint, as I step out of my suit again. Consider the current input at x of t. John plays football well. He told me yesterday over the phone that he had served as a captain of his college football team. That's our input. Input gate analyzes the important information. John plays football and he was a captain of his college team is important. He told me over the phone yesterday is less important, hence it is forgotten. This process of adding some new information can be done via the input gate. Now this example is as a human form, and we'll look at training this stuff in just a minute. But as a human being, if I wanted to get this information from a conversation, maybe it's a Google Voice listening in on you or something like that, how do we weed out the information that he was talking to me on the phone yesterday? Well, I don't want to memorize that he talked to me on the phone yesterday, or maybe that is important. But in this case, it's not. I want to know that he was the captain of the football team. I want to know that he served. I want to know that John plays football and he was the captain of the college football team. Those are the two things that I want to take away as a human being. Again, we measure a lot of this from the human viewpoint, and that's also how we try to train them so we can understand these neural networks. Finally, we get to step 3, decides what part of the current cell state makes it to the output. The third step is to decide what will be our output. First, we run a sigmoid layer, which decides what parts of the cell state make it to the output. Then we put the cell state through the tangent h, to push the values to be between -1 and 1 and multiply it by the output of the sigmoid gate. So when we talk about the output of t, we set that equal to the sigmoid of the weight of 0 of the h of t minus 1, back one step in time, by the x of t, plus of course the bias. The h of t equals the out of t times the tangent h of c of t. So our O of t equals the output gate, allows the passed in information to impact the output in the current time step. Let's consider the example to predicting the next word in the sentence. John played tremendously well against the opponent and won for his team. For his contributions, Brave blank was awarded player of the match. There could be a lot of choices for the empty space. Current input, Brave, is an adjective. Adjectives describe a noun. John could be the best output after Brave. Thumbs up for John, awarded player of the match. And if you were to pull just the nouns out of the sentence, team doesn't look right because that's not really the subject we're talking about. Contributions, brave contributions, or brave team, brave player, brave match. So you look at this and you can start to train this neural network. So it starts looking at it and goes, oh no, John is what we're talking about. So brave is an adjective. John's going to be the best output. And we give John a big thumbs up. And then of course we jump into my favorite part, the case study. Use case implementation of lSTM. Let's predict the prices of stocks using the lSTM network based on the stock price data between 2012 and 2016. We're going to try to predict the stock prices of 2017. And this will be a narrow set of data. We're not going to do the whole stock market. It turns out that the New York Stock Exchange generates roughly 3 terabytes of data per day. That's all the different trades up and down of all the different stocks going on. And each individual one second to second or nanosecond to nanosecond. But we're going to limit that to just some very basic fundamental information. So don't think you're going to get rich off this today. But at least you can give a step forward in how to start processing something like stock prices, a very valid use for machine learning in today's markets. Use case implementation of lSTM. Let's dive in. We're going to import our libraries. We're going to import the training set and get the scaling going. Now, if you watch any of our other tutorials, a lot of these pieces just start to look very familiar because it's a very similar setup. But let's take a look at that. And just a reminder, we're going to be using Anaconda, the Jupyter Notebook. So here I have my Anaconda navigator. When we go under environments, I've actually set up a Keras Python 3.6. I'm in Python 3.6. And nice thing about Anaconda, especially the newer version, I remember a year ago messing with Anaconda in different versions of Python in different environments. Anaconda now has a nice interface. And I have this installed both on a Ubuntu Linux machine and on Windows, so it works fine on there. You can go in here and open a terminal window, and then in here, once you're in the terminal window, this is where you're going to start installing using pip to install your different modules and everything. Now we've already pre-installed them, so we don't need to do that in here. But if you don't have them installed in your particular environment, you'll need to do that. And of course you don't need to use the Anaconda or the Jupyter. You can use whatever favorite Python IDE you like. I'm just a big fan of this because it keeps all my stuff separate. You can see on this machine I have specifically installed one for Keras, since we're going to be working with Keras under TensorFlow. When we go back to home, I've gone up here to application, and that's the environment I've loaded on here, and then we'll click on the Launch Jupyter Notebook. Now I've already, in my Jupyter Notebook, have set up a lot of stuff so that we're ready to go. Kind of like Martha Stewart's in the old cooking shows. We want to make sure we have all our tools for you so you're not waiting for them to load. And if we go up here to where it says New, you can see where you can create a new Python 3. That's what we did here underneath the setup, so it already has all the modules installed on it. And I'm actually renamed this. If you go under File, you can rename it. I'm calling it RNN Stock. And let's just take a look and start diving into the code. Let's get into the exciting part. Now we've looked at the tool, and of course you might be using a different tool, which is fine. Let's start putting that code in there and seeing what those imports and uploading everything looks like. Now, the first half is kind of boring when we hit the Run button, because we're going to be importing NumPy as NP. That's the number Python, which is your NumPy array, and the matplot library, because we're going to do some plotting at the end, and our pandas for our data set. Our pandas as PD. And when I hit Run, it really doesn't do anything except for load those modules. Just a quick note, let me just do a quick draw here. Oops, Shift-Alt, there we go. You'll notice when we're doing this setup, if if I was to divide this up, oops, I'm going to actually, let's overlap these. Here we go. This first part that we're going to do is our data prep. A lot of prepping involved. In fact, depending on what your system is, since we're using Keras, I put an overlap here, but you'll find that almost maybe even half of the code we do is all about the data prep. And the reason I overlap this with Keras, let me just put that down because that's what we're working in, is because Keras has like their own preset stuff, so it's already pre-built in, which is really nice. So there's a couple steps a lot of times that are in the Keras setup. We'll take a look at that to see what comes up in our code as we go through and look at stock. And then the last part is to evaluate. And if you're working with shareholders or classroom, whatever it is you're working with, the evaluate is the next biggest piece. So the actual code here, Keras is a little bit more, but when you're working with some of the other packages, you might have like 3 lines. That might be it. All your stuff is in your pre-processing and your data. Since Keras is cutting edge and you load the individual layers, you'll see that there's a few more lines here and Keras is a little bit more robust. And then you spend a lot of times, like I said, with the evaluate, you want to have something you present to everybody else and say, hey, this is what I did, this is what it looks like. So let's go through those steps. This is like a kind of just general overview. And let's just take a look and see what the next set of code looks like. And in here we have a dataset train, and it's going to be read using the PD, or pandas.readCSV, and it's the Google stock price train.csv. And so under this we have training set equals dataset train.iLocation, and we've kind of sorted out part of that. So what's going on here? Let's just take a look at it. Let's look at the actual file and see what's going on there. Now if we look at this, ignore all the extra files on this, I already have a train and a test set where it's sorted out. This is important to notice because a lot of times we do that as part of the pre-processing of the data. We take 20% of the data out so we can test it, and then we train the rest of it. That's what we use to create our neural network. That way we can find out how good it is. But let's go ahead and just take a look and see what that looks like as far as the file itself. And I went ahead and just opened this up in a basic WordPad and text editor just so we can take a look at it. Certainly you can open up in Excel or any other kind of spreadsheet. And we note that this is a comma-separated variables. We have a date, open, high, low, close, volume. This is the standard stuff that we import into our stock, or the most basic set of information you can look at in stock. It's all free to download. In this case we downloaded it from Google. That's why we call it the Google stock price. And it specifically is Google. This is the Google stock values from, as you can see here, we started off at 1/3/2012. So when we look at this first setup up here, we have a dataset train equals PD_CSV. And if you noticed on the original frame, let me just go back there, they had it set to home Ubuntu downloads Google stock price train. I went ahead and changed that because we're in the same file where I'm running the code. So I've saved this particular Python code and I don't need to go through any special paths or have the full path on there. And then of course we want to take out certain values in here. And you're going to notice that we're using our data set, and we're now in pandas. So pandas, basically it looks like a spreadsheet. And in this case we're going to do iLocation, which is going to get specific locations. The first value is going to show us that we're pulling all the rows in the data. And the second one is we're only going to look at columns 1 and 2. And if you remember here from our data, as we switch back on over, columns, we always start with 0, which is the date. And we're going to be looking at open and high, which would be 1 and 2. We'll just label that right there so you can see. Now, when you go back and do this, you certainly can extrapolate and do this on all the columns. But for the example, let's just limit a little bit here so that we can focus on just some key aspects of stock. And then we'll go up here and run the code. And again, I said the first half is very boring. Whenever you hit the run button, it doesn't do anything because we're still just loading the data and setting it up. Now that we've loaded our data, we want to go ahead and scale it. We want to do what they call feature scaling. And in here we're going to pull it up from the sklearn or the skKit pre-processing import min max scaler. And when you look at this, you got to remember that biases in our data, we want to get rid of that. So if you have something that's like a really high value, let's just draw a quick graph. And I have something here like maybe the stock has a value, one stock has a value of 100, and another stock has a value of 5. You start to get a bias between different stocks. And so when we do this, we go ahead and say, okay, 100 is going to be the max, and 5 is going to be the min, and then everything else goes, and then we change this, so we just squish it down. I like the word squish. So it's between 1 and 0. So 100 equals 1, or 1 equals 100, and 0 equals 5. And you can just multiply. It's usually just a simple multiplication we're using. Multiplication. So it's going to be minus 5 and then 100 divided, or 95 divided by 1. So, or whatever value is divided by 95. And once we've actually created our scale, we've telling it's going to be from 0 to 1. We want to take our training set, and we're going to create a training set scaled, and we're going to use our scalar, SC, and we're going to fit. We're going to fit and transform the training set. So we can now use the SC, this particular object, we'll use it later on our testing set. Because remember, we have to also scale that when we go to test our model and see how it works. And we'll go ahead and click on the run. Again, it's not going to have any output yet because we're just setting up all the variables. Okay, so we paste the data in here, and we're going to create the data structure with the 60 time steps and output. First note, we're running 60 time steps, and that is where this value here also comes in. So the first thing we do is we create our xtrain and ytrain variables, and we set them to an empty Python array. Very important to remember what kind of array we're in and what we're working with. And then we're going to come in here, we're going to go for I in range 60 to 1258. There's our 60 time steps. And the reason we want to do this is as we're adding the data in, there's nothing below the 60. So if we're going to use 60 time steps, we have to start at point 60 because it includes everything underneath of it. Otherwise you'll get a pointer error. And then we're going to take our xtrain and we're going to append training set scaled. This is a scaled value between 0 and 1. And then as I is equal to 60, this value is going to be 60 minus 60 is 0. So this actually is 0 to I. So it's going to be 0 to 60, 1 to 61. Let me just circle this part right here. 1 to 61, 2 to 62, and so on and so on. And if you remember, I said 0 to 60. That's incorrect because it does not count. Remember, it starts at 0, so this is a count of 60. So it's actually 59. Important to remember that as we're looking at this. And then the second part of this that we're looking at, so if you remember correctly, here we go from 0 to 59 of I, and then we have a comma, a 0 right here. And so finally, we're just going to look at the open value. Now, I know we did put it in there for 1 to 2. If you remember correctly, it doesn't count the second one, so it's just the open value we're looking at, just open. And then finally we have ytrain.append training set I to 0. And if you remember correctly, I comma 0. If you remember correctly, this is 0 to 59, so there's 60 values in it. So when we do I down here, this is number 60. So we're going to do this is we're creating an array, and we have 0 to 59. And over here we have number 60, which is going into the ytrain. It's being appended on there. And then this just goes all the way up. So this is down here is 0 to 59, and we'll call it 60, since that's the value over here. And it goes all the way up to 1258. That's where this value here comes in. That's the length of the data we're loading. So we've loaded 2 arrays. We've loaded one array that has, which is filled with arrays from 0 to 59, and we loaded one array which is just the value. And what we're looking at, you want to think about this as a time sequence. Here's my open. What's the next one in the series? So we're looking at the Google stock, and each time it opens, we want to know what the next one, 0 through 59, what's 60? 1 through 60, what's 61? 2 through 62, what's 62? And so on going up. And then once we've loaded those in our for loop, we go ahead and take xtrain and ytrain equals np.array xtrain.nparray ytrain. We're just converting this back into a numpy array. That way we can use all the cool tools that we get with numpy array, including reshaping. So if we take a look and see what's going on here, we're going to take our xtrain, we're going to reshape it. Wow, what the heck does reshape mean? That means we have an array, if you remember correctly, so many numbers by 60. That's how wide it is. And so when you do xtrain.shape, that gets one of the shapes. And you get xtrain.shape of 1 gets the other shape. And we're just making sure the data is formatted correctly. And so you use this to pull the fact that it's 60 by, in this case, where's that value? 60 by 1199, 1258 minus 60, 1199, and we're making sure that that is shaped correctly, so the data is grouped into 1199 by 60 different arrays. And then the 1 on the end just means at the end, because when you're dealing with shapes and NumPy, they look at this as layers, and so the end layer needs to be 1 value. That's like the leaf of a tree, where this is the branch, and then it branches out some more, and then you get the leaf. np.reshape comes from and using the existing shapes to form it. We'll go ahead and run this piece of code. Again, there's no real output. And then we'll import our different Keras modules that we need. So from Keras models, we're going to import the sequential model. We're dealing with sequential data. We have our dense layers. We have actually 3 layers we're going to bring in. Our dense, our lSTM, which is what we're focusing on, and our dropout. And we'll discuss these 3 layers more in just a moment. But you do need with the lSTM, you do need the dropout, and then the final layer will be the dense. But let's go ahead and run this, and that'll import our modules. And you'll see we get an error on here. And if you read it closer, it's not actually an error, it's a warning. What does this warning mean? These things come up all the time when you're working with such cutting edge modules that are completely being updated all the time. We're not going to worry too much about the warning. All it's saying is that the H5PY module, which is part of Keras, is going to be updated at some point. And if you're running new stuff on Keras and you start updating your Keras system, you better make sure that your H5Pi is updated too, otherwise you're going to have an error later on. And you can actually just run an update on the H5Pi now if you wanted to. Not a big deal, we're not going to worry about that today. And I said we were going to jump in and start looking at what those layers mean. I meant that. And we're going to start off with initializing the RNN, and then we'll start adding those layers in. And you'll see that we have the lSTM and then the dropout. lSTM, then dropout. lSTM, then dropout. What the heck is that doing? So let's explore that. We'll start by initializing the RNN, regressor equals sequential, because we're using the sequential model, and we'll run that and load that up. And then we're going to start adding our lSTM layer and some dropout regularization. And right there should be the Q, dropout regularization. And if we go back here and remember our exploding gradient, well, that's what we're talking about. The dropout drops out unnecessary data, so we're not just shifting huge amounts of data through the network. So we go in here, let's just go ahead and add this in. I'll go ahead and run this. And we had 3 of them, so let me go ahead and put all 3 of them in, and then we can go back over them. Here's the second one, and let's put 1 more in. Let's put that in, and we'll go ahead and put 2 more in. I said 1 more in, but it's actually 2 more in, and then let's add 1 more after that. And as you can see, each time I run these, they don't actually have an output. So let's take a closer look and see what's going on here. So we're going to add our first lSTM layer in here. We're going to have units 50. The units is the positive integer, and it's the dimensionality of the output space. This is what's going out into the next layer. So we might have 60 coming in, but we have 50 going out. We have a return sequence, because it is a sequence data, so we want to keep that true. And then you have to tell it what shape it's in. Well, we already know the shape by just going in here and looking at xtrain shape. So input shape equals the xtrain shape of 1, 1. It makes it real easy. You don't have to remember all the numbers that we put in 60 or whatever else is in there. You just let it tell the regressor what model to use. And so we follow our STM with a dropout layer. Now, understanding the dropout layer is kind of exciting because one of the things that happens is we can overtrain our network. That means that our neural network will memorize such specific data that it has trouble predicting anything that's not in that specific realm. To fix for that, each time we run through the training mode, we're going to take 0.2 or 20% of our neurons and just turn them off. So we're only going to train on the other ones. And it's going to be random. That way, each time we pass through this, we don't overtrain. These nodes come back in the next training cycle. We randomly pick a different 20. And finally, I see a big difference as we go from the first to the second and third and fourth. The first thing is we don't have to input the shape. Because the shape's already, the output units is 50 here, the next step automatically knows this layer is putting out 50, and because it's the next layer, it automatically sets that and says, oh, 50 is coming out from our last layer. It's coming out, goes into the regressor, and of course we have our dropout, and that's what's coming into this one, and so on and so on. And so the next 3 layers, we don't have to let it know what the shape is. It automatically understands that. And we're going to keep the units the same. We're still going to do 50 units. It's still a sequence coming through, 50 units and a sequence. Now, the next piece of code is what brings it all together. Let's go ahead and take a look at that. And we come in here, we put the output layer, the dense layer. And if you remember up here, we had the 3 layers. We had lSTM, dropout, and dense. Dense just says we're going to bring this all down into one output. Instead of putting out a sequence, we just want to know the answer at this point. And let's go ahead and run that. And so in here, you notice all we're doing is setting things up, one step at a time. So far, we've brought in our, way up here, we brought in our data, we brought in our different modules, we formatted the data for training it, we set it up, we have our X train and our Y train. We have our source of data and the answers we know so far that we're going to put in there. We've reshaped that. We've come in and built our Keras. We've imported our different layers. And we have in here, if you look, we have 5 total layers. Now, Keras is a little different than a lot of other systems because a lot of other systems put this all in one line and do it automatic, but they don't give you the options of how those layers interface, and they don't give you the options of how the data comes in. Keras is cutting edge for this reason. So even though there's a lot of extra steps in building the model, this has a huge impact on the output and what we can do with these new models from Keras. So we brought in our dense, we have our full model put together, our regressor. So we need to go ahead and compile it, and then we're going to go ahead and fit the data. We're going to compile the pieces so they all come together, and then we're going to run our training data on there and actually recreate our regressor so it's ready to be used. So let's go ahead and compile that, and I can go ahead and run that. And if you've been looking at any of our other tutorials on neural networks, you'll see we're going to use the optimizer Atom. Atom is optimized for big data. There's a couple other optimizers out there beyond the scope of this tutorial, but certainly Atom will work pretty good for this. And loss equals mean squared value. So when we're training it, this is what we want to base the loss on. How bad is our error? Well, we're going to use the mean squared value for our error and the Atom optimizer for its differential equations. You don't have to know the math behind them, but certainly it helps to know what they're doing and where they fit into the bigger models. And then finally we're going to do our fit, fitting the RN into the training set. We have the regressor.fit, X-train, Y-train, epochs, and batch size. So we know where this is. This is our data coming in for the X-train. Our Y-train is the answer we're looking for of our data, our sequential input. Epochs is how many times we're going to go over the whole data set. We created a whole data set of X-train. So this is each of those rows, which includes a time sequence of 60. And batch size, another one of those things where Keras really shines, is if you were pulling this, say, from a large file, instead of trying to load it all into RAM, it can now pick smaller batches up and load those indirectly. We're not worried about pulling them off a file today because this isn't big enough to cause the computer too much of a problem to run, not too straining on the resources. But as we run this, you can imagine what would happen if I was doing a lot more than just one column in one set of stock, in this case Google stock. Imagine if I was doing this across all the stocks and I had, instead of just the open, I had open, close, high, low, and you can actually find yourself with about 13 different variables times 60 because it's a time sequence. Suddenly you find yourself with a gig of memory you're loading into your RAM, which will just completely, if you're not on multiple computers or cluster, you're going to start running into resource problems. But for this, we don't have to worry about that. So let's go ahead and run this, and this will actually take a little bit on my computer because it's an older laptop. And give it a second to kick in there. There we go. All right, so we have epoch. So this is going to tell me it's running the first run through all the data. And as it's going through, it's batching them in 32 pieces. So 32 lines each time. And there's 1198. I think I said 1199 earlier, but it's 1198. I was off by 1. And each one of these is 13 seconds. So you can imagine this is roughly 20 to 30 minutes runtime on this computer. Like I said, it's an older laptop running at 0.9 gigahertz on a dual processor. And that's fine. What we'll do is I'll go ahead and stop, go get a drink of coffee, and come back, and let's see what happens at the end and where this takes us. And like any good cooking show, I've gotten my latte. I also had some other stuff running in the background, so you'll see these numbers jumped up to like 19 seconds, 15 seconds. But you can scroll through, and you can see we've run it through 100 steps, or 100 epochs. So the question is, what does all this mean? One of the first things you'll notice is that our loss is over here. it kind of stopped at 0.0014, but you can see it kind of goes down until we hit about 0.014 3 times in a row. So we guessed our epoch pretty close since our loss has remained the same on there. So to find out what we're looking at, we're going to go ahead and load up our test data, the test data that we didn't process yet. And real stock price, data set, test allocation. This is the same thing we did when we prepped the data in the first place. So let's go ahead and go through this code. And we can see we've labeled it Part 3, Making the Predictions and Visualizing the Results. So the first thing we need to do is go ahead and read the data in from our test CSV. And you see I've changed the path on it for my computer. And then we'll call it the real stock price. And again, we're doing just the one column here and the values from iLocation. So it's all the rows and just the values from that one location. That's the open, stock open. Let's go ahead and run that. So that's loaded in there. And then let's go ahead and we have our inputs. We're going to create inputs here. And this should all look familiar because this is the same thing we did before. We're going to take our data set total. We're going to do a little pandas concat from the data set train. Now remember, the end of the data set train is part of the data going in. And let's just visualize that just a little bit. Here's our train data. Let me just put TR for train. And it went up to this value here. But each one of these values generated a bunch of columns. So it was 60 across, and this value here equals this one, and this value here equals this one, and this value here equals this one. And so we need these top 60 to go into our new data. So to find out what we're looking at, we're going to go ahead and load up our test data, the test data that we didn't process yet. And real stock price, data set, test allocation. This is the same thing we did when we prepped the data in the first place. So let's go ahead and go through this code. And we can see we've labeled it Part 3, Making the Predictions and Visualizing the Results. So the first thing we need to do is go ahead and read the data in from our test CSV. And you see I've changed the path on it for my computer. And then we'll call it the real stock price. And again, we're doing just the one column here and the values from iLocation. So it's all the rows and just the values from that one location. That's the open, stock open. And let's go ahead and run that. So that's loaded in there. And then let's go ahead and we have our inputs. We're going to create inputs here. And this should all look familiar because this is the same thing we did before. We're going to take our data set total. We're going to do a little pandas concat from the data set train. Now remember, the end of the data set train is part of the data going in. And let's just visualize that just a little bit. Here's our train data. Let me just put TR for train. And it went up to this value here. But each one of these values generated a bunch of columns. So it was 60 across, and this value here equals this one, and this value here equals this one, and this value here equals this one. And so we need these top 60 to go into our new data because that's part of the next data, or it's actually the top 59. So that's what this first setup is over here, is where we're going in, we're doing the real stock price, and we're going to just take the data set test and we're going to load that in, and then the real stock price is our data test location. So we're just looking at that first column, the open price. And then our data set total, we're going to take pandas and we're going to concat, and we're going to take our data set train for the open and our data set test open. And this is one way you can reference these columns. We've referenced them a couple different ways. We've referenced them up here with the 1, 2, but we know it's labeled as a panda set as open. So pandas is great that way. Lots of versatility there. And we'll go ahead and go back up here and run this. There we go. And you'll notice this is the same as what we did before. We have our open data set. We appended our concatenated our two data sets together. We have our inputs equals data set total length, data set total minus length of data set minus test minus 60 values. So we're going to run this over all of them. And you'll see why this works, because normally when you're running your test set versus your training set, you run them completely separate. But when we graph this, you'll see that we'll be looking at the part that we didn't train it with to see how well it graphs. And we have our inputs equals inputs dot reshapes, or reshaping like we did before. We're transforming our inputs. So if you remember from the transform between 0 and 1. And finally, we want to go ahead and take our X test, and we're going to create that X test, and for I in range 60 to 80. So here's our X test, and we're appending our inputs I to 60, which remember is 0 to 59, and I comma 0 on the other side. So it's just the first column, which is our open column. And once again, we take our X test, we convert it to a NumPy array. We do the same reshape we did before, and then we get down to the final 2 lines, and here we have something new. Right here on these last 2 lines, let me just highlight those or mark them. Predicted stock price equals regressor.predicts X test. So we're predicting all the stock, including both the training and the testing model here. And then we want to take this prediction and we want to inverse the transform. So remember, we put them between 0 and 1. Well, that's not going to mean very much to me to look at a float number between 0 and 1. I want the dollar amounts. I want to know what the cash value is. And we'll go ahead and run this, and you'll see it runs much quicker than the training. That's what's so wonderful about these neural networks. Once you put them together, it takes just a second to run the same neural network that took us, what, a half hour to train? Head and plot the data. We're going to plot what we think it's going to be, and we're going to plot it against the real data, what the Google stock actually did. So let's go ahead and take a look at that in code. And let's pull this code up. So we have our PLT. That's our, if you remember from the very beginning, let me just go back up to the top. We have our matplotlibary.pyplot as PLT. That's where that comes in. And we come down here, we're going to plot, and let me get my drawing thing out again. We're going to go ahead, and PLT is basically kind of like an object. It's one of the things that always threw me when I'm doing graphs in Python, because I always think you have to create an object, and then it loads that class in there. Well, in this case, PLT is like a canvas you're putting stuff on. So if you've done HTML5, you'll have the canvas object. This is the canvas. So we're going to plot the real stock price. That's what it actually is. And we're going to give that color red. So it's going to be in bright red, and we're going to label it real Google stock price. And then we're going to do our predicted stock, and we're going to do it in blue, and it's going to be labeled predicted. And we'll give it a title, because it's always nice to give a title to your graph, especially if you're going to present this to somebody, to your shareholders in the office. And the X label is going to be time, because it's a time series. And we didn't actually put the actual date and times on here, but that's fine. We just know they're incremented by time. And then, of course, the Y label is the actual stock price. PLT.legend tells us to build the legend on here so that the color red and real Google stock price show up on there. And then the plot shows us that actual graph. So let's go ahead and run this and see what that looks like. And you can see here we have a nice graph, and let's talk just a little bit about this graph before we wrap it up. Here's our legend I was telling you about. That's why we have the legend to show the prices. We have our title and everything. And you'll notice on the bottom we have a time sequence. We didn't put the actual time in here. Now we could have. We could have gone ahead and plotted the X, since we know what the dates are, and plotted this to dates. But we also know that it's only the last piece of data that we're looking at. So last piece of data, which ends somewhere probably around here on the graph. I think it's like about 20% of the data, probably less than that. We have the Google price, and the Google price has this little up jump and then down, and you'll see that the actual Google, instead of a turn down here, just didn't go up as high and didn't go down. So our prediction has the same pattern, but the overall value is pretty far off as far as stock. But then again, we're only looking at one column. We're only looking at the open price. We're not looking at how many volumes were traded. And like I was pointing out earlier, when we talk about stock, just right off the bat, there's 6 columns. There's open, high, low, close, volume. Then there's whether how many volume shares. Then there's the adjusted open, adjusted high, adjusted low, adjusted close. They have a special formula to predict exactly what it would really be worth based on the value of the stock. And then from there's all kinds of other stuff you can put in here. So we're only looking at one small aspect, the opening price of the stock. And as you can see here, we did a pretty good job. This curve follows the curve pretty well. It has like little jumps on it, bends. They don't quite match up. So this bend here does not quite match up with that bend there, but it's pretty darn close. We have the basic shape of it, and the prediction isn't too far off. And you can imagine that as we add more data in and look at different aspects in the specific domain of stock, we should be able to get a better representation each time we drill in deeper. Of course, this took a half hour for my computer to train, so you can imagine that if I was running it across all those different variables, it might take a little bit longer to train the data. Not so good for doing a quick tutorial like this.
With that, we've reached the end of this complete neural networks tutorial. I hope you enjoyed this video. Do like and share it. Thank you for watching, and stay tuned for more from Simplilearn.
Hi everyone. Welcome to this video tutorial by Simplilearn. In this video, we will learn about an important popular deep learning neural network called generative adversarial networks. Yann LeCun, one of the pioneers in the field of machine learning and deep learning, described it as the most interesting idea in the last 10 years in machine learning. In this video, you will learn about what are generative adversarial networks and look in brief at generator and discriminator. Then, we'll understand how GANs work and the different types of GANs. Finally, we'll look at some of the applications of GANs. So let's begin. So what are generative adversarial networks? Generative adversarial networks, or GANs, introduced in 2014 by Ian J. Goodfellow and co-authors, became very popular in the field of machine learning. GAN is an unsupervised learning task in machine learning. It consists of two models that automatically discover and learn the patterns in input data. The two models, called generator and discriminator, compete with each other to analyze, capture and copy the variations within a dataset. GANs can be used to generate new examples that possibly could have been drawn from the original dataset. In the image below, you can see that there is a database that has real 100 rupee notes. The generator, which is basically a neural network, generates fake 100 rupees notes. The discriminator network will identify if the notes are real or fake. Let us now understand in brief about what is a generator. A generator in GANs is a neural network that creates fake data to be trained on the discriminator. It learns to generate plausible data. The generated instances become negative training examples for the discriminator. It takes a fixed length random vector carrying noise as input and generates a sample. Now the main aim of the generator is to make the discriminator classify its output as real. The portion of the GAN that trains the generator includes a noisy input vector, the generator network, which transforms the random input into a data instance, a discriminator network which classifies the generated data, and a generator loss, which penalizes the generator for failing to halt the discriminator. The backpropagation method is used to adjust each weight in the right direction by calculating the weight's impact on the output. The backpropagation method is used to obtain gradients, and these gradients can help change the generator weights. Now, let us understand in brief what a discriminator is. A discriminator is a neural network model that identifies real data from the fake data generated by the generator. The discriminator's training data comes from two sources. The real data instances, such as real pictures of birds, humans, currency notes, etc., are used by the discriminator as positive samples during the training. The fake data instances created by the generator are used as negative examples during the training process. While training the discriminator, it connects with two loss functions. During discriminator training, the discriminator ignores the generator loss and just uses the discriminator loss. In the process of training the discriminator classifies both real data and fake data from the generator. The discriminator loss penalizes the discriminator for misclassifying a real data instance as fake or a fake data instance as real. Now moving ahead, let's understand how GANs work. Now GANs consists of two networks, a generator which is represented as G of x and a discriminator which is represented as D of x. They both play an adversarial game where the generator tries to fool the discriminator by generating data similar to those in the training set. The discriminator tries not to be fooled by identifying fake data from the real data. They both work simultaneously to learn and train complex data like audio, video or image files. Now you are aware that GANs consists of two networks, a generator G of x and discriminator D of x. Now the generator network takes a sample and generates a fake sample of data. The generator is trained to increase the probability of the discriminator network to make mistakes. On the other hand, the discriminator network decides whether the data is generated or taken from the real sample using a binary classification problem with the help of a sigmoid function that gives the output in the range 0 and 1. Here is an example of a generative adversarial network trying to identify if the 100 rupee notes are real or fake. So first, a noise vector or the input vector is fed to the generator network. The generator creates fake 100 rupee notes. The real images of 100 rupee notes stored in a database are passed to the discriminator along with the fake notes. The discriminator then identifies the notes and classifies them as real or fake. We train the model, calculate the loss function at the end of the discriminator network, and backpropagate the loss into both discriminator and generator. Now the mathematical equation of training a GAN can be represented as, you can see here. Now this is the equation and these are the parameters. Here G represents generator, D represents the discriminator. Now P data of X is the probability distribution of real data. P of Z is the distribution of generator. X is the sample of probability data of X. Z is the sample size from P of Z. D of X is the discriminator network, and G of Z is the generator network. Now the discriminator focuses to maximize the objective function such that D of X is close to 1 and Z of Z is close to 0. It simply means that the discriminator should identify all the images from the training set as real, that is 1, and all the generated images as fake, that is 0. The generator wants to minimize the objective function such that D of Z of Z is 1. This means that the generator tries to generate images that are classified as real, that is 1, by the discriminator network. Next, let's see the steps for training a neural network. So we have to first define the problem and collect the data. Then we'll choose the architecture of GAN. Now depending on your problem, choose how your GAN should look like. Then we need to train the discriminator on real data. That will help us predict them as real for n number of times. Next, you need to generate fake inputs for the generator. After that, you need to train the discriminator on fake data to predict the generator data as fake. Finally, train the generator on the output of discriminator. With the discriminator predictions available, train the generator to fool the discriminator. Let us now look at the different types of GANs. So first we have vanilla GANs. Now vanilla GANs have min-max optimization formula that we saw earlier, where the discriminator is a binary classifier and is using sigmoid cross entropy loss during optimization. In vanilla GANs, the generator and the discriminator are simple multi-layer perceptrons. The algorithm tries to optimize the mathematical equation using stochastic gradient descent. Up next we have deep convolutional GANs or DC GANs. Now DC GANs support convolutional neural networks instead of vanilla neural networks at both discriminator and generator. They are more stable and generate higher quality images. The generator is a set of convolutional layers with fractional strided convolutions or transpose convolutions, so it unsamples the input image at every convolutional layer. The discriminator is a set of convolutional layers with strided convolutions, so it downsamples the input image at every convolutional layer. Moving ahead, the third type you have is conditional GANs or CGANs. Vanilla GANs can be extended into conditional models by using an extra label information to generate better results. In CGAN, an additional parameter called Y is added to the generator for generating the corresponding data. Labels are fed as input to the discriminator to help distinguish the real data from fake data generated. Finally, we have super resolution GANs. Now SR GANs use deep neural networks along with adversarial neural network to produce higher resolution images. Super resolution GANs generate a photorealistic high resolution image when given a low resolution image. Let's look at some of the important applications of GANs. So with the help of DC GANs, you can train images of cartoon characters for generating faces of anime characters and Pokemon characters as well. Next, GANs can be used on the images of humans to generate realistic faces. The faces that you see on your screens have been generated using GANs and do not exist in reality. Third application we have is GANs can be used to build realistic images from textual descriptions of objects like birds, humans, and other animals. We input a sentence and generate multiple images fitting the description. Here is an example of a text-to-image translation using GANs for a bird with a black head, yellow body, and a short beak. The final application we have is creating 3D objects. So GANs can generate 3D models using 2D pictures of objects from multiple perspectives. GANs are very popular in the gaming industry. GANs can help automate the task of creating 3D characters and backgrounds to give them a realistic feel.
And we're going to be going over the OpenCV tutorial. And it's going to throw in some Keras, and we're actually going to be covering a lot of ground in this tutorial, so I'll speed up for some of it and slow down as we focus on important aspects. When we talk about OpenCV, we're really talking about computer vision. So what is computer vision? And I would say OpenCV goes way beyond computer vision. It goes into graphic editors and all kinds of other things. But we're going to be focusing a little bit on computer vision, and we're going to cover the whole slew of the editors and all the other cool stuff that's in there. Computer vision is a field of machine learning whose goal is to help computers see. Its end goal is to make intelligent systems which can understand digital images. And there's all kinds of different examples, from handwriting, identification, categorizing of pictures, is that a dog or a cat in the picture, and all that different things. Those are all part of the computer vision. Cars, the new automated cars, and being able to drive down the road, they usually use aspects of computer vision to do that for our AIs. So what is OpenCV? OpenCV is a huge open source library for computer vision, machine learning, and image processing. It can be used to process images and videos, to identify objects, faces, or even handwriting of a human. And one of the cool things is the OpenCV project is outside of Python, but it has a high integration with Python. So you can use it in other programming languages. You're not set to just Python with it. And it has a huge community behind it, which is really nice. That's what makes the OpenCV project so great. We'll start with installing the OpenCV. It's pretty straightforward. In Python, you do a pip install opencv-python. You can pip install OpenCV contrib python headless. OpenCV can be installed in Windows, Mac OS, or any GNU Linux distribution by using the pip command. The first command we went over is to install the main module packages, and the second one is for the full package. And usually you want the full package. Once you start digging into it, it's so easy to use, and there's so much fun things you can play with. So the most common thing is reading in image in OpenCV. And we'll do this also in code. So if I go a little quick on the slides, it's so that we can roll up our sleeves and actually open up and do the coding on there. So when we're reading an image in an OpenCV, given an image to load it in, we can use the OpenCV function IamRead. The image can be displayed using the function IamShow. And so these are your two main categories on here. And so your basic thing is to read an image in, then you can manipulate it, and then you can display it depending on what you're using it for. And then when we talk about manipulating it, the most common thing is probably resizing images and videos. So you can read in videos, and we'll look at the command for that also and how you can process them frame by frame. Resizing is helpful in all kinds of aspects. Obviously on the display, you might want to resize it so it fits the display a certain way. A lot of times that's handled for the size of the image. If you're uploading it to the web, you might want to have a smaller image so you're not taking up a huge amount of memory. Not as big of a deal anymore, and then a lot of times the actual web page would handle the size of the image once you upload it. But what if you want to process all the images under the same neural network? Well, they're going to look for the same size, and that's also is huge, just to be able to resize your images to go into that neural network, so you're not looking at different sized images. And images read in might not be of correct size or might not fit the screen correctly. To overcome this, we can resize the image, and you can see it's a real simple command in the CV. And we're actually using what they call CV2. A lot of times people just they'll import CV2 as, or OpenCV2 as CV just to make it easy, because they might have old code or something like that, and it's easy to swap things in and move forward. And you can see here we just resize, we have our image, we have our new dimensions, and then how do we resize it? The interpolation is kind of a function in there as far as how to guess the colors, because you're combining colors and different things. And we can use drawing with the OpenCV. We can draw images in OpenCV. It allows us to draw various things like a rectangle, circles, lines. You can add text into the images and that kind of thing. So there's a whole slew of different things we can do with the OpenCV. And we'll look at these commands. We'll glance through them and show you how they work in the actual software. And they have basic image functions. And this is just so cool because so much of this is built in. You go back 10 years and people are writing the code to do this stuff, and now it's all built in and people are continually optimizing it. So you can do a lot of things without having to lift the hood up and really do the heavy lifting underneath. And so OpenCV has built-in functions which allow us to perform various operations on our images, such as blurring, resizing, cascading, edge detection, and cropping. And there's also motion detection in videos. There's all kinds of things. And you can see here we have blurring, where you can take an image and blur it slightly. We can resize it. It's easy to crop it, you know, that we can do the little round head face cropping on a web page or whatever. Or identify where the object is and crop the background out, kind of thing. And then you have image transformation. We talked a little bit just a second ago on blurring. We can also do things like rotating it. We can transform the image various ways. You can see here we can shift it. So we can shift it left, shift it right, flip it, crop it. All of these are very easy to do in the OpenCV package. And then I mentioned a little bit about, we start looking at motion detection and detecting different things. There's contour detection, which is built into the OpenCV package, which is really nice. And again, this is stuff that usually was somebody in the back end programming this, and now you have OpenCV, which does almost everything for you. So a contour is a curve or a line joining all points which have the same color or intensity. Contours help us find the points which lie in the same plane and assist in edge detection. And you can see here we've taken the cat and done a contour detection, and it kind of makes it look almost like someone stenciled it in there. So it's kind of cool, little Zen art going on there. This is how the computer might, using contour detection, see the cat on the black background. And then you also can adjust the color channels. So you can play with all the colors. Any image is basically a combination of three main colors: red, green, blue, the RGB. Sometimes a quick note, which we won't cover in the programming, is when you see that RGB, it's not always in that order. There's different formats for it, and there's also sometimes the alpha channel. So you might have RGB-A, where A is how transparent it is. So you might actually have 4 channels, which I like to work with when trying to take the background out, because the edges of images actually have reflections, and light is also a curve and wraps around. So there's some cool things to note when you're messing with these things. And the OpenCV allows us to split our image into its respective color channels. And you can see here we've taken the image of a little landscape and we've sorted it out into different channels, and you can see how you have it all in the blues, the reds, and the greens. And there's also color spaces. Color spaces are a way to represent the color channels present in an image. They tell us the various color channels which are contributing to a particular hue. So again, we can pull things out based on the hue and the images and colors on there. And blurring. Blurring is very popular right now because it's easy to find someone's face and then blur out the background without having to play with alpha channels and different things for the coloring around the, you have the edging of the head and the coloring. So blurring is a method used to remove noise from an image by applying a low pass filter over an image. We smooth out the edges and make the transition from one color to another very smooth. And you might not be able to see the difference in the cat video, but you start seeing smoothness and sharpness have always been a mainstay of editing images and things like that over the years. And so this is all built into OpenCV. And then there's bitwise operations. Bitwise operations are the and, or, XOR, etc. in image processing. They are used to create a new image or for masking. And we'll glance at masking, but masking is huge. So when we get into the code, we'll talk a little bit more about masking. I'll probably maybe offshoot for a minute on that. The operation is done between each pixel of 2 images. And so you can see here we have the square plus the circle. So if it's an and, only where the white is. So where it's in both images, it then equals a new image with just the white parts. In masking, masking is used to bring certain parts of an image into focus by lowering the definition over other parts. This is done by reducing the pixel quality of other parts of the image. Kind of a little short on the masking of what it is. So in this case, the masking would either be the background, might be all ones, and the cat in the fence might be zeros, or vice versa. We might put the cat as 1 and the background as zeros. And then you can do a transformation on either the background or the foreground to, maybe you want to blur the background out and make the foreground sharper. Or maybe you want to make the little circle with the cat in it, take the colors out so he's one color. Masking allows you to separate your image out and do those different things, and that's where the masking comes in. And it has a lot of uses. And then there's histograms. Histograms, in an image processing, histograms typically refer to a graph of pixel intensity values. The intensity of each pixel is plotted in a histogram. Again, we start with these histograms are the beginning of doing different identifications and can be used for different things. You don't really publish a histogram onto your web page of the cats because it's just kind of silly, but you can use that data in data processing to look at different things and pull different things out of the picture. Thresholding, another important aspect of image processing. A method of image segmentation. It is used to convert an image of binary by setting a threshold intensity value and deeming all values above it as 1 converted to white and below as 0 black. And you can see here we were talking about masks. In the threshold, we're able to actually create a mask of the image. In this case, you have the cats, which are mostly white, stand out because we put whatever the value is to pull those cats out and put the background further back. Edge detection. Just like threshold, it's another tool we can use to bring out an image. So we can find different things on there. A lot of cool things we can do with that. You can see here we've taken a landscape, same one we had before, and we can find the boundaries of an image by consistency and brightness. It's used for image segmentation and data extraction. And you can see with this image of the buildings how powerful it is just to pull the whole sky out. I mean, you know where the sky is. There's no debate on it. So finding edge detection has a lot of cool things it can do when you're processing images and pulling the images apart.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
So with that, really the hands-on, there's so much hands-on on this. So we're going to start with a real basic OpenCV setup in Python. We'll then take a look at some motion detection. I usually don't put the video on here because my office is under construction. You can see the partially finished wall in the back. When we do the motion detection, we'll have the video up and show you how to pull this video in, just like I'm doing here, and utilize that in a program. You can actually start detecting motions. You could think of a wilderness webcam or something like that, all kinds of fun things you can do with motion detection. And then we'll get into melding a little bit with the OpenCV and write a short Keras neural network that will train and do facial identification. So we're going to cover just a slew of really cool tools that you can do with OpenCV. So here's my favorite package to work in, the Anaconda. I'm going to be in Python 3.8. And then if you haven't yet, you need to go under environments. You can either install them through Anaconda here, or you can open up, let's see, where is it, 3.8. You can open up your terminal and do the pip install like we discussed earlier in the slide. And that was this slide right here. Pip install OpenCV contrib Python headless. I would just go right for the second one because it installs everything. So it's the full package. And you would just go ahead and open up, in this case, Py38. There's my terminal window, and I can simply do my pip command in here. You can also, if you're in Anaconda, we can go in here, let's do all, search the packages for OpenCV. And you can see here's your OpenCV, library OpenCV, Python OpenCV, and I actually installed all of these. All these are installed on my Anaconda for the use of this setup. Didn't want to miss anything. And then once we open this up, we're going to go in here to New and create a new Python window, Python 3. In this case, we're in 3.8, as I told you, which is what's set up in here. And we'll start with just OpenCV general. So let's put that in here, OpenCV. That's just a general setup on there for doing our OpenCV. And of course, some people like to, I'm not big on looking at my own face the whole time during these, but we'll go ahead and put my video back up there. And when we talk about the OpenCV, we want to go ahead and import all of our different aspects of what we're going to be working on in here. And you'll see on this, we have our import CV2. And I mentioned earlier that a lot of people, when they see the import CV2, they just go ahead and automatically do it as CV. That way, if you're using older code, it doesn't bother me too much to use CV2, but a lot of people prefer to just keep that as an open. Someday they'll probably have CV3, who knows. We want our numpy for our numbers array. Sometimes that comes in. We have our matplot library kind of by default, and we'll do our matplot library inline just because we're in Jupyter Notebook. That way if we do any plotting, it's not really going to affect what we're working on. I just do it as a standard. Pretty straightforward. And then before we get started, let me go ahead and pull over. We have a file set up on here with some images in it and some videos. And just like any of our other setups in Simplilearn, if you need a copy of some of these images, of course, it's pretty easy to come up with your own images and your own videos nowadays. But if you wanted to rerun this and set this up, you can certainly have them send the information over there with, in this case, we have the cat, which is going to be an image. We have a dog, which is going to be an MP4 video. And then we have, when we do facial recognition, we took some of our very well-known actors out there, like Ben Affleck, Elton John, the musician, Jerry Seinfeld, and other people. So we can actually train a Keras setup on there and do a facial recognition on there. And again, all of this you can send to Simplilearn and say, hey, can I get a copy of some of this information? And so we're going to start out, the first thing we want to do is just the most basic thing, which is read in an image and display it. And then I'm going to go ahead and, let's see, I'm going to cut this in half. I used to have this in Windows 10 where I just hit a button and it dropped my background and everything. So we're going to look at the horrible blue color of the Windows default. You'll just have to ignore my icons up there. And so we're going to be reading images. And the reason I did a half screen here is because when they pop up, they don't necessarily pop up by default in front in the Jupyter Notebook. So you're not even going to see them. They'd be hidden behind there. The first thing we want to do is just a basic reading of an image. In this case, we're just going to read the file cat.jpg. There's no path in here because I went ahead and saved it in the same folder that the program's running in. But if you have it in a separate folder, you'd want to put that full path in there. And so it's real simple. We have image, we have cm.imread or read. I don't know which one they use. imread. And then cv imshow. Image, and that just stands for image show. And cats, and then image. Cats is the title of the window that's going to pop up. And let's go ahead and run that. And you can see here we have our window that pops up, and there's our cat. So that's really straightforward. If you're looking at that, there's nothing really difficult. And this is why I like OpenCV so much, because it's so easy to use. And if we're going to do the image, if you remember we had dog video going on. Maybe my image up a little bit. There we go. We can go ahead and play a movie, and that is really cool. And by the way, when I was messing with this, it does actually store the sound file with the MP4. So if you have the video playing and the microphone going, it will store both of those as a separate. There's like another channel it stores in the CV when it's reading these things. In this case, we're going to go ahead and capture. We need to go ahead and tell it what file we're capturing. In the next video, we'll actually do one of the next two sections. We'll show you how to capture the camera you're actually looking at. But in this one, we have capture CB video capture dog.mp4. Pretty straightforward. It just says here's the file we're going to capture. And then it says while true, and this, if you're doing a lot of programming in Python, you should recognize this. Instead of setting is true to true and then letting it switch each time, we just say, hey, if not is true, break, and that will break the loop. And so what we're doing here is we're going to read each frame of the video as it goes. Is true frame equals capture.read. If is true is false, it breaks, so we're done. We've hit the end of the video. And then we're going to show the video, in this case of the dog, cute little puppy. And it's going to be by frame. So each frame is showing, and you see we have a wait key here. This has to do with the encode in the back. So you could probably leave it out in here, but it's usually good to leave these particular things in. this particular key in there because it does actually, there are times when that can affect the runtime. And you can see here's our little puppers, smiling and having fun. And it's playing each of those frames. So as you're watching it, it's going through, I don't know how many frames per second, probably 30 frames per second. And so it's displaying 30 frames one after another. And if you have sound with it, it by default will play the soundtrack with there, just so you know. We're not doing too much in sound on this one, that we're just focusing on the OpenCV video. And then when you're done with something, you'll see me flash this up a bunch of times. We're going to have the destroy all windows from the CV, which closes everything we got going. When we're dealing with videos, one of the issues is you have a buffer in your video. And so you'll see this kind of coding where it says wait key 60. And it's just waiting an extra period of time to make sure everything's cleared out of memory. That's all that does. And so you can see we just closed all the windows that came in on there. And then one of the cool things we can do, and we're going to do a bunch of stuff with images in just a minute, but let's start with the video. We can do resizing. And so we have a rescale the frame. We're going to send it the frame, we're going to send it the scale, and it's going to compute the height, the width and the height based on what we send for a scale. We'll put it into dimensions, and this right here is our resize. CF resize the frame, and this could also be an image. You're not stuck with just a frame when you do this kind of resize. And then this is the code they use for resizing. Not a whole lot to look in there. It does come up sometimes because there are a couple different mathematical codes of how to blend the colors together and make it smaller without it becoming really chunky or really, they used to just delete, like if you cut it in half, you just delete every other pixel. And then, of course, you're deleting information instead of melding it together. And this moves it over. That's what this is doing right here, this interpolation equals CV inter area. And then we have the change the res. We're going to be doing a live video, so when you change the resolution, again, there's not a whole lot to look in here. It's just helping us so that the resolution keeps it looking nice on there. And then we have this should look familiar from above. We do our capture. We need to set up where the video is coming from. We got to let the CV, the OpenCV, know what which file it's using. And then it says while true. This is again just like above. If not is true, break. And here's our frame resize. And then we're going to do CV IMShow frame, and then we're going to do CV IMShow frame to resize. This should look just like you saw before. And then we have our this extra code here in case we need to break early. Now I'm going to run this, and we're going to get if you're looking at this, you should say, oh, we have two different videos going. One of them is labeled video, and it's based on frame, and one is video resized based on frame. So we're going to end up with two completely separate videos playing at the same time. And let's go ahead and run and see what that looks like. You'll know one of the videos is obviously going to be the dog because we saw him before, and you can see right here, there the dog is resized. And we could easily take this scale. Yeah, we'll go this way just a little bit. And instead of 0.5, maybe we want to do 0.25 because we want it to be like a little thumbnail on there. Let me run that. And you can see how it nicely rescales it down to a quarter of the size. And then I'm going to keep the split screen. You'll see why in just a second. Let me go ahead and destroy the windows and clean up our desktop that we're working on. And we're going to go back to image editing. So we're going to go through a bunch of different editings you can do on here. Now, this next part, we're zooming through. There are so many things you can do with the OpenCV. First, we're going to just draw a blank box. We'll go ahead and run this. Here's my blank box. It's got nothing in it. And we can take, if you notice I've created blank, oops, there's my blank. We filled it with zeros. So this is a 500 by 500 by 3 channel. There's actually, it can be 4 channels if you have the alpha, which is the see-through. and this will handle an alpha channel, but you have the 3 channels in here, and you create a nice blank box that's just black in there. And then if we're going to do a blank box, we can actually take, let me go back in here, there we go. We're going to take this blank box and we're just going to fill it. I'll leave it called blank. We'll run this, and I'm putting in from 200 to 300. That's actual pixel counts. Remember, this is a 500 by 500 box. And we're going to do from 200 to 300 and 300 to 400. That's the upper left and bottom right corners of the array. And we're going to sum to 0, 0, 255, which happens to be green. And this is RBG. Be a little careful because some of the formats switch the order from red, blue, green to different colors. And if we run this, you can see here we've actually added, oh, I guess I did a red box. For some reason I thought that was a green color. I must have it switched around on there. But you can see right here that we can actually go in and we can change any pixel in here. And it works like a numpy array, which is really nice because now I can edit my blank box here and do different things in the blank box and fill it in there and draw lines. We'll go ahead and do a rectangle. Like I said, some of this is going to be quicker to pasting in here and showing you. We're going to take a rectangle and, oops, it's hard to see here. Create the shape. Let me open this up a little wider. There we go. And in the rectangle, we're going to use blank. I'm going to show it. We're going to give it a new window. That's what this is doing down here. If I left this blank, it just put the rectangle on top of everything. And we're going to use blank as our basis, starting at 0, 0. And you can see our different dimensions and thickness -1. And there's my weight key on the bottom. And let me go ahead and run that. Oops, it should have done an I am show. Which it did, but it was behind our Chrome. You can set where it appears on the window. We should probably do that on here. But you can see it opened up a new window. This window is called rectangle. This one's called blank. And so these are 2 completely different windows that we've set up on here. If I had changed this to blank, it would have just put the rectangle on top, just like it did the red square earlier. And we can do a lot with this. We can go ahead and draw, let's see, a circle, a line, and then put some text on here. And we'll take the same blank setup, since that's our basis right here is blank, and we'll go ahead and create all of those. And let me go ahead and paste that in here. And you can see here we have our CV circle. It's going in on the blank. We have our dimensions of the circle. Let me just bring these down a line so you can see a little bit better what we're looking at. There we go. And then we're going to do the color on this, the thickness -1. And this is basically a radius of the circle kind of setup. I'd have to look up to remember the exact what these different numbers represent. But you have the different sizes of the circle. We have a line here. We're going to draw a line blank. In this case, we have 300, 400, 255, and you can see a setup in here. This is again the color, the starting point, the end point, and a thickness of 3. So a lot of this is pretty straightforward, and this is going to open up a new window called line, because that's what we called it instead of putting it on the blank. And then we'll do text. Now on each one of these, we're adding the line to blank, so it's in the original blank square that we've called blank. But on each one of these, we're opening it up in a new window. We could easily continue to put them in the same window, and you could turn it into a video or some other kind of thing. And you can see down here, hello, my name is Jason. My name isn't actually Jason. And we have our location that we're going to print Jason on there, and the font, and the size, and the color, and dimensions of it, and then show text. And let's go ahead and run so you can see how all these show up on here. And if I open up my screen a little wider, you can see that we have our code, and we did certainly add a circle on here. Here's our circle. We added a line on here. Here's our line. And we've added text on here. Hello, my name is Jason. Probably should have picked a different color instead of matching it with the square box we put on there. And just like all of this, we want to go ahead and clear the data. Keep a nice clean screen. And I'm not sure why it keeps printing this stuff underneath. I gotta go fix that. And the next section we want to cover is going to be your grayscales and blending and masking and stuff like that. And let's go ahead and clear our little palette. I don't know what else to call it. That's a good name for it, palette. And here we go. You remember this one. We're going to load our image. In this case, we're going to load the image park, and we're going to display park. We get that nice view of the park. That's what we did before. And there's so many things that are built into OpenCV on here. One, we can grayscale it. And we're just going to take, and you can see here we're converting blue, green, red. Remember I said there's 3 channels. You got to be a little careful what order they're in. I can never remember. I have to actually pull it up every time I go in here because I jump around between so many editors and software. It's just the nature of dealing with pictures sometimes. But you really have to make sure you catch that and double check it. And so we're just going to, this is just a conversion, and that's what the CVT stands for, color. And then we'll display this in grayscale it. And you can see it did a nice job. There's our park. Oops, if I can grab it. And there's the grayscale on there. And then we can do such things as blur. So I can come in here and we can go ahead and this uses CV Gaussian blur. And there's a lot of settings as far as how the blur works. And then you can see here we got border default, CV border default, 7.7. I believe that has to do with the square and the pixel range. When you do a lot of blurring, then you start messing with it. And we can see here's the park up here. We went ahead and grayscaled it. Oops, there we go. Gray not responding because I hit the wrong button on this. And blur. There's our blur on there. So we have a couple different setups on that. There's also edge cascade. Some of these you just pretty much, you really have to know you're editing on videos. I'm not a huge video editor. So when I do a lot of this stuff, I'm not really sure what it is I'm doing. Like I know what blur is obviously, but I don't know what edge cascade is. Except for now that it comes out, you can clearly see that it draws lines dealing with where the different colors meet and how they connect. That's a really neat tool. It puts a nice it literally creates a nice mask of the edging. And you could see where you could use this to pull out, in this case, the sky quite easily from the whole picture. And there's dilated. Let me go ahead and run that. We can see what that looks like. Oops, give it a second to pop up to the top. Keep in mind that the dilated used the edge as our input. So we took the canny, the blur. Oh, there we go. Yeah, canny blur. Dilated used the canny. So we have our blurred coming in from the canny edges. Quite the terminology there if you're trying to follow it all. We have eroding. Let me just show you some of the settings on there. We have the number of iterations for doing eroding. So let's go ahead and run this one. And you can see how it changes the settings or the view on there. And this brought in the dilated and then eroded it back into, I'm guessing it kind of sharpens it from the blurriness we saw in the one before it, the dilated. And then of course probably one of the ones that I use the most, and I use the resize. And the reason I use this a lot is because I work in data science. And so if I have it coming in as a certain size on there, if the neural network is processing an image with a certain size, all the images coming in have to be that size. And so we have here resizing our image. And let's go ahead and run that. And you can see how we took the, in this case we used the original image and we just resized it to a smaller view on there. And if we can resize the image, we can also crop it. Again, data science loves cropping. This is, you could literally crop pictures and resize them and rotate them and make that your new input for doing categorization. And we'll actually show you how we can automate that when we get to the facial recognition Keras part of this tutorial. But we can see here we can also crop it. And we just take the picture and crop a small piece off of it there. And just like we did before, let's go ahead and clean our palette, start it over again. And again, we're just chugging through these. These are commands that, depending on what you're doing, depends on what you need. So if we're looking at changing it to grayscale, sometimes processing something in grayscale in Keras is easier. It's able to pull out the dimensions better. Blurring, that's more of a display kind of thing, where you're going to display it with a slight blur. Finding the edges, that's kind of cool. You can actually come in there and maybe use those edges to help you find something in the foreground and in the background. Dilated, give it that little blurry look. Eroded, bring it back into sharpness. Resize it and crop it. All those are things that are just neat tools to have at your fingertips and easy to use. Some of them might be more for a website and bringing up icons and cropping the headshot or something like that, where others are kind of more general use in just about any industry. Another feature is being able to translate. Transmat float 32. Remember, a lot of these things, let me just full screen this here real quick. We have our image coming in, and then we can translate it 100 in different directions on here. There's so many different things we can do with this. So as we go through this, oh my goodness, I hit a button on here. Okay, give me just a second. There we go. Okay, so let's go to translate. It's on translate on there. And we have the cat, and you can see how we've translated it down instead of the full image of the cat that we had before. We can also rotate. Rotation, like I mentioned earlier, is a fun thing to do. And we'll actually do that when we do the Keras thing, because you can process the same image at different angles, and then you've just multiplied your input as far as doing identification. In this case, you can rotate on here. We have the angle, the rotation point, none. I believe it puts it in the center. I'd have to look that up. And then you have the image shape, height, width. Rotate point is none. Width, height. So this is actually going to put the rotate point in the middle. If we send it a none to this little routine that they put together in the back. And then we're going to warp. This is the actual command here, warp affine. And you have the image, you have your rotate map, and you have your dimensions on here. And if we go ahead and plug that in, and we put the rotate in image at -45, let's see what happens. And we're going to run that. And you can see how it nicely rotated the cat's head, although it's a little creepy the way it looks like it cut the cat's head off on there. Maybe move it, translate it down a notch, just so you can't see the cutoff point. And we already did the resize, but we'll run that again so you can see how it gets resized on here. And be aware when you resize them. I do a lot of resizing for putting it into neural networks or into some kind of machine learning setup, but it does squish it. It squishes it and stretches it, and so if you're doing this for, say, display and re-editing, you might want to be a little careful about that. Make sure that you maintain the same ratio unless you intentionally want the cat to look taller and thinner. And then we can also go ahead and flip it. As you can see here, we just flipped it upside down. -1, you can probably flip it a couple different ways. I'm curious as to what -2 does. Shoop, same thing. Maybe if we put minus... And a 1 is not, well, 1 is just flipping it all the way to the opposite side from left to right. So you can see here we can flip it around a little bit. That's kind of a fun thing to have. One of those things you might have a hotkey for if you're doing some kind of picture editing and giving a lot of choices. And we also already did the, see, there we go, cropping. So you can see here where a cropped image equals the image, and we just pick out the pixels we want, and then we can show the cropped image over here. And it's just a cropping of the face. In this case, we grab 200 to 400 as the upper left corner and 300 to 400 as the bottom right corner. And let's clear our palette again. And then we're going to do contour detection. And there is so much that goes into all this. I mean, we're flashing through a lot of things, and you can see how you might combine them and use them for different things. So we're going to go ahead and get our cat back up as our image. And let's go ahead and do image shape. We're going to take an image shape and we're just going to create a blank screen for it. So this is just a blank screen here based on the shape of the cat. And strangely enough, this is done a lot. The reason that we would create a blank thing is or a blank image, is you might start filling in information on there and using that as your template for different things. And so it becomes a mask of sorts. There's an actual mask in the program, a little bit different, but you can imagine if this is your blank screen you start with, you might add circles or squares or whatever on there. And we can do the same thing here with, we can convert our picture to gray. We did that earlier, which is always kind of fun to see the cat comes back. And being that I'm messing with a lot of different feeds and stuff like that, it's you can see I got an auto responding going on there. When you do a lot of this stuff, that's what you'll start seeing more of that as you mess with it. It'll eventually come in. You just got to give it some time. There it is. There comes in my gray one on there. And we have the Gaussian blur, so we can take it and blur the image. And in this case, we fed it the gray one. So you can see the very clear mouth underneath on the gray one, and then the more blurry one on top on there. If you remember, we did earlier, come back on here, canny edges. So again, we're doing detections and things like that and looking for different things. And there's another feature called CV threshold, or the CV threshold. And in this case, we're going to send it the gray picture. And let me just pull the coding down here. There we go. And you can see here we're going to do CV threshold based on binary. Let's set up on here, and we'll go ahead and just run this so you can see what this looks like. Run. There we go. That's actually really cool how it picks up on that, on the threshold. And you can see how it just turns it into almost a black and white image. That can be a lot of fun too. And we can also look at the contours in the OpenCV. So we talk about that. We have our, let me just open this up all the way so we can see the code. We're going to return the contours and the hierarchies. And we're going to pull this off of Canny, the Canny one that we sent up here earlier. And we have the retrieve list and chain approximate sample. So there's a lot of options in here that we can follow. Let's go ahead and run that. Let's go back down here. Where are you? Up there we go. And when we run this, we get a nice setup on this. It says, hey, there's 74 contours found on here. And that's actually starts turning this into a math on, whoops, which one did we feed it? We fed it the Canny up here. So we start to look at these different setups. Let me get this out of the way. Where's Canny? There's Canny in the back. And you can see that this drew 74 different like line connections on here. So now we're starting to actually turn this into almost a mathematical formula on this. And while we're looking at these, we'll go ahead and do draw contours. And here's our contour. Let's return the contours up here. And we're going to put this on the blank. Remember how we did the blank earlier? So we're actually going to take the blank as, remember I told you could use it like a base setup on there, and we can now redraw the contours, but in this case, we changed the color. So now we're drawing the contours in red. So that's just kind of a fun thing you can do on there to change the, literally change the appearance and the setup on there. And let's go, of course, clean up our setup and destroy all our windows and move on to the next section. And we're going to look at color spaces. And let's start with, in the color spaces, we're going to read an image in. And I'm going to go ahead and show the image park. Let me just run that. Oops, I forgot to put the wait key in there. A lot of times the wait key just helps because I'm pushing all these graphics out through a single kernel because I'm working in Jupyter Notebook, and things get hung up. And so waiting that extra 60 milliseconds can sometimes really help. Sometimes as we start flashing these pictures up and down, you'll see there's no response and other things come up. that really is just because we're pushing so much out there. Now, one of the interesting things on this is we imported matplot library. And so matplot library can now easily be integrated with our imagery. And you can just see all we got to do is just dump the image into the matplot library. And now I have the image here showing on my matplot library setup. One of the things you're going to notice on this is the colors all look off. Well, again, you see that, and you see that they're supposed to be the same thing, and you should jump and say, oh, one of these is RBG and the other is GBR or BGR or something like that. And so it's reading reading the colors in a different order. That's all that means, and you have to do a transformation at some point to fix that. So let's go ahead and take a look at, we'll go ahead and go back and grayscale it again. We're going to take our image of the park. We'll put it into gray. Run. There we go. And in here we can convert our color, and this is what we were just talking about. We can convert the color scheme. Let me go ahead and run this. And you can see here we swapped the scheme out. And then I'm curious, because we did up here plot it. What does this look like when we plot this new color down here? This new scheme. What does that look like on our setup? Let me go ahead and just go down. There we go. And we called this HSV. So we'll go down here, and instead of image, I'm going to plot HSV. And let's run that. And still way off on color schemes. You can see we can really mess up with this. HSV is another type of color scheme. I was curious because I did not think it would come up correctly, but I wanted to see if it would. And we can also do a conversion to what's called, there we go, BGR, blue, green, red, to lab. And lab is just another color scheme on here. And so you can see when we swatch the color scheme, it has some really cool effects as far as what it looks like in their view. Lab ranges from, it's kind of luminosity, and then it has like then the channels coming in. So it's a little bit different setup on this, but really you have to just play with these to see what they look like. And we talk about all these different color schemes and all these switches on here. Now, the one that we were talking about earlier, I mentioned, was the BGR to RGB, because we use the BGR. We'll just run this, and we see the color change on that. And then we'll go back up, because I'm still curious. Okay, there we go. Copy. If this is the same that Matplot Library uses. And we'll just type in RGB down here, because that's what we called our figure. And we'll run this, and it will display it. Oops, it comes up there and gives us a problem because capitalization. Whoops. RGB, there we go. So let's go ahead and run that. And that looks pretty close to the original. So this is when we're converting between Matplot Library and from the OpenCV, we really want the blue, green, red to red, green, blue. That's the conversion you want to use to get to the original picture on there. And then we can also convert from HSV to the lab. Like I said, these conversions, you have to look them up most of the time, but it's important to start recognizing them. So the very fact that you're in here looking at this, and we're talking about blue, green, red versus lab versus the where was it, HSV setup on there. When you're dealing with pictures, they come in all varieties, and so really being able to switch between them is important on here. So let's go ahead and take that particular setup, conversions, and we'll go ahead and clean up our palette. Hopefully that will save us some problems down the road. And we're going to start looking at the color channels. And with this, we'll go ahead and reload the park back up. We'll display that just so you can remember what the original picture looked like. And then for right now, let's go ahead and take a blank screen. and create ourselves a blank 0. It's basically same shape as our park image. D-type, U integer 8. Don't really, usually that's the default anyway, so you don't really need to even put that in there, but it's good to have. And this is an interesting line here that OpenCV allows you to do. CV split image. And this basically just takes the 3 channels in your NumPy image, and you could use the NumPy code and figure it out, I'm sure, and splits it into blue channel, green channel, and red channel. And what we're going to do is we're going to go ahead and, there we go. We're going to do a CV merge, blue, green, and red. And what we're doing is we're merging the blank one as far as blue, the blank green blank, blank blank red. So these are the new channels as we combine them. That's what this merge thing does. This is kind of fun because you could merge, you could take like your cat with just the red whiskers, merge that with something, and then kind of mess with the images as far as like, you know, what sticks out and what sets back on there. You can get pretty creative with the imagery. And then we're just going to go ahead and show blue, green, red. We'll just do all these at once. And you can see here, the same image. Oops, there we go. I'll take it a second to pull it down. And we can now see it's either black or blue, red or blue, or you know, the different colors in here, green or black. Kind of fun. I mean, you really pull out the different colors and see how you can mess with them on there. And then if we go ahead and just do a quick print of these shapes, we go run. You can see here that, as you expected, you have the image shape, which is 427 640 by 3. Well, it's only 640 by 640, so each one of these is just the color of just the one color. That's all we're showing on here. The fact that we used the shape on here is very similar to your NumPy, and these are actually NumPy in the back end. So if you haven't messed with NumPy, real powerful setup on there. You can dive in there and do a lot of stuff in NumPy that comes back right into this over here. And then we'll merge them back in. Shoop. There we go. And we see the original picture. Give it a second to pop to the front. And you see here we merge the colors back. We separated the colors. We merge them back. Same image. And that's what we expect on this because we didn't mess with any of the colors. Let's go ahead and destroy all that. So we have another clear setup. And let's go in and look at some more alterations we can do with blurring and altering the image in different ways. For this, we'll go back to our cat picture. Here's our image, CV, I am red, cat JPEG. And if we run that and view it, there's our cat. I guess we got tired. I guess the guys in the back got tired of the cute puppy running around. And the first thing we'll go ahead and give a shot on here is averaging. These are different ways we can blur the image. So if we average it, it takes the average pixels based on 3 by 3. And if we change this to 30, just for fun, you can see how it really blurs it on there. So this is like a 30 by 30 pixel. Each pixel averages around it. We'll go back to 10. Kind of a little bit of fun stuff you can do on there. And you can see that because I'm doing the average blur, it knows to go to this frame right here. That's why I can so easily jump in here and just make some changes on that. That is a lot of fun when you're messing with videos because you can so easily throw that into your interface setup on there and be able to mess with it. And here's our Gaussian blur. And the Gaussian blur is very similar, but the pixels that are closer are given more weight. And let's just jump this up here to 30. We'll run that. And whoops, it didn't like 30. I guess I jumped too high for it. Let's do 5. There we go. You start to see the blurring on there. And then the one, let's change that and see what that does. Doesn't make a huge difference on this until you start messing with, let's see, weighted, there we go. Run. You start to see it starting to blur more and more depending on how we do the weight and how it kind of blends outward. Gaussian's nice because it adds a little bit more blending to it, where this just blurs it, where the average just blurs it out. Again, those are the kind of things you almost have to play with them a lot to start seeing how they change. And there's also the median blur. Let's go ahead and run that one as it comes up. There we go. And the median works almost identical to the average. It's very similar on there. There are some differences. And you really have to start looking at what is the difference between an average and a median value. Because that's what this is based on. This is based on the median value. If we do a run 10, there we go, there's our median. Oh, it didn't like the 10. I'm not sure why. I must have been too high of a value for it. Run. Oops. Let's try 0.5. There we go. Okay, so, and this has to be an integer for the median blur. And you can see it's similar to the average, but there is a difference in the way the math actually functions in the background. Sometimes it comes out a little different. And there's also a bilateral filter. A lot of these you use to smooth sharp edges. If something looks really sharp, you can smooth it. And this is literally what they're doing when they say smooth something and you're messing around with Photoshop. These are the kind of changes that are happening in the back end. And then we have our bilateral. Let me go and run that. And the bilateral, that is one that's really important to remember because it works like the Gaussian, but it's like a Gaussian filter on top of a Gaussian filter. And one Gaussian filter smooths out like blotches, like if you want someone to have smooth skin, but keeps the sharp edges. And so when you're messing with this and you're doing a lot of work, remembering the bilateral filter is really important if you're doing images, especially if you look at my complexion, I really need it. I should be doing the bilateral on that one. That's the kind of thing that you'd be using to really bring up people's features while smoothing out all that fuzzy noise that shows up on their skin and blemishes. And again, let's go ahead and clear our palette. Run. Another cool feature so we can do bitwise setup on here. And I'm going to create a blank setup just so you can see what it's going on there. Here's our blank box, 400, 400, 400. And it has a rectangle we're going to do from the blank copy, and then we're going to do a circle. The circle is going to be 200, 200 set up on here. So we're just building a circle and a rectangle like we did before. Let me just show you all the numbers on there so you can see what we're doing. Oops, let me maximize it. All right, there we go. Let me, always a question, do you do it before or after the comma? It really depends on what I'm working on and who I'm working with. I do whatever they want. So if it's sometimes it looks nice to have the commas in front, and sometimes afterwards when you're splitting rows, it's purely visual on here. So we're going to go ahead and build ourselves a rectangle and a circle here, and let's just go ahead and display those three things if you don't know which parts are overlapping, so they have to be the same size. And we can see over here, let me just pull this over, we have our rectangle and our circle. And we can do just like we do with any kind of bitwise functionality. And let me pull it, I guess, see if I can pull it over here without losing information on the screen. I always wish the screen was 10 times bigger than it ever is. It doesn't matter how big my screen is. So here we have the bitwise and. This is where the two regions intersect, and it's like you expect. You can see the white circle on the square, but where they're both at, but not where the black part is. So it's the and. They have to have both white on both the square and the circle. And just like that, we can also do the or. And hopefully your mind's already jumped ahead. If we're doing the or, CV bitwise or, rectangle and circle, we have the combination of the two as if you just pasted one over the other in this particular case. And we have nor, or zor as it's called, Control V. So it's not X nor or not Y. And if you look at that, that kind of makes a pretty pattern on there. Not X, not Y. Not X and Y, not. But that's the XOR on there. You can see how the XOR comes up on there. And then, of course, there's just the bitwise not on there. We'll go ahead and run that one, and you can see here where the not set up on that. In this case, it just inverses the circle from black to white. And just like before, let's go ahead and clear our palette. So we start with a clean palette over here. Also keeps my computer running smooth. And we're now into masking. Oh my gosh, I use masking so much. And if you go into any program out there that does any kind of editing, masking comes up. So we want to go ahead and work with our masking on this. And for masking, let's bring the cat back. Sure is a cute cat. In this case, we have a bunch of cute kittens. In fact, a bucket of cute kittens. That's a little scary. And we'll go ahead and create a blank page on here. And this is really interesting. In fact, I'm going to stop here and actually do a draw. And I want you to notice right there, whoops, right there is the 2, the shape. And this is a numpy shape. So what are we talking about with this numpy shape? Well, this numpy shape is zeros or ones. We're really looking for a black and white image. A lot of times when we talk about masks, we're talking about true-false. And that is the same as in numpy, like a true-false mask, just like you have in numpy. And we'll go ahead and create the blank image over here, and it's just like you'd think. It's black. And then we can easily do both the circle and rectangle. And you can see here we did an image shape. Yeah, this isn't too important right now because we're going to create the mask separately in just a second. But you can see where we're creating our image here. There we go. So you can see all the different things in the window. And it's going to create both a circle and a rectangle mask on here. And let's go ahead and do a bitwise. We're going to create the mask out of the bitwise, out of the circle and the square. We'll go ahead and run that so you can see what the mask looks like. And in fact, let's go back to, let's clear up our things. It gets our palette here. We'll just go run that. We're going to play with the, let's see, where are the kittens? Got to have our cute kittens on our display. There we go. There's our kittens come back. Okay, our bucket of kittens. That cracks me up, a bucket of kittens. And here's our mask run. You can see we have an interesting mask showing on there. And then we're gonna take and combine these. Let's see, here we go. And we're going to do a bitwise where we have the image, and masked equals masked. So here's a bitwise setup on here. And let's see what that looks like. And it's just kind of fun. I've created this mask, adding all these things together, and you can see how easily we can actually just kind of zero in there and show just the kitten on the mask. So that's a lot of fun. And you could also reverse this and have an image without the kitten on there and just a black hole where the cat was. So those are both things that can happen on here. Let's go ahead and clear our setup. And masks can get so complicated. You can see we added 2 masks together, a square and a circle, and got a half circle on there. I tell you, I've gotten into so many layers of masks that I can't even track what's going on anymore. So you got to be a little careful with your masks and how you add them together and bring them together. But there's a lot of things you can do with them. You could just as easily swap the green channel in for one. So you have just certain areas where you have like just a circle or it's just green, or maybe the whole background is green and one area is actually full color. So there's a lot of cool things. Or you could mask, take the mask of the of a black and white image and then mask a section of it in color. I've seen that done to make some really cool photographs. Histograms, not something I normally think of when dealing with photographs, but you can do a histogram of the information on there. So let's bring back the kittens because they're just so cute. And let's grayscale it. Bring them back in our grayscaled cats. And then what we can do with this is we can go ahead and do a histogram on the grayscale. boy, we can get so much into histograms because histograms have so much cool data that you can bring in. So a lot of times you can take images of something, you can start looking at the number of pixels, the bins that they fall in, different setups as it pulls in. But you can see we have a grayscale, the histogram of the grayscale here. And just like we do the grayscale, we can also do a histogram of the colored scale too. Boom, there we go. And the same setup, we got our plot figure, our title, we're just doing a histogram, we're just going to throw in the colors blue, green, red. And then we just go through each of the colors and we go ahead and mask them and then plot them on here. Let me just pull that over so you can easily see what's going on. And the same thing with the grayscale. All we did was come in here and just drop the grayscale right on here with the setup. And so we have our figure, our bins, and a number of pixels. And if we plot the red histogram of the colors, you can see here some really kind of fun patterns. And you could analyze these patterns on different things too. I don't know about kittens. I don't really think of kittens with histograms. Wouldn't really do a histogram of a cat. But you could see if this image was like a heartbeat image or something like that, the histogram would really be showing and telling you exactly what's going on. And we'll keep the cute kittens up there and look at thresholding. So we have the threshold, the thresh, and you can do a threshold on here. As far as, there we go. Let me just bring that down so you can see some of the numbers that go into there. And we're going to use the grayscale and just do a simple thresholding view on here. And what we're looking at is the colors that come forward. You can do different thresholds on different colors. And here we're just saying, hey, if it's, because we're dealing with grays, if the certain color is over 150 or 255, you can see we have a nice, or if it's over 150, then it just turns it black, otherwise it's white. And so we create a nice threshold. And you could actually turn around and use this as a mask back on the original picture, and it would bring the cats out and make some interesting pictures on there. But that's a basic threshold on there. There's what they call an inverse threshold. Let's go ahead and take a look and see what that looks like so you have an idea. We'll run this. And this is just, you'll see right here, up here we had threshold gray, very similar. But when we get down to, there we go, thresh binary inverse, there's the key that changes it. So it's still is thresh inverse equals the same call, the same module CV threshold. It's just how do we process it on the end. And if we run that, if you guessed it, inverse means inverse, then you are correct. Oh, give it a second to pop back up here on top. There we go. So very similar to the original thresh inverse, but opposite. And also makes for kind of a cool picture. You could imagine taking either one of these and doing some cool things with them over the original pictures. And then finally there's an adaptive threshold on here. And the adaptive threshold, let me just pull that over here. There we go. It doesn't quite show up on this. We have adaptive threshold Gaussian, so we're going to use the Gaussian. If you remember, Gaussian means that it is slow to bring it up. Slow, that's not even quite the right word. There we go. Okay, I wanted to bring that over so you could see a little bit better. Gaussian means it's adaptive, so that the weight closest to the pixel is very different than as you get further and further away as far as adaptive threshold. And then the adaptive is based more on the difference between the pixels as opposed to the grayness on there. And let's go ahead and when we run it, let's take a look on this and see what that looks like. And we can see just quite the wild imagery. Again, it almost makes it like a black and white etching or something like that. So it kind of a really cool effect. So a lot of these things are designed to help find edges, which is our next section we're going to go over is pulling out the edges and finding the edge detection. And so you can see how complicated it is. It's not an easy thing to find the edges on these pictures. What is the edge? What are the colors? How do you find that? with the histogram we saw in the color scheme, how they did a certain setup, and you might be able to pull that information and use it to find an edge. And so there's a whole thing on edge detection. This is so central to a lot of stuff being worked on now because, well, let's face it, if you're doing like any kind of imagery, you want to know where the edges are so you can draw a box around it, whether you're trying to program it to do a facial recognition, as we'll do in the third section we're going to cover. We're in the first section. But let's go ahead and bring back our park, run that. And we're also going to do a nice gray picture on here. Oops, let me put the wait key back in there. I don't know why it does not. When I run it without giving it that extra 60 milliseconds or whatever to pull it in there, it sure gives me a lot of problems on this machine. And again, it's because I'm doing the Jupyter Notebook. When I put this into a widget or something like that and start using OpenCV or use it as a backend for code, I don't see these kind of problems. It has a lot to do with just using it in Jupyter Notebook. And so let's start with the Sobel, the Sobel X, or the Sobel line detection on here. We're going to put in our grayscale setup on here. There's a lot of different settings on the Sobel X, Sobel Y, and combining them back together. So let's go ahead and take that. And we want to go ahead and show, oops, I forgot to bring my shows over. And I'm doing Sobel first, and the reason I wanted to do Sobel first is because the other one is based on the math behind Sobel that we're going to hit, the second one, which is which happens to be the Laplacian. And so this works on the intensity from one pixel to the next. And it kind of creates a formula for it. And as you can see, as we get into the intensity from one setup to the other, let me bring this down, we can start to see some lines in here. We have from the Y direction and the X direction, and we combine them, and you can see there's an interesting kind of pattern set up in here. Now, for a scene like the park, it's not really pulling it in that good. And like I said, each one of these has a different strength to it. With this one, you might do images a little bit better, close-up shots. But let's look at the Laplacian. Now, the Laplacian is very similar to how it works in the background as the Sobel as far as intensity. But you take that formula for generating the intensity on there. And, whoops. What happened there? Okay. We take the intensity for the Laplacian. There it is. And they use the second derivative. And you can see how it really transforms the edges on this image. And there's a lot of things we could do with this. If you remember from earlier, we talked about taking out noise, blurring. If you use some of those features on here, like the foreground would just disappear with the right blurring technique or the right transposition technique. And it really becomes an art form trying to jump between all these and figure out which one's going to work for your picture and your setup on there. And then you run the histogram to kind of maybe try to find a mathematical thing behind it. It's really a challenge to take the background out or bring the background in and sort those things out. And all these tools are slowly being built, and that's what OpenCV works so good, just to address that. And then we already did the Canny setup. We'll go ahead and run the line detection under Canny. And the Canny literally combines all of the different math functions of our Laplacian and the Sobel setup. And you can see here it does a really good job of drawing lines and putting in areas on there. And again, this is just a starting point. One of the cool things you can do with here is blur it and then get rid of the bumps in the beginning and clean it up and do all kinds of things to create a mask on there. And let's go ahead and clean up our screen or pictures and images. And then we're going to dive into the second stage of this, which is motion detection. Now, we covered a huge amount in all these tools that they have on there, from our canny edge detection to bitwise mapping to masking. That's a lot of stuff to cover. Some of those tools we're going to use in the next setup, or the next one of the next two setups. But we're going to start with motion detection, which is kind of fun. If you have a web camera, or you have, there's all kinds of reasons you could use it. An outdoor webcam. That's what I've always wanted to put one up there because I live up in the mountains. It'd be fun to track the animals going by. But you could also use the motion detector to track somebody coming into an area and then do facial recognition on them. So you can see the motion detector has a lot of cool tools on there. And the fact that we're going to grab from the camera is really helpful also. So let's go ahead and go in here and open up a new, new Python 3. And we'll go ahead and rename this real quick. OpenCV motion detector. There we go. So let's dive into our motion detector. And there's so many. We're going to actually use a lot of the tools we looked at earlier. Let's go ahead and start by importing our OpenCV. And we went ahead and just did OpenCV2. Remember last time I said sometimes we leave it as CV or import CV2 as CV and so on. We're just going to import it as CV2 in this one. And we're going to do date time for tracking. We have this thing called static back. It's we want to be able to reset something to none, and so having it as a global variable here makes sense. And then I'm going to have current motion and motion list. And what it is a current motion is going to have a start time and an end time. That's when it detects a motion going on. And then the motion list is just going to keep tagging those on. So we have a new one and an ending one. Now we're looking at a lot of code here. So the first piece of code that's I really want to draw your attention to is this one right here, cv2.captureVideo. And then the number is, if you had multiple videos in here, you can actually capture the video off the different video cameras. And so we're looking for the main default one that's going to be set up in here. This is actually kind of cool because I always had the idea of having the front-facing camera and a side-facing camera so that you could flip between them and do different things as far as the final edit and that kind of thing. But this is the video. It's looking at this camera. We're just setting this up right now for which camera to look at. Now, when we're dealing with video, we're kind of creating an infinite loop, and so at some point we have to put a break in it, and we'll do that. We'll show you that break here in a sec. In fact, I'm going to skip between the two and skip the code in the middle so you can see the beginning and the end. And so we have an infinite while loop, and we're going to stack images as the video goes and display them. And then when we get to the end of this infinite while loop, we need a way out. In other words, you don't want it just to go on forever until you hit the escape key. You could do that if you want. But we like to actually add something in there. And we'll go ahead and do, here we go, this. We're going to tag on the end here key wait, key Q2, and then just break. Now, this won't work like this unless we're actually displaying a video and that video screen is highlighted. All this says is if we are active in the active video screen when we do the display, when we get to that, break. Now I kind of jumped ahead because we actually have to create a display in the middle, but I wanted to put this all together so you could see it all in one shot here. We have our while loop we're working with. We're going to go ahead and initiate our frame outside of here. It says, hey, this is video. Whenever I do video, this is what we're looking at. Then we're going to read the video. And you'll have two returns on here, check and frame. And the frame is nothing more than the image coming in. That's what that is. And the check is, hey, do we have an image coming in? If you remember from earlier when we played the dog video, it came up with check would come out false when you got to the end of the video. Because this is an indefinite loop, we never do anything with the check. We don't have to worry about that too much. So here's our kind of our wrapper, and we're going to add a couple more things before the end of the break on this. And then we're going to initialize our motion. So up here I initialized the current motion as having nothing in it. So this is a current motion. There's no action going on. We haven't started an action. There's no end to the action. And then when these fill up, we'll put them into the motion list. And so we're going to go ahead and add in our motion equal to 0. So we're initializing the motion in the loop. And it starts out and says there's no motion going on. Now, we're going to go ahead and do some fun stuff here. And this stuff these next lines of code come off of what we just went over. We're going to grayscale it. Very straightforward. So whatever's coming in the camera is going to have a grayscale to it. And then we're going to do a Gaussian blur. This makes it easier to find the changes. We're looking for sharp edges that are moving. That's how we're going to do our motion detector. And if everything's a little blurry, that means the edges are going to stick out when they move because they're kind of blurring it to those edges. And then we're going to go ahead and do a if static back is none, static back equals gray. So we're going to assign our very first value to the first frame that comes in. That's all this is doing on here. And then continue on there. Now, I'm kind of zipping through these steps. I'm going to go back through them in just a second so that you'll make a little bit more understanding as we go. A difference between static background and the current frame, which is a Gaussian blur. So we want the difference between the two frames. And this is just kind of a fun, abstract way of finding, hey, what's the original frame and how much has it changed? And then if there's a change, and you're going to hopefully already have guessed that there's some problems with this piece of code right here. And I've run into this. What if your image is your outdoor cam and the grass is blowing in the wind? Or the lighting changes because the sun rises and sets. So it might work great in a room that has consistent lighting, not so good for a wilderness cam. And you've got to start thinking about these things, and there's ways around it. And if there's a change between the static background and the current frame is greater than 30, it will show white color. So this is kind of fun. Here's our first threshold. We're looking for a threshold between the background and the foreground. So we're starting to find a little bit there on the setup, and then we're going to go ahead and take our threshold frames, the difference from the background and the foreground, and we're going to put that into a thresh frame copy into a find contours, and we're going to use the chain approximate sample for finding the contours. So this is going to find some contours for us. And then what we want to look at is on the contours, so we're counting lines. We're counting how many contours or how many lines are in here. And if there's over 10,000 of these lines that are the difference between the initial frame and the new frame, then the motion's going to be 1. Wow, that's a lot to unpack. So let's go back up here and just go over that real quick, because I did each line as we went in there. First thing we're doing is we're converting it to gray. Why? It's easier to see gray. You can see the differences in movements and things like that in gray a lot better than in color. Next, we're going to blur the gray. This just makes it so it's easier to see the changes going on. We've reset our static back to none, so we initialize our background to gray. So if it's none, then we want the static back to be whatever the gray value is of our first frame. So when I turn the camera on, I'm going to be outside the camera, so you can see the back wall of my office, which is still under construction. Just a wall socket and some weird stuff back there. And that's what I'm going to use for my basic setup, and then when I go back in and move around, or actually I'll just be in it and just try to hold still and move around a little bit. And then we have the difference between the static background and the gray frame. So this is the gray frame coming in versus the static background. And then we take that and we make our threshold, and we basically create a bunch of lines. We find the contours of the threshold, the difference between those. And so that's where we get our nice lines. And if we have enough lines on there, then that means we have a motion equals 1. So that's a lot of fun. Motion equals 1. So the next stage is if we have a motion equals 1, we want to track it. And so we'll go ahead and do that here. Just throw that one in. And it says, hey, if this is a motion equals 1, and our current motion that we're looking at on our 0 slot has nothing in it, and the motion equals 1, then we want to go ahead and stamp the date time in there. So now we're tracking the start of movement. We have the beginning of movement. And we can do a bunch of really fun things. And this next part we're going to use for a bounding rectangle. And this is going to come up in a display we're going to show you in a second. This one, like, tracking the current motion, it's kind of cool. It's either 0 or 1. Really looking at the contour area and figuring out how much value to put this at. We put it at 10,000. That's really part of the OpenCV. Another thing with the OpenCV is we're going to start looking at these contours and we're going to create a rectangle around them. And then CV2 rectangle, we're just going to take the frame and write a rectangle right on top of that frame. Now, if for some reason I stop moving, we want to know about that. So now we've created a rectangle around movements. We've detected our motions. If it didn't detect any motions and there's nothing going on, then we want to go ahead and take and append the end time. So if motion equals 0 and current motion of 0 is not equal to an empty set, then we've had movement going on and the current motion of 1 needs to equal the date time. We'll go ahead and just tag the current motion right on top, and then the current motion is reset to an empty set. So that's all it is we're just creating an array of the motions. And this is just kind of fun right now. We're going to go ahead and do displaying the images. We'll start with image gray frame. And there's our gray on there. And if you remember up here, we drew a box on it. So you're going to start seeing the rectangle on the frame coming in. And then we're going to go and start displaying the gray frame because we converted everything to frame. We want to go ahead and display the differential so you can see what's going on in there and why that looks different. And we want to display both the threshold frame and the color frame. So we're going to do all of these up here. There we go. Okay. So we basically are showing up everything that we put together so that it's going to show up on the screen in little boxes. And then we have our key weight, and I said I need to fill some more stuff in here. Well, if we're in the middle of detection of motion and I hit the Q button, it'd be nice to know that. It'd be nice to tag that on to the end. So we'll go ahead and tag that on to the end here. And if motion equals 1 and current motion of 0 is not equal to an empty set, then current motion of 1 equals date time now, and motionless append the current motion. And then break. That takes us out of the loop completely. And then once we hit the break, we'd like to see what's going on with our motion list. That's what it's all about, is the motion list. So we'll do a quick display on our motion list. I don't want to go past 30 if I do too many start and stops. This is important. Let me go ahead and highlight this right here. We want to release the video and of course destroy all our windows. Okay, and that's just cleaning up. Always good to clean up on there. And these are nothing more. Let me go back up to the top. Here we go. We've already talked a lot about the show. So we're showing the gray frame that we created. We're showing the difference frame that we created. We're showing the threshold frame. And then we're showing the actual color frame that's actually coming in, the frame that's coming in. So, wow, that's a lot to break down. Let's go ahead and run it. Hopefully I didn't miss something when I was coming over here. And we should see it coming through. It's setting up, it's accessing the window. And I have to minimize it because it's behind it, and there we are. Still moving. There we go, move back and forth. And this is kind of cool because you can see as I move back and forth, look at the lines around my face. Especially on the difference frame, you can see where it's putting nice contours on there and setting it up. So I need to go ahead and click on one of these boxes because I moved the mouse on the other one, and then we'll push the Q button. And then we'll bring back up our OpenCV. And you can see here, every time I start and stop, it puts a start time and an end time. And we could have easily put the frame count. You can put just about anything you want on there. And I wanted to go ahead and run this one more time. And then move. Then hold still. And then click on, and then go ahead and hit the Q. And we can see here that instead of having, there we go, boom. That it picked up on a number of different start and stops on here. 1, 2, 3, 4, 5, 6, 7 start and stops. So not bad, you know, a little motion detector. Again, you can see up here where we're capturing the video. We're looping through and finding the video on each one. And then we do all of our fun transformations on creating the grayscale and Gaussian blur. Anything to make it cleaner as far as counting up the threshold lines, to see whether we should make it a motion or not. And then of course we tack the motion on there. We added these little boxes around the contours. That was kind of fun because you could see as I moved how it changed, and there was still like this weird blur in the background. And then of course if we stop, it tags on an end value. And here's all of our displays. And voila, we have a motion detector. Or at least a start to one. You got to mess with it a little bit, and there's obviously you might want to do like every one of the tricks that I use is where you have the static right here, is we revert to the gray static view. This one is if it's you might just revert this to a new frame every so many frames, that kind of thing. So there's a little bit of lots of play in here that you can do with this.
Choose from over 300 in-demand skills and get access to 1,000 plus hours of video content for free. Visit SkillUp by Simplilearn. Click on the link in the description to know more.
That puts us on the demo, which is facial recognition. So let's go ahead and create a new, whoops, where's our new? There we go, new Python 3. And you could see how you can combine the motion detector with the facial recognition detector. So there's a lot of really cool things we can do here. This will be cross OpenCV facial recognition rename. There we go. And so to start with, let's go ahead and import our information on here. We're going to import our CV2 as CV. Again, this is a personal preference. I go back and forth on this. There's a lot of reasons to do it this way if they update it and it's backward compatible. If it's not backward compatible, that's going to cause problems. But that's going to be fine. We have a lot of files going on with this. So as we start messing with the Keras and you want to have access to these files, let us know. We can send you, compress them down and send them. Just put a note into the, send a note over to the Simplilearn team, and they can help you with that. So the first thing we're going to start with is the beginning. We have face detection. We've got a picture of a lady, a group of 5 people image. We have a grayscale the people. Let's go ahead and run. We'll go ahead and move this off to the side again like we've been doing. And run it. There we go. And of course it appears right behind here. Move it off to the side. And give that a second to pull in. As of now, we haven't done anything. As you can see, we just have 2 blank gray screens. Now, because these aren't loaded all the way, if you try to exit out of them, they'll just kind of lock the system up with it when you're connected with the Jupyter notebooks. So we want to go ahead and just destroy all the windows. Let me run that and see that they are gone. And so we have our gray people, gray. Those are gray boxes. That's what the gray people are in there. And we're going to bring in it's called a cascade classifier. And when you look at the cascade classifier, it's going to load the XML har face file right there. This is real important. This is all pre-built. It's looking for edges that are common in faces. That's what this means. When you look at the har face XML, like it's looking at the edges is what it's doing. There is all kinds of really fun stuff they have. Let me just bring this over from the GitHub. This is the OpenCV data har cascades GitHub. And if you go into here, you can see we have eyes, let's see, what is this? Eye tree with eyeglasses, frontal cat face. I guess a lot of people like to identify their cat in photos. Frontal face. So there's a lot of different full body, left eye, right eye. There's a Russian numbers. You can also create your own. So there's a lot of stuff you can do with with a har cascade file. We're going to load that up specific to detecting faces in here. So that's what this part is about. Let's go ahead and apply that. And so you can see we create a faces rectangle, har cascade detect multi-scale. We're going to put our gray into there, where we loaded the picture in there. And then it has some scale factor, many neighbors. There's a lot of different things you can do with this. A lot of times these are pretty much the default. Default works pretty good on a lot of this stuff. And then if you want to dig in deeper into why one would work more, why you need more information, you can go back into the OpenCV. But it's good to know about the har cascade detect multi-scale. And then when we're processing these, the first thing we want to know is we want to print number of faces found. You want to make sure we're not looking at a crowd of 500 people with a ton of different faces on there. And just because, let me go and put this back up here, just because we like to have a view of it, we're going to go ahead and create, square it off so it has just the face in there, create the face rectangle, and then we're going to go ahead and show those images. If you're like me, I like to see what I'm looking at. So let's go ahead and run this. And when we run this, let me go ahead and put this back into half screen. The first thing we do is you notice that number of faces found is 1. That's really what we're looking for, is we want to make sure there's just a single face on here. And you can see here, there's our group of 5 people that says it's actually just one person it found in there. Again, you can see it has a nice image of the person coming up in the different scales and colors. And this is the one we really want to look at, as you can see right here, as it puts a rectangle right around the face. This is really nice because now if you are processing this, you're processing the face, or maybe you're processing the background. It could be used for either one, to pull the background out from the face and blur it, or take the face and center it. So there's a lot of different things you can do here. If you know this is a face, and then you remember from previous, we did edging, you can now draw an edge and find that edging around her head, knowing that the center of the face where her nose is. And then you can blur the background. You'll see that in a lot of newer Zoom and WebEx kind of things, where they blur the background out so people can't see what's behind you when you're on one of those meetings. Now we're going to go ahead and clear this. Again, this thing is set up in Jupyter. There's ways to get around this, but for the most part, it's just good to clean up after yourself because we're extending it out there. So we'll go ahead and destroy all the windows. The next 2 steps, or our final 2 steps, are to go ahead and create a model and train it. So we want to train our model and then actually apply it, use it for something. And we're going to go in here, let me just pull this up. And what we got here is we have our people. We're going to look at pictures of Ben Affleck, Elton John, Jerry Seinfeld, Madonna, Mindy Kaling. These are really easy to pull up images because these are famous actors. I don't recognize any of them. No, I'm kidding. I actually know all of them. And we've got it in here. We've got it set up in one of the files, and we're just going to print the directory. So you can take a quick look at that and see what we're looking at here. this is where it goes to. Let me go ahead and pull that up so you can see what the actual files look like. And you can see here is drilling down into it. Let me just go under Ben Affleck, and you can see it's all these pictures. So this is what we're looking at, is different headshots of Ben Affleck on here. One of the things to notice is that at some point we probably need to resize, because some of these photos are a little bit wider, a little bit taller, and that squishes things and expands them. So a lot of these detections, when we're starting looking at faces, is actually doing its best to do the same thing, compress and expand them into and train it on those different shapes. And we'll go ahead and load our HAR cascade back in here with our face XML that we had before. Being that we're in Jupyter Notebooks, it's probably still listed in there. We want to go ahead and create an empty array of features and an empty array of labels. And we'll show you what that does here in just a minute. This is for tracking our different features in here. So let's go ahead and we have our features and our labels. Let's go ahead and create the data. This is what we're doing here. So we have our person and people. Here's all our people. It's going to go through each one. We have our path, which is our directory. Always good to double check those. Make sure you go in the right direction. We can actually print the path out so that as we go, we know we're looking at the full path. Kind of a troubleshooting thing. Usually at this point, I've already deleted a lot of these things out of here, and you can see that the guys in the back were, when they were doing it, they forget where they put the files or where they're going. They get some kind of weird error, and then you're like, oh yeah, I moved the program over one or something like that. And so we need to go ahead and create a label, people.indexPerson. So we're creating a label for our training scenario. And then for each image in the OS list directory per person, we're going to look at each one of those images. Then we'll take that and we'll create the image path, image array, and here's our reader where we're going to read in the image. Here we are in OpenCV. We go ahead and put that into a grayscale. Faces rectangle. So we look at find the faces on there and create a rectangle around it. That's what this part is. This is all from what we did before. You already saw this programming in here. And so we are basically taking our features and filling it up with the different faces, just the face. We don't want to look at the whole body shot. If you remember from the image, one of them had him leaning against a tree. Some of them are close up, some of them are far away. So we really want to look just at the face. And then we're going to go ahead and append our label. So we have our features. These are each one of our images. And the label then corresponds to each one of our actors. So once we've done that, we have our setup on here. And this is for training purposes. So that's what we really want to do, is we want to create our trainer. Let me come back down here. Create our trainer. we want to train our model. So here we come in down here. We have our features. We're going to print that the training is done. So it's gone through and it's cleaned up all the features, all the setup in here. Then we have our face recognizer. This is the heart of what's going on. The face recognizer is an LBH face recognizer crate. So we're creating a neural network right here. That's the model. And then we take our face recognizer and we train it with our features and our labels. So now we have those different images and we're going to train them on this model here. And then we'll go ahead and just save it. Save features.mpa features and save labels. We're just saving everything. That's all this is down here. And this is interesting because there's so many things we can do down here. Let me just go ahead and run this. And you can see it's going through and it's opening up each of the files. And then it goes through, and the training's really quick. There's not a lot of data in here. There's what, a dozen pictures of each one. This isn't like going through 7 gigabytes of information that takes a day to process in one of these neural networks and trains them, or 2 or 3 days in the case of a project I'm working on. This is just a small amount of data. So it processes rather quickly. Some of the things you can do on here is to increase the data just with these images is you can tilt them. You can take them and tilt it by 15% or 10%. Remember earlier we were looking at all those different commands. That is one of the tricks they use for training a setup and not knowing what angle the person's going to be at. They might only have 12 pictures, and then if you tilt it 15 degrees and 30 degrees in each direction, you've now increased it by a factor of 5. So now you have about 60 pictures that you're doing for each person. So there's a lot of cool things you can do as far as your training setup. We've now created our face recognizer. It's trained, it's ready to go. So the next step is to go ahead and use it, and let's see what that looks like. So let's go ahead and create our face recognition setup. And we're going to reload this. Here's our people again, same as before. Of course, you could just leave it up there since with Jupyter Notebook, it automatically brings a lot of this stuff in. And then we have our features, allow pickles true, so we're loading up our features. Here's our labels. We're going to load our labels. Remember, we saved them up here. And then we go ahead and take our face recognizer and we go ahead and create that. And then we're going to just read the face trained at the YML file we created. So we're just loading back up what we had up here. That's all that is. This is really good to know about because this makes it very portable. This way, if you're using it in one location, obviously you can download it. All your security cameras track your neighbors as they walk down the sidewalk next to your house. And then we're going to just read a image in. And this one we're just going to take right from the Ben Affleck, and we're going to do the first, the Ben Affleck #1 image in there. That's all that is. And we'll go ahead and create our grayscale image, and we'll show that just because it's good to see whatever we're working with. So this is taking our image and converting it to a grayscale. Show person in grayscale. Detect the face in the image. This is nothing new. This is from before. We're doing the Mahar Cascade Detect Multi-Scale setup on there. And then we want to go ahead and create that rectangle around it. Once we create that rectangle around it, then we want to go ahead and do a prediction on it. Let's go ahead and do that. There we go. So here's our faces rectangle, and so we're going to create that with our faces ROI. And then here's the key right here. Here's our faces recognizer predict. It's going to return the label and the confidence on here. And then we're going to go ahead and print that label with the confidence of, and it'll show the confidence. And then we'll go ahead and put some text on there and print it out. It's always nice to see what's going on, and then another rectangle on there. So we're just showing the image again. So as it comes down. This is the key, though, is we want to print out and find out what's the chances of this label being correct. Now, right about now, you should be guessing that it's going to get it correct, and you're going to guess it's going to have a very high confidence rating. And the reason you want to guess that is because we didn't take this image out and switch it around. In other words, this image was part of the training, and so it should have a very high confidence and have it correct because it's already in the model. And let's go ahead and see what happens. We'll go ahead and run this. And you can see the label says, hey, it's Ben Affleck with a 99.53%. And if we bring up the images here, whoops, we go ahead and half screen this again so we can see what we got going here. And for whatever reason, it doesn't want to put them on top. Hold on. I lost my images. There it is. And you can see appeared up on my far left monitor, which I don't know why I went there. That was kind of weird. And then there's the grayscale behind it. And you can see here we were able to identify Ben Affleck with a confidence of 99.53.
Now what is Keras? Before we move on to Keras, let's take a look at TensorFlow. TensorFlow is a software library which was created by Google to implement large-scale machine learning models and to help solve complex numerical problems. TensorFlow is an end-to-end open-source machine learning platform which you can think of as an infrastructure layer for differentiable programming. It combines 4 key abilities. First, efficiently executing low-level tensor operations on CPU and GPU or TPU, computing gradient of arbitrary differential expressions, scaling computation to many devices, and exporting programs to external runtimes such as servers, browsers, or mobiles. But what does Keras have to do with all of this? Keras is nothing more than a high-level deep learning API which is written in Python for neural networks. It has multiple backend neural network computations and it makes implementing neural networks easy. As we know, Keras is a powerful and easy-to-use free open-source Python library for developing and evaluating deep learning models. Keras is a high-level API of TensorFlow 2, an approachable, highly productive interface for solving machine learning problems with a focus on modern deep learning. It provides essential abstractions and building blocks for developing and shipping machine learning solutions with high iteration velocity. Keras empowers engineers and researchers to take full advantage of the scalability and cross-platform capabilities of TensorFlow 2. You can run Keras on TPU or on large classes of GPU, and you can export your Keras model to run in the browser or on a mobile device. Keras provides a Python interface for artificial neural networks. Keras acts as an interface for TensorFlow library, and it helps in implementation of commonly used neural network building block layers such as objectives, activation functions, and optimizers, and a host of tools to make working with images and text data easier to simplify the coding necessary for writing deep neural network code. Basically, it wraps efficient numerical computation libraries such as Theano and TensorFlow and allows you to define and train neural network models in just a few lines of code. In fact, TensorFlow and Keras are so tied together that even in TensorFlow, the official Get Started with TensorFlow tutorial, we use high-level Keras APIs embedded in TensorFlow instead of just using TensorFlow by itself. Some of the important features of Keras include Keras being a high-level interface which uses Theano or TensorFlow for its backend. Keras can run smoothly on both CPU and GPU. It supports almost all the models required for you to create a complete neural network. And it is extremely modular in nature, which means it is incredibly expressive, flexible, and apt for innovative research. So why do we need Keras? First of all, Keras is an API which is designed for human beings, not for machines, which means that it follows best practices for reducing cognitive load. It offers consistent and simple APIs. It minimizes the number of users' action required for common use cases, and it provides clear and actionable feedback upon user error. It is extremely powerful and easy to use, and it also wraps numerical computation libraries such as Theano and TensorFlow and allows you to train and define neural networks in a few lines of code. This makes Keras easy to learn and use. As a Keras user, you can be more productive, allowing you to try more ideas than your competition faster, which in turn will help you win machine learning competition. This ease of use does not come at the cost of reduced flexibility because Keras integrates deeply with low-level TensorFlow functionality. It enables you to develop highly hackable workflows where any piece of functionality can be customized or reused easily. Building a model in Keras. Let's take a look at the basic pipeline which you will have to follow when you are using Keras to define a neural network. First of all, you will have to define a neural network. You will have to select the activation functions and the various mathematical operations that are going to be taking place in your neural network along with the different weightages. Next, you will use Keras to compile your network, which is basically you will use Keras to build it. After this, you will fit to your network. You will fit all the training data that you have to your network and use your testing data to evaluate how the network works. Finally, you will use this network to make predictions. This entire 5-step pipeline can be executed in Keras within 2 to 3 lines of code. Neural networks, which would have taken people days or even weeks to make, can be executed in Keras in a couple of hours. Now, uses of Keras. The first use of Keras is to productize deep models on smartphones. Deep models require a lot of computation power to run, but with the help of Keras, we can literally make deep models a product which can be sold and executed on smartphones. The next use of Keras is in distributed training of deep learning models. Distributed training means that we can split our deep learning model into different parts and train it on systems all across the globe. This makes training of our deep learning model extremely fast. Along with saving time, we are also saving on the computational power of our system, as it is not only our system which has to run such a heavy program. By distributing it across various systems, all the resources required to train a deep learning model go down significantly. Before we can see the differences between these platforms, we first need to know what exactly each of these platforms are. Let's start with TensorFlow. What is TensorFlow? TensorFlow is a low-level software library which is created by Google to help implement machine learning models and to solve complex numerical problems. TensorFlow is nothing but a free and open source software library for machine learning. It can be used across a range of tasks but has a particular focus on training and inference of deep neural networks. TensorFlow is a symbolic math library based on data flow and differential programming. It is used for both research and production at Google. What do you mean by data flow? It basically means that we perform calculations by converting every element into graphical form. The variables of the graph are called tensors, and mathematical operations are called operators. Here, in the computational graph shown, you can see that x, y, and 2 are the variables. They will also be called tensors, and division, multiplication, and addition are the operators. This graph basically shows us the calculation that is going to occur in a machine learning model where x and y are going to be divided and y and 2 are going to be multiplied. The results of these two calculations are then going to be added to give us the final output. I told you that x, y, and 2 are also called tensors. What exactly are tensors? Tensors are multidimensional arrays with a uniform type. All tensors are immutable like Python numbers and strings, which means that you cannot update the contents of a tensor. You can only create a new tensor. Next, let's look at the API Keras. What exactly is Keras? Keras is a high-level deep learning API written in Python for easy implementation and computation of neural networks. Keras is an open-source software library that provides a TensorFlow interface for artificial neural networks. Keras acts as an interface for the TensorFlow library, which means that it runs on top of TensorFlow. Up until version 2.3, Keras supported multiple backends, including TensorFlow, Microsoft Cognitive Toolkit or CNTK, R, Theano, and PlaidML. As of version 2.4, only TensorFlow is supported. Designed to help enable fast experimentation with deep neural networks, it focuses on being user-friendly, modular, and extensible. Keras is a high-level API of TensorFlow, an approachable, highly productive interface for solving machine learning problems with a focus on modern deep learning. It provides essential abstractions and building blocks for developing and shipping machine learning solutions with high iteration velocity. Keras does not perform its own low-level operations such as tensor products and convolution. It relies on backend engines for that. Even though Keras supports multiple backend engines, its primary backend engine is TensorFlow, and its primary supporter is Google, which means that Keras acts as nothing more but a wrapper class around TensorFlow, Theano, CNTK, PlaidML, or MXNet, which are low-level APIs. Next, we will look at PyTorch. What exactly is PyTorch? PyTorch is a low-level API which is developed by Facebook for natural language processing and computer vision. It is a more powerful version of NumPy. It is an open-source machine learning library based on the Torch library used for applications such as computer vision and natural language processing. Primarily developed by Facebook's AI Research Lab, it is free and open source software released under the modified BSD license. Although the Python interface is a more polished and the primary focus of development, PyTorch also has a C++ interface. Python is a widely liked language because it is easy to understand and write. PyTorch emphasizes flexibility and allows deep learning models to be expressed in basic Python. PyTorch is mainly used for natural language processing and for computer vision. Now let's move on to the differences between TensorFlow, Keras, and PyTorch. The first difference that we'll be looking at is called level of API. There are two main types of APIs, a low-level API and a high-level API. API stands for Application Programming Interface. A low-level application programming interface is generally more detailed and allows you to have more detailed control to manipulate functions within them on how to use and implement them, while a high-level API is more generic and simple and provides more functionality with one command statements than a lower-level API. High-level interfaces are comparatively easier to learn and to implement the models using them. They allow you to write code in a shorter amount of time and to be less involved with the details. In this case, TensorFlow is a high and low-level API. Pure TensorFlow is a low-level API, while TensorFlow wrapped in Keras is a high-level API. Keras in itself is a high-level API which uses multiple low-level APIs as a backend and simplifies the operation of these low-level APIs. PyTorch is a low-level API. The next criteria that we'll be looking at is speed. TensorFlow is very fast and is used for high performances. Keras is slower as it works on top of TensorFlow. Not only does it have to wait for TensorFlow to finish implementation, it then starts its own implementation. Meanwhile, PyTorch works at the same speed as TensorFlow, as both of them are both low-level APIs. Now, Keras is a wrapper class for TensorFlow and has added abstraction functionalities on top of TensorFlow, which make it slower than TensorFlow and PyTorch. In computation speed, both TensorFlow and PyTorch are almost equal, and in development speed, Keras is faster as it has built-in functionalities which can significantly reduce your development time. The next difference is on the architecture. TensorFlow is not very easy to use, and even though it provides Keras as a framework that makes it work easier, TensorFlow still has a very complex architecture which is hard to use. Meanwhile, Keras has a simpler architecture and is easier to use. It provides a high level of abstraction which makes implementation of programs in Keras significantly easier. PyTorch, on the other hand, also has a complex architecture and the readability is less when compared to Keras. TensorFlow uses computational graphs which makes it very complex and hard to interpret, but it has amazing computational ability across platforms. PyTorch is a little hard for beginners, but is really good for computer vision and deep learning purposes. Datasets and debugging. TensorFlow works with large datasets due to its high execution speed, and debugging is really hard in TensorFlow due to its complex nature. Meanwhile, Keras only works with very small datasets as its speed of execution is low. Programs do not require frequent debugging in Keras as they are relatively simpler, and PyTorch can manage high-level tasks in higher dimension datasets and is easier to debug than both Keras and TensorFlow. Next, we'll be looking at ease of development. As we said before, TensorFlow works with many hard concepts such as computational graphs and tensors, which means that writing code in TensorFlow is very hard. It is generally used by people when they are doing research work and really need very specific functionalities. Keras, on the other hand, provides a high level of abstraction which makes it very easy to use. It is best for people who are just starting out with Python and machine learning. PyTorch is easier than TensorFlow but is still comparatively hard than Keras. It is not very easy to learn for beginners, but is significantly more powerful than just plain Keras. Ease of deployment. TensorFlow is very easy to deploy as it uses TensorFlow serving. TensorFlow serving is a flexible, high-performance serving system for machine learning models designed for production environments. TensorFlow serving makes it easy to deploy new algorithms and experiments while keeping the same server architecture and APIs. TensorFlow serving provides out-of-the-box integration with TensorFlow models but can be easily extended to serve other types of models and data. In Keras, model deployment can be done with either TensorFlow serving or Flask, which makes it relatively easy but not as easy as it would be with TensorFlow and PyTorch. PyTorch uses PyTorch Mobile, which makes deployment easy, but again, for TensorFlow, deployment is way easier as TensorFlow serving can update your machine learning backend on the fly without the user even realizing. There's a growing need to execute ML models on edge devices to reduce latency, preserve privacy, and enable new interactive use cases. In the past, engineers used to train models separately. They would then go through a multi-step, error-prone, and often complex process to train the models for execution on a mobile device. The mobile runtime was often significantly different from the operations available during training, leading to inconsistent developer and eventually user experience. All of these frictions have been removed by PyTorch Mobile by allowing a seamless process to go from training to deployment by staying entirely within the PyTorch ecosystem. It provides an end-to-end workflow that simplifies the research to production environment for mobile devices. In addition, it paves the way for privacy-preserving features via federated learning techniques. At the end of the day, the question that really matters is which framework should you use, Keras, TensorFlow, or PyTorch? Now, TensorFlow has implemented various levels of abstraction to make implementation of deep learning and neural networks easy. This has also made debugging easier. Keras is simple and easy, but not as fast as TensorFlow. It is more user-friendly than any other deep learning API, however, and is easier to learn for beginners. PyTorch, on the other hand, is the preferred deep learning API for teachers, but it is not as widely used in production as TensorFlow is. It is faster, but it has lower GPU utilization. At the end of the day, the framework that we would suggest that you use is TensorFlow. Why? While PyTorch may have been the preferred deep learning library for researchers, TensorFlow is much more widely used in day-to-day production. PyTorch's ease of use combined with the default eager execution mode for easier debugging predestines it to be used for fast, hacky solutions and smaller scale models. But TensorFlow's extensions for deployment on both servers and mobile devices combined with the lack of Python overhead makes it the preferred option for companies that work with deep learning models. In addition, the TensorFlow board visualization features offers a nice way of showing the inner workings of your model to, say, your customers. Meanwhile, between TensorFlow and Keras, the main difference isn't in performance. TensorFlow is a bit faster due to less overhead, but also the level of control you would like. Keras is much easier to start with than plain TensorFlow, but if you want to do something with Keras that doesn't come out of the box, it will be harder to implement that. TensorFlow, on the other hand, allows you to create any arbitrary computational graph, providing much more flexibility. So if you're doing more research type of work, TensorFlow is the sure route to go due to the flexibility that it provides.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
So we're going to dive right into what is Keras. We'll also go all the way through this into a couple of tutorials because that's where you really learn a lot is when you roll up your sleeves. So when we talk about what is Keras, Keras is a high-level deep learning API written in Python for easy implementation of neural networks. It uses deep learning frameworks such as TensorFlow, PyTorch, etc. as backend to make computation faster. And this is really nice because as a programmer, there is so much stuff out there and it's evolving so fast, it can get confusing. And having some kind of high-level order in there where you can actually view it and easily program these different neural networks is really powerful. It's really powerful to have something out really quick and also be able to start testing your models and seeing where you're going. So Keras works by using complex deep learning frameworks such as TensorFlow, PyTorch, MLPlaid, etc. as a backend for fast computation, while providing a user-friendly and easy-to-learn front end. And you can see here we have the Keras API specifications, and under that you'd have like TF Keras for TensorFlow, Thano Keras, and so on. And then you have your TensorFlow workflow that this is all sitting on top of. And this is, like I said, it organizes everything. The heavy lifting is still done by TensorFlow or whatever underlying package you put in there. And this is really nice because you don't have to dig as deeply into the heavy end stuff while still having a very robust package you can get up and running rather quickly. And it doesn't distract from the processing time because all the heavy lifting is done by packages like TensorFlow. This is the organization on top of it. So the working principle of Keras. The working principle of Keras is Keras uses computational graphs to express and evaluate mathematical expressions. And you can see here we put them in blue. They have the expression expressing complex problems as a combination of simple mathematical operators, where we have like the percentage, or in this case in Python that's usually your remainder, or multiplication. You might have the operator of x to the power of 0.3. And it uses useful for calculating derivatives by using backpropagation. So if we're doing with neural networks, when we send the error back up to figure out how to change it, this makes it really easy to do that without really not banging your head and having to handwrite everything. It's easier to implement distributed computation, and for solving complex problems, specify input and outputs and make sure all nodes are connected. And so this is really nice as you come in through, is that as your layers are going in there, you can get some very complicated different setups nowadays, which we'll look at in just a second. And this just makes it really easy to start spinning this stuff up and trying out the different models. So when we look at Keras models, Keras model, we have a sequential model. Sequential model is a linear stack of layers where the previous layer leads into the next layer. And this, if you've done anything else, even like the sklearn with their neural networks and propagation and any of these setups, this should look familiar. You should have your input layer, it goes into your layer 1, layer 2, and then to the output layer. And it's useful for simple classifier or decoder models. And you can see down here we have the model equals a Keras sequential. And this is the actual code. You can see how easy it is. We have a layer that's dense, your layer 1. As an activation, they're using the ReLU in this particular example. And then you have your name layer 1, layer dense ReLU, name layer 2, and so forth. And they just feed right into each other. So it's really easy just to stack them, as you can see here, and it automatically takes care of everything else for you. And then there's a functional model. And this is really where things are at. This is new. Make sure you update your Keras, or you'll find yourself running this, doing the functional model. You'll run into an error code because this is a fairly new release. And it uses multi-input and multi-output model. The complex model, which forks into 2 or more branches. And you can see here we have our image inputs equals your Keras input shape equals 32 by 32 by 3. You have your dense layers, dense 64 activation ReLU. This should look similar to what you already saw before, but if you look at the graph on the right, it's going to be a lot easier to see what's going on. You have 2 different inputs. And one way you could think of this is maybe one of those is a small image and one of those is a full-sized image. And that feedback goes into, you might feed both of them into one node because it's looking for one thing, and then only into one node for the other one. And so you can start to get kind of an idea that there's a lot of use for this kind of split and this kind of setup. We have multiple information coming in, but the information's very different even though it overlaps. And you don't want it to send it through the same neural network. And they're finding that this trains faster and also has a better result depending on how you split the data up and how you fork the models coming down. And so in here we do have the 2 complex models coming in. We have our image inputs, which is a 32 by 32 by 3, or 3 channels, or 4 if you're having an alpha channel. You have your dense, your layers, dense is 64 activation using the ReLU, very common. X equals dense inputs, X layers dense X64 activation equals ReLU, X outputs equals layers dense 10X, model equals Keras, model inputs equals inputs, outputs equals outputs, name equals minced model. So we add a little name on there. And again, this is this kind of split here. This is setting us up to have the input go into different areas. So if you're already looking at Keras, you probably already have this answer. What are neural networks? But it's always good to get on the same page, and for those people who don't fully understand neural networks, to dive into them a little bit or do a quick overview. Neural networks are deep learning algorithms modeled after the human brain. They use multiple neurons, which are mathematical operations, to break down and solve complex mathematical problems. And so just like the neuron, one neuron fires in and it fires out to all these other neurons, or nodes as we call them, and eventually they all come down to your output layer. And you can see here we have the really standard graph: input layer, a hidden layer, and an output layer. One of the biggest parts of any data processing is your data pre-processing. So we always have to touch base on that. With a neural network, like many of these models, they're kind of, when you first start using them, they're like a black box. You put your data in, you train it, and you test it and see how good it was. And you have to pre-process that data, because bad data in is bad outputs. So in data pre-processing, we will create our own data examples set with Keras. The data consists of a clinical trial conducted on 2,100 patients, ranging from ages 13 to 100, with the patients under 65 and the other half over 65 years of age. We want to find the possibility of a patient experiencing side effects due to their age. And you can think of this in today's world with COVID, what's going to happen on there. And we're going to go ahead and do an example of that in our live hands-on. Like I said, most of this you really need to have hands-on to understand. So let's go ahead and bring up our Anaconda, and I'll open that up and open up a Jupyter notebook for doing the Python code in. Now, if you're not familiar with those, you can use pretty much any of your setups. I just like those for doing demos and showing people, especially shareholders. It really helps because it's a nice visual. So let me go ahead and flip over to our Anaconda. And the Anaconda has a lot of cool tools. They just added Data Lore and IBM Watson Studio Cloud into the Anaconda framework. But we'll be in the Jupyter Lab or Jupyter Notebook. I'm going to do Jupyter Notebook for this because I use the lab for like large projects with multiple pieces because it has multiple tabs. Where the notebook will work fine for what we're doing. And this opens up in our browser window because that's how Jupyter Notebook is set to run. And we'll go under New, create a new Python 3, and it creates an untitled Python. We'll go ahead and give this a title, and we'll just call this Keras tutorial. And let's change that to capital. There we go. We'll go ahead and just rename that. And the first thing we want to go ahead and do is get some pre-processing tools involved. And so we need to go ahead and import some stuff for that, like our NumPy, do some random number generation. I mentioned sklearn or your scikit. If you're installing sklearn, the sklearn stuff, it's scikit you want to look up. That should be a tool of anybody who is doing data science. If you're not familiar with the sklearn toolkit, it's huge, but there's so many things in there that we always go back to. And we want to go ahead and create some train labels and train samples for training our data. And then just a note of what we're actually doing in here. Let me go ahead and change this. This is kind of a fun thing you can do. We can change the code to Markdown. And then Markdown code is nice for doing examples once you've already built this. Our example data, we're going to do experimental. There we go. Experimental drug was tested on 2,100 individuals between 13 to 100 years of age. Half the participants are under 65, and 95% of participants are under 65. Experienced no side effects, while 95% of participants over 65 experienced side effects. So that's kind of where we're starting at. And this is just a real quick example, because we're going to do another one with a little bit more complicated information. And so we want to go ahead and generate our setup. So we want to do for I and range, and we want to go ahead and create, if you look here, we have random integers, train the labels, append. So we're just creating some random data. And then we go ahead and just run that. And so once we've created our random data, and you can certainly ask for a copy of the code from Simplilearn. They'll send you a copy of this, or you can zoom in on the video and see how we went ahead and did our train samples append. And we're just using this. I do this kind of stuff all the time. I was running a thing on that had to do with errors following a bell-shaped curve on a standard distribution error. And so what do? I generate the data on a standard distribution error to see what it looks like and how my code processes it, since that was the baseline I was looking for. In this, we're just doing generating random data for our setup on here. And we could actually go in, print some of the data up. Let's just do this, print. We'll do train samples, and we'll just do the first 5 pieces of data in there to see what that looks like. And you can see the first 5 pieces of data in our train samples is 49, 85, 41, 68, 19. Just random numbers generated in there. That's all that is. And we generated significantly more than that. Let's see, 50 up here, 1,000. Yeah, so there's 1,000 here. 1,000 numbers we generated. And we could also, if we wanted to find that out, we can do a quick print the length of it. And so, or you could do a shape kind of thing, and if you're using NumPy, although the link for this is just fine. And there we go, it's actually 2100, like we said in the demo setup in there. And then we want to go ahead and take our labels. Oh, that was our train labels. We also did samples, didn't we? So we could also print, do the same thing. Oh, labels. And let's change this to labels. And labels. And run that just to double check, and sure enough we have 2100, and they're labeled 10, 10, 10. I guess that's if they have symptoms or not. 1 symptoms, 0 none. And so we want to go ahead and take our train labels and we'll convert it into a NumPy array, and the same thing with our samples. And let's go ahead and run that. And we also shuffle. This is just a neat feature you can do in NumPy right here. Put my drawing thing on, which I didn't have on earlier. I can take the data and I can shuffle it. So we have our, it just randomizes it. That's all that's doing. We've already randomized it, so it's kind of an overkill. It's not really necessary. But if you're doing a larger package where the data is coming in, and a lot of times it's organized somehow, and you want to randomize it just to make sure that the input doesn't follow a certain pattern that might create a bias in your model. And we go ahead and create a scalar. The scalar range, minimum max scalar, feature range 0 to 1. And then we go ahead and scale the scaled train samples. So we're going to go ahead and fit and transform the data so it's nice and scaled. And that is the age. So you can see up here we have 49, 85, 41. We're just moving that so it's going to be between 0 and 1. And so this is true with any of your neural networks. You really want to convert the data to 0 and 1, otherwise you create a bias. So if you have like 100 creates a bias versus the math behind it gets really complicated. If you actually start multiplying stuff, because there's a lot of multiplication and addition going on in there, that higher end value will eventually multiply down, and it will have a huge bias as to how the model fits it, and then it will not fit as well. And then one of the fun things we can do in Jupyter Notebook is that if you have a variable and you're not doing anything with it, and it's the last one on the line, it will automatically print. And we're just going to look at the first 5 samples on here. And so it's going to print the first 5 samples. And you can see, here we go, 0.9195, 0.791. So everything's between 0 and 1. And that just shows us that we scaled it properly and it looks good. It really helps a lot to do these kind of print-ups halfway through. You never know what's going to go on there. I don't know how many times I've gotten down and found out that the data sent to me that I thought was scaled was not. And then I have to go back and track it down and figure it out on there. So let's go ahead and create our artificial neural network. And for doing that, this is where we start diving into TensorFlow and Keras. TensorFlow, if you don't know the history of TensorFlow, it helps to jump into, we'll just use Wikipedia. Be careful, don't quote Wikipedia on these things because you get in trouble. But it's a good place to start. Back in 2011, Google Brain built Disbelief as a proprietary machine learning setup. TensorFlow became the open source for it. So TensorFlow was a Google product, and then it became open sourced, and now it's just become probably one of the de factos when it comes for neural networks as far as where we're at. So when you see the TensorFlow setup, it's got like a huge following. There are some other setups like the Scikit under the sklearn has their own little neural network. But the TensorFlow is the most robust one out there right now. And Keras sitting on top of it makes it a very powerful tool, so we can leverage both the Keras easiness in which we can build a sequential setup on top of TensorFlow. And so in here we're going to go ahead and do our input of TensorFlow, and then we have the rest of this is all Keras here from number 2 down. We're going to import from TensorFlow the Keras connection, and then you have your TensorFlow Keras models, import sequential. It's a specific kind of model. We'll look at that in just a second. If you remember from the files, that means it goes from one layer to the next layer to the next layer. There's no funky splits or anything like that. And then we have from TensorFlow Keras layers, we're going to import our activation and our dense layer. And we have our optimizer Atom. This is a big thing to be aware of, how you optimize your data. When you first do it, Atom's as good as any. Atom is usually, there's a number of optimizer out there. There's a couple of main ones, but Atom is usually assigned to bigger data. It works fine. Usually the lower data does it just fine, but Atom is probably the mostly used. But there are some more out there, and depending on what you're doing with your layers, your different layers might have different activations on them. And then finally down here you'll see our setup where we want to go ahead and use the metrics. And we're going to use the TensorFlow Keras metrics for categorical cross entropy. So we can see how everything performs when we're done. That's all that is. A lot of times you'll see us go back and forth between TensorFlow, and then Scikit has a lot of really good metrics also for measuring these things. Again, it's the end of the at the end of the story. How good does your model do? And we'll go ahead and load all that, and then comes the fun part. I actually like to spend hours messing with these things. And 4 lines of code. You're like, you're going to spend hours on 4 lines of code? No, we don't spend hours on 4 lines of code. That's not what we're talking about when I say spend hours on 4 lines of code. What we have here, and I'm going to explain that in just a second, we have a model. And it's a sequential model. If you remember correctly, we mentioned the sequential up here where it goes from one layer to the next. And our first layer is going to be our input. It's going to be what they call dense, which is usually it's just dense, and then you have your input and your activation. How many units are coming in? We have 16. What's the shape? What's the activation? And this is where it gets interesting, because we have in here ReLU on 2 of these and softmax activation on 1 of these. There are so many different options for what these mean and how they function. How does the ReLU, how does the softmax function? And they do a lot of different things. We're not going to go into the activations in here. That is what really you spend hours doing, is looking at these different activations. And just some of it is just almost like you're playing with it like an artist. You start getting a feel for like a inverse tangent activation, or the tan-H activation. Takes up a huge processing amount, so you don't see it a lot. Yet it comes up with a better solution, especially when you're doing when you're analyzing Word documents and you're tokenizing the words. And so you'll see this shift from one to the other because you're both trying to build a better model. And if you're working on a huge data set, it'll crash the system. It'll just take too long to process. And then you see things like softmax. Softmax generates an interesting setup where a lot of these, when you talk about ReLU, oops, let me do this. ReLU, there we go. ReLU has a setup where if it's less than 0, it's 0, and then it goes up. And then you might have what they call lazy setup, where it has a slight negative to it so that the errors can translate better. Same thing with softmax. It has a slight laziness to it so that errors translate better. All these little details make a huge difference on your model. So one of the really cool things about data science that I like is you build your what they call you build to fail. And it's an interesting design setup. Oops, I forgot the end of my code here. The concept of build to fail is you want the model as a whole to work so you can test your model out. So that you can do you can get to the end and you can do your, let's see, where was it? Overshot down here. You can test out the quality of your setup on there. And see, where did I do my TensorFlow? Oh, here we go. It was right above me. There we go. We start doing your cross entropy and stuff like that. Is you need a full functional set of code so that when you run it, you can then test your model out and say, hey, it's either this model works better than this model and this is why. And then you can start swapping in these models. And so when I say I spend a huge amount of time on pre-processing data, it's probably 80% of your programming time. Well, between those two, it's like 80-20. You'll spend a lot of time on the models. Once you get the model down, once you get the whole code and the flow down set, depending on your data, your models get more and more robust as you start experimenting with different inputs, different data streams, and all kinds of things. And we can do a simple model summary here. Here's our sequential, here's our layer, our output, our parameter. This is one of the nice things about Keras is you can see right here, here's our sequential 1 model. Boom, 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 boom. Everything's set and clear and easy to read. So once we have our model built, the next thing we're going to want to do is we're going to go ahead and train that model. And so the next step is, of course, model training. And when we come in here, this a lot of times is just paired with the model because it's so straightforward. It's nice to print out the model setup so you can have a tracking. But here's our model. The keyword in Keras is compile, optimizer atom, learning rate, another term right there that we're just skipping right over that really becomes the meat of the setup is your learning rate. So whoops, I forgot that I had an arrow, but I'll just underline it. A lot of times the learning rate set to 0.01. Depending on what you're doing, this learning rate can overfit and underfit. So you'd want to look up, I know we have a number of tutorials out on overfitting and underfitting that are really worth reading once you get to that point and understanding. And we have our loss, sparse categorical cross entropy. So this is going to tell Keras how far to go until it stops. And then we're looking for metrics of accuracy. So we'll go ahead and run that. And now that we've compiled our model, we want to go ahead and run it, fit it. So here's our model fit. We have our scaled train samples, our train labels, our validation split. In this case, we're going to use 10% of the data for validation. Batch size, another number you kind of play with. Not a huge difference as far as how it works, but it does affect how long it takes to run, and it can also affect the bias a little bit. Most of the time, though, a batch size is between 10 to 100, depending on just how much data you're processing in there. We want to go ahead and shuffle it. We're going to go through 30 epochs and put a verbose of 2. Let me just go ahead and run this. And you can see right here, here's our epoch, here's our training, here's our loss. Now, if you remember correctly up here, we set the loss. Let's see, where was it? Compiled our data. There we go, loss. So it's looking at the sparse categorical cross entropy. This tells us that as it goes, how much does the error go down? Is the best way to look at that. And you can see here, the lower the number, the better. It just keeps going down. And vice versa, accuracy we want. Let's see, where's my accuracy? Value accuracy at the end. And you can see 0.619, 0.69, 0.74, it's going up. We want the accuracy, would be ideal if it made it all the way to 1. But we also, the loss is more important because it's a balance. You can have 100% accuracy and your model doesn't work because it's overfitted. Again, you want to look up overfitting and underfitting models. And we went ahead and went through 30 epochs. It's always fun to kind of watch your code going. To be honest, I usually, the first time I run it, I'm like, oh, that's cool, I get to see what it does. And after the second time of running it, I'm like, I like to just not see that. And you can repress those, of course, in your code. Repress the warnings in the printing. And so the next step is going to be building a test set and predicting it now. So here we go. We want to go ahead and build our test set. And we have, just like we did our training set, a lot of times you just split your initial set up. But we'll go ahead and do a separate set on here. And this is just what we did above. There's no difference as far as the randomness that we're using to build this set on here. The only difference is that we already did our scalar up here. Well, that doesn't matter because the data is going to be across the same thing. But this should just be transform down here instead of fit transform. Because you don't want to refit your data on your testing data. There we go. And now we're just transforming it because you never want to transform the test data. Easy mistake to make, especially on an example like this where we're not doing, we're randomizing the data anyway, so it doesn't matter too much because we're not expecting something weird. And then we want to go ahead and do our predictions. The whole reason we built the model is we take our model, we predict, and we're going to do, here's our X-scale data, batch size 10, verbose, and now we have our predictions in here, and we could go ahead and do a, we'll print predictions, and then I guess I could just put down predictions in 5 so we can look at the first 5 of the predictions. And what we have here is we have our age and the prediction on this age versus what we think it's going to be, what we think is going to, they're going to have symptoms or not. And the first thing we notice is that's hard to read because we really want a yes/no answer. So we'll go ahead and just round off the predictions using the argmax, the numpy argmax for predictions. So it just goes to a 0, 1, and if you remember, this is a Jupyter Notebook, so I don't have to put the print. I can just put in rounded predictions, and we'll just do the first 5. And you can see here 0, 1, 0, 0, 0. So that's what the predictions are that we have coming out of this. Is no symptoms, symptoms, no symptoms, symptoms, no symptoms. And just as we were talking about at the beginning, we want to go ahead and take a look at this. There we go. Confusion matrices for accuracy check. Most important part when you get down to the end of the story, how accurate is your model before you go and play with the model and see if you can get a better accuracy out of it. And for this, we'll go ahead and use the scikit, the sklearn metrics, scikit being where that comes from. Import confusion matrix, some iteration tools, and of course a nice matplot library. That makes a big difference, so it's always nice to have a nice graph to look at. Picture's worth 1,000 words. And then we'll go ahead and call it CM for confusion matrix, y true equals test labels, y predict rounded predictions. And we'll go ahead and load in our CM. And I'm not going to spend too much time on the plotting, going over the different plotting code. You can spend we have whole tutorials on how to do your different plotting on there. But we do have here is we're going to do a plot confusion matrix. There's our CM, our classes, normalized false, title, confusion matrix. CMAP is going to be in blues. And you can see here we have to the nearest CMAP, titles, all the different pieces, whether you put tick marks or not, the marks, the classes, the color bar. So a lot of different information on here as far as how we're doing the printing of the confusion matrix. You can also just dump the confusion matrix into a Seaborn and real quick get an output. It's worth knowing how to do all this when you're doing a presentation to the shareholders. You don't want to do this on the fly. You want to take the time to make it look really nice, like our guys in the back did. And let's go ahead and do this. Forgot to put together our CM plot labels. We'll go ahead and run that. And then we'll go ahead and call the definition for our mapping. And you can see here, plot confusion matrix. That's the little script we just wrote. And we're going to dump our data into it. So our confusion matrix, our classes, title confusion matrix, and let's just go ahead and run that. And you can see here we have our basic setup. No side effects 195, had side effects 200, no side effects that had side effects. So we predicted the 10 of them who actually had side effects, and that's pretty good. I mean, I don't know about you, but you know, that's 5% error on this, and this is because there's 200 here. That's where I get 5% is divide these both by 2 and you get 5 out of 100. You can do the same kind of math up here. Not as quick on the fly because it's 15 and 195, not an easily rounded number. But you can see here where they have 15 people who predicted to have with the no side effects but had side effects kind of setup on there. And these confusion matrix are so important at the end of the day. This is really where you show whatever you're working on comes up, and you can actually show them, hey, this is how good we are or not, how messed up it is. So this was I spent a lot of time on some of the parts, but you can see here is really simple. We did the random generation of data, but when we actually built the model coming up here, here's our model summary, and we just have the layers on here that we built with our model on this, and then we went ahead and trained it and ran the prediction. Now we can get a lot more complicated. Let me flip back on over here because we're going to do another demo. So that was our basic introduction to it. We talked about the oops, here we go. Okay, so implementing a neural network with Keras. After creating our samples and labels, we need to create our Keras neural network model. We will be working with a sequential model which has 3 layers. And this is what we did. We had our input layer, our hidden layers, and our output layers. And you can see the input layer coming in was the age factor. We had our hidden layer, and then we had the output. Are you going to have symptoms or not? So we're going to go ahead and go with something a little bit more complicated. Training our model is a 2-step process. We first compile our model, and then we train it in our training data set. So we have compiling. Compiling converts the code into a form of understandable by machine. We used the atom in the last example, a gradient descent algorithm, to optimize the model, and then we trained our model, which means it let it learn on training data. And I actually had a little backwards there, but this is what we just did. Is if you remember from our code we just had, oops, let me go back here. Here's our model that we created, summarized. We come down here and we compile it. So it tells it, hey, we're ready to build this model and use it. And then we train it. And this is the part where we go ahead and fit our model and put that information in here, and it goes through the training on there. And of course we scaled the data, which was really important to do. And then you saw we did the creating a confusion matrix with Keras. As we are performing classifications on our data, we need a confusion matrix to check the results. A confusion matrix breaks down the various misclassifications as well as correct classifications to get the accuracy. And so you can see here, this is what we did with the true positive, true negative, false negative. And that is what we went over. Let me just scroll down here. On the end, we printed it out, and you can see we have a nice printout of our confusion matrix with the true positive, false negative, true negative. And so the blue ones We want those to be the biggest numbers because those are the better side. And then we have our false predictions on here as far as this one. So I had no side effects, but we predicted, let's see, no side effects predicting side effects and vice versa.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
Now, saving and loading models with Keras. We're going to dive into a more complicated demo. And you're going to say, oh, well, that was a lot of complication before. Well, if you broke it down, we randomized some data, we created the Keras setup, we compiled it, we trained it, we predicted, and we ran our matrix. So we're going to dive into something a little bit more fun. Is we're going to do a face mask detection with Keras. So we're going to build a Keras model to check if a person is wearing a mask or not in real time. And this might be important if you're at the front of a store. This is something today which is might be very useful as far as some of our, making sure people are safe. And so we're going to look at mask and no mask. And let's start with a little bit on the data. And so in my data I have with a mask. You can see they just have a number of images showing the people in masks. And again, if you want some of this information, contact Simplilearn, and they can send you some of the information as far as people with and without masks, so you can try it on your own. And this is just such a wonderful example of this setup on here. So before I dive into the mask detection, talking about being in the current with COVID and seeing if people are wearing masks, this particular example I had to go ahead and update to a Python 3.8 version. It might run in a 3.7, I'm not sure. I kind of skipped 3.7 and installed 3.8. So I'll be running in a Python 3.8, and then you also want to make sure your TensorFlow is up to date, because they call functional layers. That's where they split. If you remember correctly from back, let's take a look at this. Remember from here, the functional model and a functional layer allows us to feed in the different layers into different nodes into different layers and split them. Very powerful tool. Very popular right now in the edge of where things are with neural networks and creating a better model. So I've upgraded to Python 3.8, and let's go ahead and open that up and go through our next example, which includes multiple layers, programming it to recognize whether someone wears a mask or not, and then saving that model so we can use it in real time. So we're actually almost a full end-to-end development of a product here. Of course, this is a very simplified version, and there'd be a lot more to it. You'd also have to do like recognizing whether it's someone's face or not. All kinds of other things go into this. So let's go ahead and jump into that code, and we'll open up a new Python 3. Oops, Python 3. It's working on it. There we go. And then we want to go ahead and train our mask. We'll just call this train mask. And we want to go ahead and train mask and save it. So it's save mask, train mask detection, not to be confused with masking data. A little bit different. We're actually talking about a physical mask on your face. And then from the Keras standpoint, we got a lot of imports to do here. And I'm not going to dig too deep on the imports. We're just going to go ahead and notice a few of them. So we have in here, oops, let me go Alt-D, there we go. Have something to draw with a little bit here. We have our image processing, and the image processing right here, let me underline that, deals with how do we bring images in, because most images are like a square grid, and then each value in there has 3 values for the 3 different colors. Keras and TensorFlow do a really good job of working with that, so you don't have to do all the heavy listening and figuring out what's going to go on. And we have the mobile net average pooling 2D. This again is how do we deal with the images and pooling them. Dropout's a cool thing worth looking up. If you haven't, as you get more and more into Keras and TensorFlow, it'll auto drop out certain nodes. That way you'll get a better, the nodes just kind of die. They find that they actually create more of a bias than a help. and they also add processing time, so they remove them. And then we have our flatten. That's where you take that huge array with the 3 different colors and you find a way to flatten it so it's just a one-dimensional array instead of a 2 by 2 by 3. Dense input, we did that in the other one, so that should look a little familiar. Oops, there we go. Our input, our model. Again, these are things we had on the last one. Here's our optimizer with our atom. We have some pre-processing on the input that goes along with bringing in the data in. More pre-processing with image to array, loading the image. This stuff is so nice. It looks like a lot of work, so you have to import all these different modules in here. But the truth is it does everything for you. You're not doing a lot of pre-processing. You're letting the software do the pre-processing. And we're going to be working with the setting something to categorical. Again, that's just a conversion from a number to a category. 0, 1 doesn't really mean anything. It's like true, false. Label binarizer, the same thing. We're changing our labels around. And then there's our train, test, split, classification report. Our IM utilities, let me just go ahead and scroll down here a notch for these. This is something a little different going on down here. This is not part of the TensorFlow or the sklearn. This is the scikit setup in TensorFlow above. The path, this is part of OpenCV, and we'll actually have another tutorial going out with the OpenCV. So if you want to know more about OpenCV, you'll get a glance on it in this software, especially the second piece when we reload up the data and hook it up to a video camera. We're going to do that on this round. But this is part of the OpenCV thing, and you'll see CV2 is usually how that's referenced. But the IM utilities has to do with how do you rotate pictures around and stuff like that, and resize them. And then the matplot library for plotting, because it's nice to have a graph, tells us how good we're doing, and then of course our numpy numbers array and just a straight OS access. Wow, so that was a lot of imports. Like I said, I'm not going to spend, I spent a little time going through them, but we didn't want to go too much into them. And then I'm going to create some variables that we need to go ahead and initialize. We have the learning rate, number of epochs to train for, and the batch size. And if you remember correctly, we talked about the learning rate to the -4.00001. A lot of times it's 0.001 or 0.001. Usually it's in that variation depending on what you're doing and how many epochs, and they kind of play with the epochs. The epochs is how many times we're going to go through all the data. And now I have it as 2. The actual setup is for 20, and 20 works great. The reason I have it for 2 is it takes a long time to process. One of the downsides of Jupyter is that Jupyter isolates it to a single kernel. So even though I'm on an 8-core processor with 16 dedicated threads, only one thread is running on this, no matter what. So it doesn't matter. So it takes a lot longer to run, even though TensorFlow really scales up nicely. And the batch size is how many pictures do we load at once and process. Again, those are numbers you have to learn to play with depending on your data and what's coming in. And the last thing we want to go ahead and do is there's a directory with a data set we're going to run. And this just has images of masks and not masks. And if we go in here, you'll see data set. And then you have pictures with masks. They're just images of people with masks on their face. And then we have the opposite. Let me go back up here. Without masks. So it's pretty straightforward. They look kind of askew because they tried to format them into very similar setup on there. So they're mostly squares. You'll see some that are slightly different on here. And that's kind of an important thing to do on a lot of these data sets. Get them as close as you can to each other. And we actually will run in this processing of images up here, and the cross layers and importing and dealing with images. It does such a wonderful job of converting these that a lot of it we don't have to do a whole lot with. So you have a couple things going on there. And so we're now going to be, this is now loading the images, and let me see. And we'll go ahead and create data and labels. Here's our here's the features going in, which is going to be our pictures, and our labels going out. And then for categories in our list directory, and if you remember, I just flashed that at you. I had
face mask or no face mask. Those are the two options. And we're just going to load into that. We're going to append the image itself and the labels. So we're just going to create a huge array. And you can see right now this could be an issue if you had more data. At some point, thankfully I have a 32 gig hard drive or RAM. Even that, you could do with a lot less of that. Probably under 16 or even 8 gigs would easily load all this stuff. And there's a conversion going on in here. I told you about how we are going to convert the size of the image, so it resizes all the images. And that way our data is all identical the way it comes in. And you can see here with our labels, we have without mask, without mask, without mask. The other one would be with mask. Those are the two that we have going in there. And then we need to change it to the one-hot encoding. And this is going to take our, up here we had, what was it, labels and data. We want the labels to be categorical. So we're going to take labels and change it to categorical, and our labels then equal a categorical list. We'll run that. And again, if we do labels and we just do the last or the first 10, let's do the last 10 just because minus 10 to the end. There we go. Just so we can see what the other side looks like. We now have 1. That means they have a mask. 1, 0, 1, 0, so on. 1 being they have a mask and 0 no mask. And if we did this in reverse, I just realized that this might not make sense if you've never done this before. Let me run this. 0, 1. So 0 is, do they have a mask on? 0. Do they not have a mask on? 1. So this is the same as what we saw up here without mask. 1 equals, the second value is without mask. So with mask, without mask. And that's just with any of your data processing, we can't really, if you have a 0, 1 output, it causes issues as far as training and setting it up. So we always want to use a one-hot encoder if the values are not actual linear value or regression values. They're not actual numbers if they represent a thing. And so now we need to go ahead and do our train X, test X, train Y, test Y, train, split, test data. And we'll go ahead and make sure it's going to be random, and we'll take 20% of it for testing and the rest for setting it up as far as training their model. This is something that's become so cool. When they're training these sets, they realize we can augment the data. What does augment mean? Well, if I rotate the data around and I zoom in, I zoom out, I rotate it, shear it a little bit, flip it horizontally, fill mode, as I do all these different things to the data, it is able to, it's kind of like increasing the number of samples I have. So if I have all these perfect samples, what happens when we only have part of the face, or the face is tilted sideways, or all those little shifts cause a problem if you're doing just a standard set of data. So we're going to create an augment in our image data generator, which is going to rotate, zoom, and do all kinds of cool things. And this is worth looking up, this image data generator and all the different features it has. A lot of times, the first time through my models, I'll leave that out because I want to make sure there's a thing what we call build to fail, which is just cool to know. You build the whole process, and then you start adding these different things in so that you can better train your model. And so we go and run this, and then we're going to load. And then we need to go ahead, and you probably would have gotten an error if you hadn't put this piece in right here. I haven't run it myself because the guys in the back did this. We take our base model, and one of the things we want to do is we want to do a MobileNet v2. And this is a big thing right here. Include the top equals false. A lot of data comes in with a label on the top row. So we want to make sure that that is not the case. And then the construction of the head of the model that will be placed on the top of the base model. We want to go ahead and set that up. And you'll see a warning here. I'm kind of ignoring the warning because it has to do with the size of the pictures and the weights for input shape. So it'll switch things to defaults, just saying, hey, we're going to auto shape some of this stuff for you. You should be aware of that. with this kind of imagery, we're already augmenting it by moving it around and flipping it and doing all kinds of things to it. So that's not a bad thing in this. But in other data, it might be if you're working in a different domain. And so we're going to go back here, and we have our base model. We're going to do our head model equals our base model output. And what we got here is we have an average pooling 2D, pool size 7.7 head model. Head model flatten, so we're flattening the data. So this is all processing and flattening the images. And the pooling has to do with some of the ways it can process some of the data. We'll look at that a little bit when we get down to the lower level and just processing it. And then we have our dense. We've already talked a little bit about a dense, just what you think about. And then the head model has a dropout of 0.5. What we can do with a dropout? The dropout says that we're going to drop out a certain amount of nodes while training. So when you actually use the model, it will use all the nodes. But this drops certain ones out, and it helps stop biases from forming. So it's really a cool feature in here. They discovered this a while back. We have another dense mode, and this time we're using softmax activation. Lots of different activation options here. Softmax is a real popular one for a lot of things, and so is the ReLU. And we could do a whole talk on activation formulas and what their different uses are and how they work. When you first start out, you'll use mostly the ReLU and the softmax for a lot of them, just because they're some of the basic setups. It's a good place to start. And then we have our model equals model, inputs equals base model dot input, outputs equals head model. So again, we're still building our model here. We'll go ahead and run that. And then we're going to loop over all the layers in the base model and freeze them so they will not be updated during the first training process. So for layer and base model layers, layers.trainable equals false. A lot of times when you go through your data, you want to kind of jump in partway through. I'm not sure why in the back they did this for this particular example, but I do this a lot when I'm working with series and specifically in stock data. I want it to iterate through the first set of 30 data before it does anything. I would have to look deeper to see why they froze it on this particular one. And then we're going to compile our model. So compiling the model, atom, init, layer, decay, initial learning rate over epochs. And we go ahead and compile. Our loss is going to be the binary cross entropy, which will have that print out. Optimizer for opt, metrics is accuracy. Same thing we had before. Not a huge jump as far as the previous code. And then we go ahead and we've gone through all this, and now we need to go ahead and fit our model. So train the head of the network, print info training head, run. Now I skipped a little time because you'll see the run time here is at 80 seconds per epoch. It takes a couple minutes for it to get through on a single kernel. One of the things I want you to notice on here while it's finishing the processing is that we have up here our augment going on. So anytime the train X and train Y go in, there's some randomness going on there and is jiggling it around what's going into our setup. Of course, we're batch sizing it, so it's going through whatever we set for the batch values, how many we process at a time. And then we have the steps per epoch, the train X, the batch size, validation data. Here's our test X and test Y, where we're sending that in. And this, again, it's validation. One of the important things to know about validation is when both our training data and our test data have about the same accuracy, that's when you want to stop. That means that our model isn't biased. If you have a higher accuracy on your testing, you've trained it, and your accuracy is higher on your actual test data, then something in there is probably has a bias and it's overfitted. So that's what this is really about right here with the validation data and validation steps. So it looks like let me go ahead and see if it's done processing. Looks like we've gone ahead and gone through 2 epochs. Again, you could run this through about 20 with this amount of data, and it would give you a nice refined model at the end. We're going to stop at 2 because I really don't want to sit around all afternoon, and I'm running this on a single thread. So now that we've done this, we're going to need to evaluate our model and see how good it is, and to do that we need to go ahead and make our predictions. These are our predictions on our test X to see what it thinks are going to be. So now it's going to be evaluating the network, and then we'll go ahead and go down here, and we will need to turn the indexing, because remember it's either 0 or 1. It's 0, 1, 0, 1. So you have 2 outputs: not wearing a mask, not wearing a mask. And so we need to go ahead and take that argument at the end and change those predictions to a 0 or 1 coming out. And then to finish that off, we want to go ahead and let me just put this right in here and do it all in one shot. We want to show a nicely formatted classification report so we can see what that looks like on here. And there we have it. We have our precision. It's 97% with a mask. There's our F1 score, support without a mask, 97%. So that's pretty high setup on there. You know, 3 people are going to sneak into this door who are without a mask and it thinks they have a mask, and there's going to be 3 people with a mask that's going to flag the person at the front to go, oh hey, look at this person, he might not have a mask. That's I guess if it's a setup in front of a store. So there you have it. And of course, one of the other cool things about this is if someone's walking into the store and you take multiple pictures of them, you know, this is just it would be a way of flagging, and then you can take that average of those pictures and make sure they match or don't match if you're on the back end. And this is an important step because this is just cool. I love doing this stuff. So we're going to go ahead and take our model and we're going to save it. So model save mask detector.model. We're going to give it a name. We're going to save the format. In this case, we're going to use the H5 format. And so this model we just programmed has just been saved. So now I can load it up into, say, another program. What's cool about this is, let's say I want to have somebody work on the other part of the program. Well, I just saved the model. They upload the model. Now they can use it for whatever. And then if I get more information and we start working with that, at some point I might want to update this model. Make a better model. And this is true of so many things, where I take this model and maybe I'm running a prediction on making money for a company, and as my model gets better, I want to keep updating it, and then it's real easy just to push that out to the actual end user. And here we have a nice graph. You can see the training loss and accuracy as we go through the epochs. We only did the, only shows just the one epoch coming in here, but you can see right here as the value loss, train accuracy, and value accuracy start switching and they start converging. And you'll hear converging. This is the convergence they're talking about when they say I know when I work in the scikit with sklearn neural networks, this is what they're talking about, a convergence, is our loss and our accuracy come together, and also up here, and this is why I'd run it more than just 2 epochs. As you can see, they still haven't converged all the way. So that would be a cue for me to keep going. But what we want to do is we want to go ahead and create a new Python 3 program. And we just did our train mask. So now we're going to go ahead and import that and use it and show you in a live action. Get a view of both myself in the afternoon along with my background of an office, which is in the middle still of reconstruction for another month. And we'll call this mask detector. And then we're going to grab a bunch of a few items coming in. We have our MobileNet v2 import preprocessing input, so we're still going to need that. We still have our TensorFlow image to array. We have our load model. That's where most of the stuff's going on. This is our CV2 or OpenCV. Again, I'm not going to dig too deep into that. We're going to flash a little OpenCV code at you, and we actually have a tutorial on that coming out. Our NumPy array, our IM utilities, which is part of the OpenCV or CV2 setup. And then we have, of course, time and just our operating system. So those are the things we're going to go ahead and set up on here. And then we're going to create, this takes just a moment. Our module here, which is going to do all the heavy lifting. So we're going to detect and predict a mask. We have frame, FaceNet, MaskNet. These are going to be generated by our OpenCV. We have our frame coming in, and then we want to go ahead and create a mask around the face. It's going to try to detect the face and then set that up so we know what we're going to be processing through our model. And then there's a frame shape here. This is just our height versus width. That's all HW stands for. They've called it blob, which is a CV2 DNN blob form image frame. So this is reformatting this frame that's going to be coming in literally from my camera. And we'll show you that in a minute, that little piece of code that shoots that in here. And we're going to pass the blob through the network and obtain the face detections. So FaceNet.setImport blob, detections FaceNet forward, print detections shape. So this is what's going on here. This is that model we just created. We're going to send that in there, and I'll show you in a second where that is, but it's going to be under FaceNet. And then we go ahead and initialize our list of faces, their corresponding locations, and the list of predictions from our face mask network. We're going to loop over the detections, and this is a little bit more work than you think as far as looking for different faces. What happens if you have a crowd of faces? So we're looping through the detections and the shapes going through here. And probability associated with the detection. Here's our confidence of detections. We're going to filter out weak detection by ensuring the confidence is greater than the minimum confidence. So we've set it, remember, 0 to 1. So 0.5 would be our minimal confidence, probably is pretty good. And then we're going to put in compute bounding boxes for the object. If I'm zipping through this, it's because we're going to do an OpenCV, and I really want to stick to just the Keras part. And so I'm just kind of jumping through all this code. You can get a copy of this code from Simplilearn and take it apart, or look for the OpenCV coming out. And we'll create a box. The box sets it around the image. Ensure the bounding boxes fall within the dimensions of the frame. So we create a box around what we hope is going to be the face. Extract the face, ROI, convert it from BGR to RGB channel. Again, this is an OpenCV issue. Not really an issue, but it has to do with the order. I don't know how many times I've forgotten to check the order colors when working with OpenCV. Causes all kinds of fun things when red becomes blue and blue becomes red. And we're going to go ahead and resize it, process it, frame it, face frame, setup. Again, the face, the CV2 color, we're going to convert it. We're going to resize it, image to array, pre-process the input, pin the face, locate face, start X, start Y, and X. Boy, that was just a huge amount, and I skipped over a ton of it, but the bottom line is we're building a box around the face, and that box, because the OpenCV does a decent job of finding the face, and that box is going to go in there and see, hey, does this person have a mask on it? And so that's what all this is doing on here. And then finally we get down to this where it says predictions equals masknet.predict faces batch size 32. So these different images where we're guessing where the face is are then going to go through and generate an array of faces, if you will. And we're going to look through and say, does this face have a mask on it? And that's what's going right here is our prediction. That's the big thing that we're working for. And then we return the locations and the predictions. The location just tells where on the picture it is, and then the prediction tells us what it is. Is it a mask or is it not a mask? Alright, so we've loaded that all up. So we're going to load our serialized face detector model from disk. And we have the path that it was saved in. Obviously, you're going to put it in a different path depending on where you have it or however you want to do it and how you saved it on the last one where we trained it. And then we have our weights path. And so finally our FaceNet, here it is, equals cv2.dnn.readnet prototext path weights path. And we're going to load that up on here. So let me go ahead and run that. And then we also need to, I'll just put it right down here. I always hate separating these things in there. And then we're going to load the actual mask detector model from disk. This is the model that we saved. So let's go ahead and run that on there also. So this is pulling in all the different pieces we need for our model. And then the next part is we're going to open up our video. And this is just kind of fun because it's all part of the OpenCV video setup. And let me just put this all in as one. There we go. So we're going to go ahead and open up our video. We're going to start it and we're going to run it until we're done. And this is where we get some real kind of live action stuff, which is fun. This is what I like working about with images and videos, is that when you start working with images and videos, it's all right there in front of you. It's visual and you can see what's going on. So we're going to start our video streaming. This is grabbing our video stream source 0 start. That means it's grabbing my main camera I have hooked up. And then starting video, you're going to print it out. Here's our video source equals 0 start. Loop over the frames from the video stream. Oops, a little redundancy there. Let me close. I'll just leave it. That's how they had it in the code. So while true, we're going to grab the frame from the threaded video stream and resize it to have the maximum width of 400 pixels. So here's our frame. We're going to read it from our visual stream. We're going to resize it. And then we have returning. Remember, we returned from our procedure the location and the prediction. So detect and predict mask. We're sending it the frame. We're sending it the face net and the mask net. So we're sending all the different pieces that say this is what's going through on here. And then it returns our location and predictions, and then for our box and predictions in the location and predictions, and the box is again, this is an OpenCV set that says, hey, this is a box coming in from the location, because you have the two different points on there. And then we're going to unpack the box and predictions, and we're going to go ahead and do mask without a mask equals prediction. We're going to create our label, no mask. We're going to create color if the label equals mask L00225. And this is going to make a lot more sense when I hit the run button here. But we have the probability of the label. We're going to display the label and bounding box rectangle in the output frame. And then we're going to go ahead and show the output from the frame, CV2 IM show frame. And then the key equals CV2 wait key 1. We're just going to wait till the next one comes through from our feed. And we're going to do this until we hit the stop button pretty much. So are you ready for this? Let's see if it works. We've distributed our model. We've loaded it up into our distributed code here. We've got it hooked into our camera. And we're going to go ahead and run it. And there it goes. It's going to be running, and we can see the data coming down here, and we're waiting for the pop-up. And there I am in my office with my funky headset on. And you can see in the background my unfinished wall, and it says up here, no mask. Oh no, I don't have a mask on. I wonder if I cover my mouth, what would happen? You can see my no mask goes down a little bit. I wish I'd brought a mask into my office. It's up at the house. But you can see here that this says, there's a 95, 98% chance that I don't have a mask on. And it's true, I don't have a mask on right now. And this could be distributed. This is actually an excellent little piece of script that you could start, you install somewhere on a video feed on a security camera or something, and then you'd have this really neat setup saying, hey, do you have a mask on when you enter a store or public transportation or whatever it is where they're required to wear a mask. Let me go ahead and stop that. Now, if you want a copy of this code, definitely give us a holler. We will be going into OpenCV in another one, so I skipped a lot of the OpenCV code in here as far as going into detail. Really focusing on the Keras, saving the model, uploading the model, and then processing a streaming video through it so you can see that the model works. We actually have this working model that hooks into the video camera, which is just pretty cool and a lot of fun. So I told you we're going to dive in and really roll up our sleeve and do a lot of coding today. We did the basic demo up above for just pulling in a cross, and then we went into a cross model where we pulled in data to see whether someone was wearing a mask or not. So very useful in today's world as far as a fully running application.
Sequential models in Keras. So what is Keras? Keras is a high-level Python deep learning API, which is used for easy implementation of neural networks. It has multiple low-level backends like TensorFlow, Thano, PyTorch, etc., which are used for fast computation. So you could think of this as Keras being almost its own little programming language, and then it sits on neural networks. In this case, the ones listed were TensorFlow, Thano, and PyTorch, which can all integrate with the Keras model. This makes it very diverse and also makes it very easy to use and switch around with different things. Keras is very user-friendly as far as neural network software goes as a high-level API. Computational graphs. So computational graphs are really the heart and soul of neural networks. We talk about a computational graph. They are a visual representation of expressing and evaluating mathematical equations. The nodes and data flow in a graph correspond to mathematical operations and variables. You'll hear a lot, some of the terms you might hear are node and edge, the edge being the data flow in this case. It could also represent an actual value. They have, I think in Spark they have a graph X, which works just on computing edges. There's all kinds of stuff that has evolved from computational graphs. We're focusing just on Keras and on neural networks. So we're not going to go into great detail on everything a computational graph does. It is a core component of a neural network, is what's important to know on this. So Keras offers a Python user-friendly front end while maintaining a strong computation power by using a low-level API like TensorFlow, PyTorch, etc., which use computational graphs as a backend. So one, this allows for abstraction of complex problems while specifying control flow. If you've ever looked at some of the backend or the original versions of TensorFlow, it's really a nightmare. You have all these different settings you have to put in there and create. It's a lot of back-end programming. This is like the old computers when you had to tell it how to dispose of a variable and how to properly reallocate the memory for use. All that is covered nowadays in our higher level programming. Well, this is the same thing with Keras, is it covers a lot of this stuff and does things for you that you could spend hours on just trying to figure out. It's useful for calculating derivatives by using backpropagation. We're definitely not going to teach a class on derivatives in this little video, but understanding a derivative is the rate of change. So if you have a particular function you're using in your neural network, a lot of them is just simple y equals mx plus b, your Euclidean geometry where you just have a simple slope times the intercept. And they get very complicated. They have the inverse tangent function for activation as opposed to just a linear Euclidean model. And you can think about this as you have your data coming in and you have to alter it somehow. Well, you alter it going down to get an answer, you end up with an error, and that error goes back up, and you have to have that back propagation with the derivative. You want to know how it changed so that you can figure out how to adjust it for the error. A lot of that's hidden, so you don't even have to worry about it with Keras. And in today's Keras, it'll even, if you create your own formula for computing an answer, it will automatically compute the derivative for you in a lot of cases. It's easier to implement distributed computation. So Keras is a really nice way to package it and get it off on different computers and share it. And it allows parallelism, which means that two operations can run simultaneously. So as we start developing these backends, it can do all kinds of cool things and utilize multiple cores, GPUs on a computer to get that parallel processing up. What are neural networks? Well, like I said, there are already, we talked about in computational edges, you have a node and you have a connection, or your edge. So neural networks are algorithms fashioned after the human brain, which contain multiple layers. Each layer contains a node called a neuron, which performs a mathematical operation. They break down complex problems into simple operations. So one, an input layer takes in our data and pre-processes it. when we talk about pre-processing, when you're dealing with neural networks, you usually have to pre-process your data so that it's between -1 and 1 or 0 and 1 into some kind of value that's usable. That occurs before it gets to the neural network. In fact, 80% of data science is usually in prepping that data and getting it ready for your different models. 2, you have hidden layer performs a nonlinear transformation of input. Now it can do a linear transformation. It can use just a basic Euclidean geometry, and you could think of a node adding all the different connections coming in. So each connection would have a weight, and then it would add to that weight plus an intercept in the node itself. So you can actually use Euclidean geometry. But a lot of these get really complicated. They have all these different formulas, and they're really cool to look at. But when you start looking at them, look at how they work. You really don't need to know the high math behind it to figure them out and figure out what they're doing, which is really cool. That means a lot of people can use this without having to go get a PhD in mathematics. Number 3, the output layer takes the results from hidden layer, transforms them, and gives a final output. So sequential models. So what makes this a sequential model? Sequential models are linear stacks of layers where one layer leads to the next. It is simple and easy to implement, and you just have to make sure that the previous layer is the input to the next layer. So you have used for plain stack of layers where each layer has one input and one output tensor, and this is what TensorFlow is named after. Is each one of these layers is like a tensor. Each node is a tensor, and then the layer is also considered a tensor of values. And it's used for simple classifier, declassifier models. It's also used for regression models too. So it's not just about this is something, this is a teapot, this is a cat, this is a dog. It's also used for generating the actual values. You know, this is worth $10, that's worth $30. The weather's going to be 90 degrees out or whatever it is. So you can use it for both classifier and declassifier models. And one more note when we talk about sequential models. The term sequential is used a lot, and it's used in different areas and different notations when you're in data science. So when we talk about time series, we'll talk about sequential. That is something very different. Sequential in this case means it goes from the input to layer 1 to layer 2 to the output. So it's very directional. It's important to note this because if you have a sequential model, can you have a non-sequential model? And the answer is yes. If you master the basics of a sequential model, you can just as easily have another model that shares layers. You can have another model where you have an input coming in and it splits. And then you have one set that's doing one set of nodes. Maybe they're doing a yes-no kind of node, where it's either putting out a 0 or a 1, a classifier. And the other one might be regression. It's just processing numbers, and then you recombine them for the output. That's what they call the cross API. So there's a lot of different availabilities in here, and all kinds of cool things you can do as far as encoding and decoding and all kinds of things. And you can share layers and things like that. We're just focusing on the basic cross model with the sequential model. So let's dive into the meat of the matter. Let's do a demo on here. Today's demo, in this demo, we'll be performing flower classification using sequential model in Keras. And we'll use our model to classify between 5 different types of flowers. Now, for this demo, and you can do this demo on whatever platform you want, or whatever user interface for developing Python, I'm actually using Anaconda, and then I'm using Jupyter notebooks to develop in. And if you're not familiar with this, you can go under Environment. Once you've created environment, you can come in here to open a terminal window. And if you don't have the different modules in here, you can do your Conda install, or whatever module it is. Just happened that this particular setup didn't have a Seaborn in it, which I already installed. So here's our Anaconda, and then I'm going to go back and start up my Jupyter notebook, where I already created a new Python project, Python 3. I'm in Python 3.8 on this particular one. Sequential model for flowers. So lots of fun there. So we're going to jump right into this. the first thing is to make sure you have all your modules installed. So if you don't have NumPy, Pandas, Matplotlib, and Seaborn, and the Keras, and sklearn, or scikit, it's not actually sklearn, you'll need to go ahead and install all of those. Now, having done this for years and having switched environments and doing different things, I get all my imports done, and then we just run it, and if we get an error, we know we have to go back and install something. Right off the bat, though, we have NumPy, Pandas, Matplotlib, Seaborn. These are built on top of each other. Pandas, the data frame, and built on top of NumPy, the data array. And then we bring in our sklearn, or scikit. This is the scikit setup, scikit. Even though you use sklearn to bring it in, it's a scikit. And then our Keras. We have our pre-processing the images, image data generator, our model. This is our basic model, our sequential model. And then we bring in from Keras layers, import dents, optimizers. These optimizers, a lot of them already come in. These are your different optimizers, and it's almost, a lot of this is so automatic now. Atom is a lot of times the default because you're dealing with a large data. And then we get our SGD, which is smaller data, does better on smaller pieces of data. And I'm not going to go into all of these different optimizers. We didn't even use these in the actual demo. You just have to be aware that they are different optimizers. And the more you dig into these models, you'll hit a point where you do need to play with these a little bit. But for the most part, leave it at the default when you're first starting out. And we're doing just the sequential. You'll see here layers dense. And then if we come down a little bit more, when they put this together and they're running the dense layers, you'll also see they have dropout, they have flatten, they have activation, they have the convolutional layer 2D, max pooling 2D, batch normalization. What are all these layers? And when we get to the model, we're going to talk about them. A lot of times when you're just starting, you can just import Keras.layers, and then you have your dropout, your flatten, your convolutional neural network 2D. And we'll cover what these do in the actual example when we get down there. What I want you to take from here, though, is you need to run your imports and load your different aspects of this. And, of course, your TensorFlow TF, because this is all built on TensorFlow. And then finally, import random as RN, just for random generation. And then we get down here, we have our CV2. That is your open image, or your open CV, they call it, for processing images. That's what the CV2 is. We have our TQDM. The TQDM is for is a progress bar. Just a fancy way of adding, when you're running a process, you can view the bar going across in the Jupyter setup. Not really necessary, but it's kind of fun to have. We want to be able to shuffle some files. Again, these are all different things. PIL is another image processor. It goes with the CV2. A lot of times you'll see both of those. And so we run those. We've got to bring them all in. And the next thing is to set up our directories. And so when we come into the directories, there's an important thing to note on here, other than we're looking at a lot of flowers, which is fun. Is we get down here, we have our directory archive flowers. That just happens to be where the different files for different flowers are put in. We're denoting an X and a Z. And the X is the date of the image, and the Z is the tag for it. What kind of flower is this? And the image size is really important because we have to resize everything. If you have a neural network, and if you remember from our neural networks, let me flip back to that slide. When we look at this slide, we have two input nodes here. With an image, you have an input node, depending on how you set it up, for each pixel. And that pixel has 3 different color schemes usually in it, sometimes 4. So if you have a picture that's 150 by 150, you multiply 150 times 150 times 3. That's how many nodes, input layers, coming in. I mean, so this is a massive input. A lot of times you think, oh yeah, it's just a small amount of data or something like that. No, it's a full image coming in. Then you have your hidden layers. A lot of times they match what the image size is coming in. So each one of those is also just as big. And then we get down to just a single output. So that's kind of a thing to note in here, what's going on behind the scenes. And of course, each one of these layers has a lot of processes and stuff going on. And then we have our different directories on here. Let me go ahead and run that. So I'm just setting the directories. That's all this is. Archive flowers, daisy, sunflower, tulip, dandelion, rose. Just our different directories that we're going to be looking at. And then we want to go ahead and we need to assign labels. Remember, we defined X and Z. So we're just going to create a definition here. And the first thing is return flower type. Okay, it just returns it what kind of flower it is, I guess, assign the label to it. But we're going to go ahead and make our train data. And when you look at this, there's a couple things to take away from here. The first one is we're just appending right onto our NumPy array the image. We're going to let NumPy handle all that different aspects as far as 150 by 150 by 3. We just dump it right into the NumPy, which makes it really easy. We don't have to do anything funky on the processing, and we want to leave it like that. And I'm going to talk about that in a minute. And then, of course, we have to have the string, append the label on there. And I want you to notice right here, we're going to read the image in, and then we're going to size it. And this is important because we're just changing this to 150 by 150. We're resizing the image so it's uniform. Every image comes in identical to the other ones. This is something that's so important is when you're resizing or reformatting your data, you really have to be aware of what's going on. With images, it's not a big deal because with an image, you just resize it so it looks squishy or spread out or stretched. The neural network picks up on that and it doesn't really change how it processes it. So let's go ahead and run that. And now we've got our definition set up on there. And then we want to go ahead and make our training data. So make the train data daisy flower, daisy directory, print length of X. So here we go. Let's go ahead and run that. And we're just loading up the flower daisy. So this is going all in there, and it's setting, it's adding it in to our setup on there, to our X and Z setup. And we see we have 769. And then, of course, you can see this nice bar here. This is the bar going across is that little added code in there that just makes it really cool for doing demos. Not necessarily when you're building your own model or something like that, but if you're going to display this to other people, adding that little, what was it called? TQDM. I can never remember that, but the TQDM module in there is really nice. And we'll go ahead and do sunflowers. And of course, you could have just created an array of these. But this has an interesting problem that's going to come up, and I want to show you something. It doesn't matter how good the people in the back are or how good you are at programming. Errors are going to come up, and you got to figure out how to handle them. And so when we get all the way down to the, where is it? Dandelion. Here's our dandelion directory we're going to build. Jupyter has some cool things it does, which makes this really easy to deal with. But at the same time, you would want to go back in there depending on how many times you rerun this, how many times you pull this. So when you're finding errors going in here, there's a couple things you can do. And we're just going to, oh, it wasn't, no, there it is. There's our error. I knew there was an error. This processed 1,062 out of 1,065. Now, I can do a couple things. One, I could go back into our definition. And I can just put in here try, and so if it has a bad conversion, because this is where the error is coming from, just skip it. That's one way to do it. When you're doing a lot of work in data science and you look at something like this where you're losing 3 points of data at the end, you just say, okay, I lost 3 points. Who cares? Or you can go in there and try to delete it. It really doesn't matter for this particular demo. And so we're just going to leave that error right alone and skip over because it's already added all the other files in there. And this is a wonderful thing about Jupyter Notebook is that I can just continue on there and the X and Z, which we're creating, is still running, and we'll just go right into the next flower row. So all these flowers are in there. That's just a cool thing about Jupyter Notebook. And then we can go ahead and just take a quick look and see what we're dealing with. And this is, of course, really, when you're dealing with other people and showing them stuff, this is just kind of fun where we can display it on the plot library here. And we're just going to go through and let's see, what do we got here? Looks like we're going to do like 5 of each of them, I think. Is that how they set this up? Plot library 5 by 2. Okay, oh, I see how they did it. Okay, so 2 each. So we have 5 by 2 set up on our axes, and we're just going to go in and look at a couple of these flowers. It's always a good thing to look at some of your data. No matter what you're doing, we've reformatted this to 150 by 150. You can see how it really blurs this one up here on the tulip. That is at resize to 150 by 150. And these are what's actually going in. These are all 150 by 150 images. You can check the dimensions on the side. And you can see just a quick sampling of the flowers we're actually going to process on here. And again, like I said at the beginning, most of your work in data science is reprocessing this different information. So we need to go ahead and take our labels and run a label encoder on there. And then we're just going to, LE is a label encoder. One of the things we imported, and then we always use the fit to categorical, y comma 5, x, here's our array, x. So if you look at this, here's our fit. We're going to transform z. That's our z array we created. And then we have y, which equals that. And then we go ahead and do to categorical. We want 5 different categories. And then we create our x, NP array of x. X equals x over 255. So what's going on here, there's 2 different transformations. One, we've turned our categories into 0, 1, 2, 3, 4, 5 as the output. And we have taken our x array, and remember the x array is 3 values of your different colors. This is so important to understand. When we do this across a NumPy array, this takes every one of those 3 colors. So we have 150 by 150 pixels. Out of those 150 by 150 pixels, they each have 3 color arrays. And those color arrays range from 0 to 250. So when we take the x equals x over 255, range from 0 to 255, this converts all those pixels to a number between 0 and 1. And you really want to do that when you're working with neural networks. Now, if you do a linear regression model, it doesn't affect it as much, and so you don't have to do that conversion if you're doing straight numbers. But when you're running neural networks, if you don't do this, you're going to create a huge bias. And that means they'll do really good on predicting 1 or 2 things, and they'll just totally die on a lot of other predictions. So now we have our x and y values. X being the data in, y being our known output. And with any good setup, we want to divide this data into our training. So we have x train. We have our x test. This is the data we're not going to program the model with. And of course your y train corresponds to your x train, and your y test corresponds to your x test, the outputs. And this is, when we do the train test split, this was from the scikit, sklearn. We imported train test split. And we're just going to go ahead and do the test size at about 1/4 of the data, 0.25. And of course random's always good. This is such a good tool. I mean, certainly you can do your own division. You could just take the first 0.25 of the data or whatever, do the length of the data. Not real hard to do, but this is randomized so that if you're running this test a few times, you can kind of get an idea whether it's going to work or not. Sometimes what I will do is I'll just split the data into 3 parts, and then I'll test it on 2, with one being or I'll train it on 2 of those parts, with one being the test, and I rotate it. So I come up with 3 different answers, which is a good way of finding out just how good your model is. But for setting up, let's stick with the xtrain, xtest, and the sklearn package. And then we're going to go ahead and do a random seed. Now, a lot of times the Keras actually does this automatically, but we're going to go ahead and set it up on here. And you can see we did an NP random seed from 42, and we get a nice RN number. And then we do TF random, we set the seed. So you can set your randomness at the beginning of your TensorFlow. And that's what the tf.random.set is. So that's a lot of prep. All this prep, and then we finally get to the exciting part. This is where you probably spend, once you have the data prepped and you have your pipeline going and you have everything set up on there, this is the part that's exciting, is building these models. And so we look at this model. One, we're going to designate it as sequential. They have the API, which is the Keras TensorFlow API versus sequential. Sequential means we're going one layer to the next. So we're not going to split the layer and bring it back together. It looks almost the same with the exception of bringing it back together. So it's not a huge step to go from this to an API. And the first thing we're going to look at is our convolutional neural network in 2D. So what's going on here? There's a lot of stuff that's going on here. The default for, well, let's start with the beginning. What is a convolutional 2D network? Well, a convolutional 2D network creates a number of small windows, and those small windows float over the picture, and each one of them is their own neural network, and it's basically becomes like a categorization. And then it looks at that and it says, oh, if we add these numbers up a certain way, we can find out whether this is the right flower based on this little window floating around, which looks at different things. And we have filters 32. So this is actually creating 32 windows, is what that's doing. And the kernel size is 5 by 5. So we're looking at a 5 by 5 square. Remember, it's 150 by 150. So this narrows it down to a 5 by 5. It's a 2D, so it has your X, Y coordinates. And when we look at this 5 by 5, remember each one of these is actually looking at 5 by 5 by 3. So we're actually looking at 15 by 15 different pixels. And padding is just, usually I just ignore that. Activation by default is ReLU. We went ahead and put the ReLU in there. There's a lot of different activations. ReLU is for your smaller, remember I mentioned atom, when you have a lot of data use an atom kind of activation, or use an atom processing. We're using the ReLU here. It kind of gives you a yes or no, but it doesn't give you a full yes or no. It has a 0 and then it kind of shoots off at an angle. Very common. It's the most common one. And then of course here's our input shape, 150 by 150 by 3 pixels. And then we have to pool it. So whenever you have a convolutional 2D layer, we have to bring this back together and pool this into a neural network. And then we're going to go ahead and repeat this. So we're going to add another network here. One of the cool things, if you look at this, is that as it comes in, it just kind of automatically assumes you're going down to the next layer. And so we have another convolutional neural network, 2D. Here's our max pooling again. We're going to do that again, max pooling. And we're just going to filter on down. Now, one of the things they did on this one is they changed the kernel size. They changed the number of filters. And so each one of these steps kind of looks at the data a little bit differently. And that's kind of cool because then you get a little added filtering on there. This is where you start playing with the model. You might be looking at a convolutional neural network, which is great for image classifications. When we get down to here, one of the things we see is flatten. So we just flatten it. Remember, this is 150 by 150 by 3. Well, and actually the pool size changes, so it's actually smaller than that. Flatten just puts that into a 1D array. So instead of being, a tensor of this really complexity with the pixels and everything, it's just flat. And then the dense is just another activation on there. By default, it is probably ReLU as far as this activation. And then, oh yeah, here we go. In sequential, they actually added the activation as ReLU. So this just, because this is sequential, this activation is attached to the dense. And there's a lot of different activations, but ReLU is the most common one. And then we also see a softmax. Softmax is similar, but it has its own kind of variation. And one of the cool things, you know what, let me bring this up because if you don't know about these activations, this doesn't make sense. And I just did a quick Google search on images of TensorFlow activations. I should probably look at which website this is. But this is the output of the values. So as your x, as it adds in all those weighted x values going into the node, it's going to activate it a certain way. And that's a sigmoid activation. And you can see it goes between 0 and 1 and has a nice curve there. This also shows the derivatives. And if we come down, the 7 popular activation functions, nonlinear activations, there's a lot of different options on this. Let me see if I can find the... Oops, let me see if I can find the specific to ReLU. So this is a leaky ReLU. And you can see instead of it just being 0 and then a value between going up, it has a little leaky there. Otherwise, your ReLU loses some nodes. They just become inactive. But you can see there's a lot of different options here. Here's a good one right here with the ReLU. You can see the ReLU function on the upper left here. And then the leaky ReLU over here on the right, which is very commonly used also. One of the things I use with processing language is the exponential one or the tangent h, the hyperbolic tangent, because they have that nice funky curve that comes in that has a whole different meaning and captures word use better. Again, these are very specific to domain, and you can spend a lot of time playing with different models. For our basic model, we'll stick to the ReLU and the softmax on here, and we'll go ahead and run and build this model. So now that we've had fun playing with all these different models that we can add in there, we need to go ahead and have a batch size on here, 128, epochs 10. This means that we're going to send 128 rows of data or flowers at a time to be processed. And the epochs 10, that's how many times we're going to loop through all the data. And then there's all kinds of stuff you can do. Again, this is now built into a lot of Keras models already by default. So there's different ways to reduce the values and verbose. Verbose equals 1 means that we're going to show what's going on. Value, monitor what we're monitoring. We'll see that as we actually train the model. This is what's going to come out of there. If you set the verbose equal to 0, you don't have to watch it train the model, although it is kind of nice to actually know what's going on sometimes. And since we're still working on bringing the data in, here's our batch size, here's our epochs, we need to go ahead and create a data generator. This is our image data generator, and it has all the different settings in here. Almost all of these are defaults. So if you're looking at this going, oh my gosh, this is confusing, most of the time you can actually just ignore most of this. Vertical flip, so you can randomly flip pictures, you can randomly horizontally flip them. You can shift the picture around. This kind of helps, gives you multiple data off of them. Zooming, rotation, there's all kinds of different things you can do with images. Most of these we're just going to leave as false. We don't really need to do all that setup because we already have a huge amount of data. If you're short data, you can start flipping like a horizontal picture and it will generate, it's like doubling your data almost. So the upside is you double your data. The downside is that if you already have a bias in your data, you already have 5,000 sunflowers and only 2 roses, that's a huge bias. It's also going to double that bias. That is the downside of that. And so we have our model compile, and this you're going to see on all the Keras. We're going to take this model here, we're going to take all this information as far as how we want it to go, and we're going to compile it. This actually builds the model, and so we're going to run that. And I want you to notice learning rate, very important. This is the default 001. You really don't. This is how slowly it adjusts to find the right answer. And the more data you have, you might actually make this a smaller number. If you have a very small sample of data, you might go even larger than that. And then we're going to look at the loss, categorical cross entropy, most commonly used. And this is how much it improves. The model's improving is what this number means. Or yeah, that's important on there. And then the accuracy. We want to know just how good our model is on the accuracy. And then one of the cool things to do is if you're in a group of people who are studying the model, if you're in shareholders, you don't want to do this, is you can run the model summary. I do this by default, and you can see the different layers that you built into this model. Just a quick summary on there. So we went ahead and we're going to go ahead and create a, we'll call it history, but we want to do a model fit generator. And so what this history is doing is this is tracking what's going on while it fits the model. Now there's a lot of new setups in here where they just use fit and then you put the generator in here. We're going to leave it like this, even though the new default is a little different on that. Doesn't really matter, it does the same thing, and we'll go ahead and just run that. And you can see while it's running right here, we're going through the epochs. We have 1 of 10, now we're going through 6 to 25. Here's our loss. We're printing that out so you can see how it's improving, and our accuracy. The accuracy gets better and better. And this is 6 out of 25. This is going to take a couple minutes to process because we are training 150 by 150 by 3 pixels across 6 layers or 8 layers, whatever it was. That is a huge amount of processing, so this will take a few minutes to process. This is when we talk about the hardware and the problems that come up in data science and why it's only now just exploding being able to do neural networks. This is why. This process takes a long time. Now you should have seen it jump on the screen here because I did pause the recorder to let this go ahead and run all the way through its epochs. Let's go ahead and take a look and see what these epochs are. And if you set the verbose to 0 instead of 1, it won't show what's going on in the behind the scenes as it's training it. So when we look at this epoch, 10 epochs, we went through all the data 10 times. If I remember correctly, there's roughly a gig of data there, so that's a lot of data. The first thing you're going to notice is the 270 seconds. That's how much each of those epochs took to run. And so if you divide 60 in there, you roughly get about 5 minutes worth of each epoch. So if I have 10 epochs, that's 50 minutes, almost an hour of runtime. That's a big deal when we talk about processing. On this particular computer, I actually have, 8 cores with 16 dedicated threads. So it runs like a 16-core computer. It alternates the threads going in. And it still takes it 5 minutes for each one of these epochs. So you start to see that if you have a lot of data, this is going to be a problem if you have a number of models. You want to find out how good the models are doing and what model to use. And so each of those models could take all night to run. In fact, I have a model I'm running now that takes about a day and a half to test each model. It takes 4 days to do the whole data. So what I do is I actually take a small piece of the data, test it out to find out, get an idea of how the different setups are going to do, and then I increase that size of the data and then increase it again, and I can just take that curve and kind of say, okay, if the data is doing this, then I need to add in more dense layers or whatever. So you can do a small chunks of data and then figure out what it costs to do a large set of data and what kind of model you want. The loss, as we see here, continues to go down. This is the error. This is how much error is in there. It really isn't a user-friendly number other than the more it trends down, the better. And so if you continue to see the loss going down, eventually you'll get to the point where it stops going down and it goes up and down and kind of wavers a little bit. At that point, you know you've run too many epochs. You're starting to get a bias in there, and it's not going to give you a good model fit. The accuracy just turns this into something that we can use. And so the accuracy is what percentage of guesses, in this case it's categorical, so this is the percentage of guesses are correct. Value loss is similar, it's a minus a value loss. And then you have the value accuracy, and you'll see the value accuracy is pretty similar to the accuracy, just rounds it off basically. And so a lot of times you come down here and you go, okay, we're doing 0.5, 0.6, 0.7. And that is 70% accuracy, or in this case, 68.59% accuracy. And that's a very usable number, and it's very important to have. If you're identifying flowers, that's probably good enough if you can get within a close distance and knowing what flower you're identifying. If you're trying to figure out whether someone's going to die from a heart attack or not, you might want to rethink it a little bit or rekey how you're building your model. So if I'm working with a group of clients, shareholders in a company or something like that, you don't really want to show them this. You don't want to show them, hey, this is what's going on with the accuracy. These are just numbers. And so we want to go ahead and put the finishing touches, just like when you are building a house and you put in the frame and the trim on the house. It's nice to have a nice view of what's going on. And so we'll go ahead and do a pie plot, and we'll just plot the history of the loss, the history of the value loss over here, epochs, train, and test. And so we're just going to compute these. This is really important. And what I want you to notice right here is when we get to about 5 epochs, a little more than 5, 6 epochs, you see a crossover here, and it starts crossing as far as the value loss. And what's going on here is you have the loss in your actual model and your actual data, and you have the value loss where it's testing it against the test data. The data wasn't used to program your model, wasn't used to train your model on. And so when we see this crossing over, this is where the bias is coming in. This is becoming overfitted. And so when you put these two together, right around 5 and 6, you start to see how it does this switch over here. And that's really where you need to stop, right around 5, 6. It's always hard to guess because at this point, the model's kind of a black box. But you know that right around here, if you're saving your model after each run, you want to use the one that's right around 5 epochs because that's the one that's going to have the least amount of bias. So this is really important as far as guessing what's going on with your model and its accuracy and when to stop. It also is, I don't show people this mess up here. I show somebody this kind of model and I say, this is where the training and the testing comes in on this model. It just makes it easier to see and people can understand what's going on. So that completes our demo, and you can see we did what we were set out to do. We took our flowers and we were able to classify them within about 68, 70% accuracy, whether it's going to be a dahlia, sunflower, cherry blossom, rose. A lot of other things you can do with your output as far as different tables to see where the errors are coming from and what problems are coming up. Image classification using Keras. And we're going to take a look at image classification using Keras and the basic setup, and we'll actually look at 2 different demos on here. What's in it for you today? What is image classification? Intel image classification data, creating neural networks with Keras, and the VGG16 model. What is image classification? The process of image classification refers to assigning classes to an entire image. Images can be classified based on different categories like whether it is a nighttime or daytime shot, what the image represents, etc. And you can see here we have mountains looking for mountains. We'll actually be doing some pictures of scenery and stuff like that. In deep learning, we perform image classification by using neural networks to extract features from images and classifies them based on these features. And you can see here where it says like what computer sees, and it says, oh yeah, we see mostly forest, maybe a little bit of mountains because of the way the image is. And this is really where one of the areas that neural networks really shines. If you try to run this stuff through more like a linear regression model, you'll still get results, but the results kind of miss a lot of things as the neural networks get better and better at what they do with different tools we have out there. So Intel image classification data. The data being used is the Intel image classification data set, which consists of images of 6 types of land areas. And so we have forest, building, glaciers, and mountains, sea, and street. And you can see here is a couple of the images out of there as a setup in the Intel image classification data that they use. And then we're going to go into creating a neural networks with Keras. The convolutional neural network that we are creating from scratch looks as shown below. You'll see here we have our input layer. They have it listed max pooling. So you have as you're coming in with the input layer, and the input layer is actually before this, but the first layer that it's going to go into is going to be a convolutional neural network. Then you have a max pooling that pulls the convolutional neural network's returns. In this case, they have 2 of those. That is very standard with convolutional neural networks. One of the ones that I was looking at earlier that was standard being used by one of the larger companies, I can't remember which one, for doing a large amount of identification, had 2 convolutional neural networks, each with their max pooling, and then about 17 dense layers after it. We're not going to do that heavy duty of a code, but we'll get you headed in the right direction. And that gives you an idea of what you're actually going to be looking at when you look at the flattened part and then the dense. We're talking like 17 dense layers afterwards. I find that a lot of the stuff I've been working on, I end up maxing it out right around 9 dense layers. It really depends on what you have going in and what you're working with. And the VGG16 model. VGG16 is a pre-trained CNN model which is used for image classification. It is trained on a large, varied data set and fine-tuned to fit image classification data sets with ease. And you can see down here we have the input coming in, the convolutional neural network 1-to-1, 1-to-2, and then pooling. And then we do 2-to-1, 2-to-2 convolutional neural network, then pooling, 3-to-2, and you can see there's just this huge layering of convolutional neural networks. And in this case, they have 5 such layers going in, and then you have 3 dense going out, or more. Now, when they took this setup, this actually won an award back in 2019 for this particular setup. And it does really good, except that, again, we only show the 3 dense layers here. And as you find out, depending on your data going in and what you have set up, that really isn't enough on one of these setups. And I'm going to show you why we restricted it, because it does take up a lot of processing power in some of these things. So let's go ahead and roll up our sleeves, and we're going to look at both the setups. We're going to start with the first classification, and then we'll go into the VGG16 and show you how that's set up. Now I'm going to be using Anaconda, and let me flip over to my Anaconda so you can see what that looks like. Now I'm running in the Anaconda here. You'll see that I've set up a main Python 3.8. I always put that in there because this is where I'm doing like most of my kind of playing around. This is done in Python version 3.8. We're not going to dig too much into versions. At this point you should already have Keras installed on there. Usually Keras takes a number of extra steps. And then our usual setup is the NumPy, the pandas, your scikit, which is going to be the sklearn, your seaborn, and I'll show you those in just a minute. And then I'm just going to be in the Jupyter lab where I've created a new notebook in here. And let's flip on over there to my blank notebook. Now, there's a couple cool things to note in here is that, one, I use the Anaconda Jupyter notebook setup because it keeps everything separate, except for Keras. Keras is actually running separately in the back. I believe it's a C program. What's nice about that is that it utilizes the multiprocessors on the computer, and I'll mention that just in a little bit when we actually get down to running the code. And when we look in here, the couple things to note is here's our, oops, I thought I grabbed the other drawing thing. But here's our NumPy and our pandas right here and our operating system. This is our scikit. You always import it as sklearn for the classification report. We're going to be using, well, usually import like seaborn brings in all of your pyplot library also. Kind of nice to throw that in there. I can't remember if we're actually using seaborn, if they just, the people in the back just threw that together. And then we have the sklearn shuffle for shuffling data. Here's our matplot library that the seaborn is pretty much built on. CV2, if you're not familiar with that, that is our image module for importing the image. And then of course we have our TensorFlow down here, which is what we're really working with. And then the last thing is just for visual effect while we're running this. If you're doing a demo and you're working with the partners or the shareholders, This TQDM is really kind of cool. It's an extensible progress bar for Python. And I'll show you that too. Remember, data science is not, I mean, most of this code, when I'm looking through this code, I'm not going to show half of this stuff to the shareholders or anybody I'm working with. They don't really care about pandas and all that. We do, because we want to understand how it works. So we need to go ahead and import those different setup on there. And then the next thing is we're going to go ahead and set up our classes. Now we remember if we had mountain, street, glacier, building, sea, and forest, those were the different images that we have coming in. And we're going to go ahead and just do class name labels, and we're going to kind of match that class name of I for I, class name equals the class names. So our labels are going to match the names up here. And then we have the number of classes, and print the class names and the labels. And we'll go ahead and set the image size. This is important that we resize everything, because if you remember with neural networks, they take one size data coming in. And so when you're working with images, you really want to make sure they're all resized to the same setup. It might squish them, it might stretch them. That generally does not cause a problem in these. And some of the other tricks you can do with, if you need more data, and this is one that's used regularly, we're not going to do it in here, is you can also take these images and not only resize them, but you can tilt them one way or the other, crop parts of them, so that they process slightly differently, and it'll actually increase your accuracy of some of these predictions. And so you can see here we have mountain equals 0, that's what this class name label is, street equals 1, glacier equals 2, buildings equals 3, sea 4, forest equals 5. Now, we did this as an enumerator, so each one is 0 through 5. A lot of times we do this instead as 0, 1, 0, 1, 0, 1, so you have 5 outputs, and each one's a 0 or a 1 coming out. So the next thing we really want to do is we want to go ahead and load the data up, and just put a label in there, loading data. just so you know what we're doing, I'm going to put in the loading data down here. Make sure it's well labeled. And we'll create a definition for this. And this is all part of your pre-processing. At this point, you could replace this with all kinds of different things depending on what you're working on. And once you download, you can go download this data set, send a note to the Simplilearn team here in YouTube, and they'll be happy to direct you in the right direction. And make sure you get this path here, so you have the right, wherever you saved it. A lot of times I'll just abbreviate the path or put it as a sub thing and just get rid of the directory. But again, double check your paths. We're going to separate this into a segment for training and a segment for testing. And that's actually how it is in the folder. And let me just show you what that looks like. So when I have my lengthy path here where I keep all my programming Simplilearn, this particular setup we're working on, image classification and image classification. Clearly you probably wouldn't have that lengthy of a list. And when we go in here, you'll see sequence train, sequence test. They've already split this up. This is what we're going to train the data in. And again, you can see buildings, forest, glacier, mountain, sea, street. And if we double click, let's go under forest. You can see all these different forest images. And there's a lot of variety here. I mean, we have wintertime, we have summertime. So it's kind of interesting. You know, here's like a fallen tree versus a road going down the middle. That's really hard to train. And if you look at the buildings, a lot of these buildings, you're looking up a skyscraper, we're looking down the setup. Here's some trees with one, and I want to highlight this one. It has trees in it. Let me just open that up so you can see it a little closer. The reason I want to highlight this is I want you to think about this. We have trees growing. Is this the city or a forest? So this kind of imagery makes it really hard for a classifier. And if you start looking at these, you'll see a lot of these images do have trees and other things in the foreground, weird angles. Really a hard thing for a computer to sort out and figure out whether it's going to be a forest or a city. And so in our loading of data, one, we have to have the path, the directory. We're going to come in here, we have our images and our labels. So we're going to load the images in one section, the labels in another. And if you look through here, it just goes through the different folders. In fact, let me do this. There we go. As we look at this, we're just going to loop through the 6 different folders that have the different landscapes, and then we're going to go through and pull each file out and each label. So we set the label, we set the folder for file and list. Here's our image path, join the paths. This is all kind of general stuff, so I'm kind of skipping through it really quick. And here's our image setup. If you remember, we're talking about the images. We have our CV2 reader, so it reads the image in. It's going to go ahead and take the image and convert it to from blue, green, red to red, green, blue. This is a CV2 thing. Almost all the time it imports it, and instead of importing it as a standard that's used just about everywhere, it imports it with the BGR versus RGB. RGB is pretty much a standard in here. You have to remember that was CV2. And then we're going to go ahead and resize it. This is the important part right here. We've decided what the size is, and we want to make sure all the images have the same size on them. And then we just take our images and we're just going to append the image, append the label, and then the images is going to turn into a numpy array. This just makes it easier to process and manipulate. And then the labels is also a numpy array. And then we just return the output, append images and labels, and we return the output down here. So we've loaded these all into memory. We haven't talked much. There'd be a different setup in there because there is ways to feed the files directly into your cross model. But we want to go ahead and just load them all because it's really, for today's processing and what our computers can handle, that's not a big deal. And then we go ahead and set the train images, train labels, test images, test labels, and that's going to be returned in our output append. And you can see here we did images and labels set up in there, and it just loads them in there, so we'll have these 4 different categories. Let me just go ahead and run that. So now we've gone ahead and loaded everything on there. And then if you remember from before, we imported, let me just go back up there, shuffle. Here we go. Here's our sklearn utilities import shuffle. And so we want to take these labels and shuffle them around a little bit, just mix them up so it's not having the same, if you run the same process over and over, then you might run into some problems on there. And just real quick, let's go ahead and do a plot so we can just, we've looked at them as far as from outside of our code. We pulled up the files and I showed you what that was going on. We can go ahead and just display them here too. And I tell you, when you're working with different people, this should be highlighted right here. This thing is like when I'm working on code and I'm looking at this data and I'm trying to figure out what I'm doing, I skip this process. The second I get into a meeting and I'm showing what's going on to other people, I skip everything we just did. So, and go right to here where we want to go ahead and display some images and take a look at it. And in this display, I've taken them and I've resized the images to 20 by 20. That's pretty small. So we're going to lose just a massive amount of detail. And you can see here these nice pixelated images. I might even just stick with the folder showing them what images we're processing. Again, this is, you gotta be a little careful of this. Maybe resizing it was a bad idea. In fact, let me try it without resizing it and see what happens. Oops. So I took out the image size and then we put this straight in here. One of the things, again, this is, put the D, there we go. One of the things, again, that we want to note whenever we're working on these things is the CV2, there are so many different image classification setups. It's really a powerful package when you're doing images. But you do need to switch it around so that it works with the pyplot. And so make sure you take your numpy array and change it to a uinteger 8 format because it comes in as a float. Otherwise, you'll get some weird images down there. And so this is just basically we've created a plot. We went ahead and did the plot 20 by 20, or the plot figure size is 20 by 20. And then we're doing 25, so a 5 by 5 subplot. Nothing really going on here too exciting, but you can see here where we get the images. And really, when you're showing people what's going on, this is what they want to see. So you skip over all the code and you have your meeting, you say, okay, here's our images of the building. Don't get caught up in how much work you do, get caught up in what they want to see. So if you want to work in data science, that's really important to know. And this is where we're going to start having fun. Here's our model. This is where it gets exciting when you're digging into these models. And you have here, there we go. When you have here, if you look here, here's our convolutional neural network 2D. And 2D is an image. You have two different dimensions, X, Y, and even though there's three colors, it's still considered 2D. If you're running a video, you'd be convolutional neural network 3D. If you're doing a series going across, a time series, it might be 1D. And on these, you need to go ahead and have your convolutional neural network. If you look here, there's a lot of really cool settings going on to dig into. We have our input shape, so everything's been set to 150 by 150. And it has, of course, three different color schemes in it. That's important to notice. Activation default is ReLU. This is small amounts of data being processed on a bunch of little neural networks. And right here is the 32. That's how many of these convolutional neural networks are being strung up on here. And then the 3 by 3, when it's doing its steps, it's actually looking at a little 3 by 3 square on each image. And so that's what's going on here. And with convolutional neural networks, the window floats across and adds up all these numbers going across on this data. And then eventually it comes up with 30, in this case, 32 different feature options that it's looking for. And of course, you can change that 32. You can change the 3 by 3, so you might have a larger setup. You know, if you're going across 150 by 150, that's a lot of steps. So we might run this as 15 by 15. There's all kinds of different things you can do here. We're just putting this together. Again, that would be something you would play with to find out which ones are going to work better on this setup. And there's a lot of play involved. That's really where it becomes an art form, is guessing at what that's going to be. The second part I mentioned earlier, and I can only begin to highlight this. When you get to these dense layers, one is the activation is a ReLU. They use a ReLU and a softmax here. It's a whole setup just explaining why these are different and how they're different. Because there's also an exponential, there's a tangent. In fact, there's just a ton of these, and you can build your own custom activations depending on what you're doing. A lot of different things go into these activations. There are 2 or 3 major thoughts on these activations, and ReLU and softmax are, well, ReLU, you're really looking at just the number, you're adding all the numbers together and you're looking at Euclidean geometry, ax plus bx2 plus cx3 plus bias. With softmax, this belongs to the party of it's activated or it's not, except they call it softmax because when you get to 0, instead of it just being 0, it's actually a little bit less than 0, so that when it trains, it doesn't get lost. There's a whole series of these activations. Another activation is the tangent, where it just drops off and you have like a very narrow area where you have from -1 to 1, or exponential, which is 0 to 1. So there's a lot of different ways to do the activation. Again, we can do, that'd be a whole separate lesson on here. We're looking at the convolutional neural network, and we're doing the 2 pools. This is so common. You'll see two convolutional neural networks stacked on top of each other, each with its own max pool underneath. And let's go ahead and run that. So we built our model there, and then we need to go ahead and compile the model. So let's go ahead and do that. We are going to use the Atom optimizer. The bigger the data, the Atom fits better on there. There's some other optimizer, but I think Atom's a default. I don't really play with the optimizer too much. That's like once you get a model that works really good, you might try some different optimizers, but Atom's usually the most. And then we're looking at loss. Pretty standard. We want to minimize our loss. We want to maximize the loss of error. And then we're going to look at accuracy. Everybody likes the accuracy. I'm going to tell you right now, I start talking to people and I'm like, okay, what's the loss on this and that? And as a data science, yeah, I want to know how what's going on with that, and we'll show you why in a minute. But everybody wants to see accuracy. They want to know how accurate this is. And then we're going to run the fit. And I wanted to do this just so I can show you, even though we're in Python setup in here where Jupyter Notebook is using only a single processor, I'm going to bring over my little CPU tool. This is 8 cores on 16 dedicated threads, so it shows up as 16 processors. And actually I got to run this and then move it over. So we're going to run this, and hopefully it doesn't destroy my mic. And as it comes in, you can see it's starting to go through the epochs. And I set it for 5 epochs. And then this is really nice because Keras uses all the different threads available. So it does a really good job of doing that. This is going to take a while. If you look at here, it's ETA 2 minutes and 25 seconds, 24 seconds. So this is roughly 2.5 minutes per epoch. And we're doing 5 epochs. So this is going to be done in roughly 15 minutes. I don't know about you, but I don't think you want to sit here for 15 minutes watching the green bars go across. So we'll go ahead and let that run. And there we go. There was our 15 minutes. It's actually less than that because I did, when I went in here, realized that, where was it? Here we go. Here's our model compile. Here's our model fit. And here's our epochs. So I did 4 epochs. So a little bit better, a little more like 10 to 11 minutes instead of doing the full 15. And when we look at this, here's our model. We talked about the compiler. Here's our history. We're going to history equals the model fit. We'll go into that in just a minute. And what we're looking at is we have our epochs. Here's our validation split. So as we train it, we're weighing the accuracy versus, you kind of pull some data off to the side while you're training it. And the reason we do that is that you don't want to overfit. And we'll look at that chart in just a minute. Here's batch size. This is just how many images you're sending through at a time. The larger the batch, it actually increases the processing speed. And there's reasons to go up or down on the batch size because of the smaller the batch. There's a certain point where you get too large of a batch and it's trying to fit everything at once. So 128 is kind of big. Depends on the computer you're on and what it can handle. And then of course we have our train images and our train labels going in telling it what we're going to train on. And then we look at our 4 epochs here. Here's our accuracy. We want the accuracy to go up, and we get all the way up to 0.83 or 83%. This is actual percentage based pretty much. And we can see over here our loss. We want our loss to go down. Really fluctuates. 55, 1.2, 0.77, 0.48. So we have a lot of things going on there. Let's go ahead and graph those. Turn that up. And our team in the back did a wonderful job of putting together this basic plot setup. Here's our subplot coming in. We're going to be looking at, from the history, we're going to send it the accuracy and the value accuracy labels and set up on there. And we're going to also look at loss and value loss. So you can see what this looks like. what's really interesting about this setup, and let me just go ahead and show you, because without actually seeing the plots, it doesn't make a whole lot of sense. It's just basic plotting of the data using the PyPlot library. And I want you to look at this. This is really interesting. When I ran this the first time, I had very different results. And they vary greatly. And you can see here our accuracy continues to climb. And there's a crossover here. Put it in here. Right here's our crossover. And I point that out because as we get to the right of that crossover where our accuracy, and we're like, oh yeah, I got 0.8%, we're starting to get an overfit here. That's what this switchover means. As our value, as the training set versus the value accuracy stays the same. And so that this is the one we actually really want to be aware of, and where it crosses is kind of where you want to stop at. And we can see that also with the train loss versus the value loss right here. We did one epoch, and look how it just flatlines right there with our loss. So really, one epoch is probably enough. And you're going to say, wow, okay, 0.8%. Certainly, if I was working with the shareholders, telling them that it has an 80% accuracy isn't quite true. And we'll look at that a little deeper. It really comes out here that the accuracy of our actual values is closer to 0.41% right here, even after running it this number of times. And so you really want to stop right here at that crossover. One epoch would have been enough. So the data is a little overfitted on this when we do 4 epochs. And, oops, there we are. Okay. My drawing won't go away. Let me see if I can get, there we go. For some reason, I've killed my drawing ability and my recorder. All right, took a couple extra clicks. So let's go ahead and take a look at our actual test loss. So you see where it crosses over. That's where I'm looking at. That's where we start overfitting the model. And this is where, if we were going to go back and continually upgrade the model, we would start taking a look at the images and start rotating them. We might start playing with the convolutional neural network instead of doing the 3x3 window. We might expand that, or find different things that might make a big difference as far as the way it processes these things. So let's go ahead and take a look at our test loss. Now remember, we had our training data. Now we're going to look at our test images and our test labels for our test loss here. And this is just model evaluate, just like we did fit up here. Where was it? One more. Model fit with our training data going in. Now we're going to evaluate it on the, and this data has not been touched yet. So this model's never seen this data. This is on completely new information as far as the model is concerned. Of course, we already know what it is from the labels we have. And this is what I was talking about. Here's the actual accuracy right here, 0.48 or 4847. So this 49% of the time guesses what the image is. And I mean, really, that's the bottom dollar. Does this work for what you're needing? Does 49% work? Do we need to upgrade the model more? In some cases, this might be, what was I doing? I was working on stock evaluations, and we were looking at what stocks were the top performers. Well, if I get that 50% correct on top performers, I'm good with that. That's actually pretty good for stock evaluation. In fact, the number I had for stock was more like 30-something% as far as being a top performer stock. Much harder to predict. But at that point, you're like, well, you'll make money off of that. So again, this number right here depends a lot on the domain you're working on. And then we want to go ahead and bring this home a little bit more as far as looking at the different setup in here. And one of the, from sklearn, if you remember, actually let's go back to the top. we had the classification report, and this came in from our sklearn or scikit setup, and that's right here. You can see it right here on the see, there we go, classification report right here. sklearn metrics import classification report. That's what we're going to look at next. A lot of this stuff depends on who you're working with. So when we start looking at precision, you know, this is like for each value. I can't remember what one was probably mountains. So if 44% is not good enough, if you're doing like you're in the medical department and you're doing cancer, is this cancerous or not? And I'm only 44% accurate. Not a good deal. You know, I would not go with that. So it depends on what you're working with on the different labels and what they're used for. Facebook, you know, 44%, I'm guessing the right person. I would hope it does a little bit better than that. But here's our main accuracy. This is what almost everybody looks at. They say, oh, 48%, that's what's important. Again, it depends on what domain you're in and what you're working with. And now we're going to do the same model. Oops, somehow I got my, there it goes. I thought I was going to get stuck on there again. This time we're going to be using the VGG16. And remember, this one has all those layers going into it. So it's basically a bunch of convolutional neural networks getting smaller and smaller on here. And so we need to go ahead and import all our different stuff from Keras. We're importing the main one is the VG16 setup on there. Just aim that, there we go. There's kind of a pre-processing images, applications, pre-process input. This is all part of the VGG16 setup on there. And once we have all of those, we need to go ahead and create our model. And we're just going to create a VGG16 model in here. Inputs, model inputs, outputs, model inputs. I'm not going to spend as much time as I did on the other one. We're going to go through it really quickly. One of the first things I would do is, if you remember in Keras, you can treat a model like you would a layer. And so at this point, I would probably add a lot of dense layers on after the VGG16 model and create a new model with all of those things in there. And we'll go ahead and run this because here's our model coming in and our setup. And it'll take it just a moment to compile that. Hey, what's funny about this is I'm waiting for it to download the package. Since I pre-ran this, it takes it a couple minutes to download the VGG16 model into here. And so we want to go ahead and train features for the model. We're going to predict the train images, and we're going to test features on the predict test images on here. And then I told you I was going to create another model too, and the people in the back did not disappoint me. They went ahead and did just that. And this is really an important part. This is worth stopping for. I told you I was going to go through this really quick. So here's our, we have our model 2 coming in. And we've created a model up here with the VGG16, model equals model inputs, model inputs. And so we have our VGG16. This has already been pre-programmed. And then we come down here, and I want you to notice on this right here, model 2 layers -4 to 1, x layer x. We're basically taking this model and we're adding stuff onto it. And so we've just basically duplicated this model. We could have done the same thing by using model up here as a layer. We could have had the input go to this model and then have that go down here. So we've added on this whole setup, this whole block of code from 13 to 17 has been added on to our VGG16 model. And we have a new model with the layer, input, and X down here. Let's go ahead and run that and compile it. And that was a lot to go through right there. When you're building these models, this is the part that gets so complicated that you get stuck playing in, and yet it's so fun. It's like a puzzle. How can I loop these models together? And in this case, you can see right here that the layers we're just copying layers over and adding each layer in. This is one way to build a new model. And we'll go ahead and run that. Like I said, the other way is you can actually use the model as a layer. I had a little trouble playing with it. Sometimes when you're using the straight model over, you run into issues. And it seems like it's going to work, and then you mess up on the input and the output layers. There's all kinds of things that come up. Let's go ahead and do the new model. We're going to compile it. Again, here's our metrics: accuracy, sparse categorical loss. Pretty straightforward, just like we did before. You got to compile the model. And just like before, we're going to create a history. The history is going to be new model fit train 128. And just like before, if you remember when we started running this stuff, we're going to have to go ahead and it's going to light up our setup on here. And this is going to take a little bit to get us all set up. It's not going to just happen in a couple minutes. So let me go ahead and pause the video and run it, and then we'll talk about what happened. Okay, now when I ran that, these actually took about 6 minutes each. So it's a good thing I put it on hold. We did 4 epochs. I actually had to stop it because it was at 10 and switch it to 4 because I didn't want to wait an hour. And you can see here our accuracy and our loss numbers going down. And just at a glance, it actually performed, if you look at the accuracy, 0.2658. So our accuracy is going down, or 26%, 34%, 35%. And you can see here at some point it just kind of kicks the bucket. Again, this is overfitting. That's always an issue when you're running on programming these different neural networks. And then we're going to go ahead and plot the accuracy history. We built that nice little subroutine up above, so we might as well use it. And you can see it right here. There's that crossover again. And if you look at this, look how the red shifts up, how our loss functions and everything crosses over. We're overfitting. After one epoch, we're clearly not helping the problem or doing better. It's just gonna baseline. This one actually shows with the training versus the loss, value loss. Maybe second epoch. So on here, we're now talking more between the first and the second epoch, and that also shows kind of here. So somewhere in here, it starts overfitting. And right about now, you should be saying, uh-oh, something went wrong there. I thought that when we went up here and ran this, look at this. We have the accuracy up here is hitting that 48%, and we're down here. You look at the score down here, that looks closer to 20%, not nearly anywhere in the ballpark of what we're looking for. And we'll go ahead and run it through the actual test features here. And there it is. We actually run this on the unseen data and everything, 0.18 or 18%. I don't know about you, but I wouldn't want, at 18%, this did a lot worse than the other one. I thought this was supposed to be the super model, the model that beats all models, VGG16 that won the awards and everything. Well, the reason is that one, we're not pre-processing the data, so it needs to be more. There needs to be more as far as like rotating the data at 45-degree angle, taking partials of it, so you can create a lot more data to go through here. And that would actually greatly change the outcome on here. And then we went up here, we only added a couple dense layers. We added a couple convolutional neural networks. This huge pre-trained setup is looking for a lot more information coming in as far as how it's going to train. And so this is one of those things where I thought it would have done better. And I had to go back and research it and look at it and say, well, why didn't this work? Why am I getting only 18% here instead of 44% or better? And that would be wise. It doesn't have enough training data coming in. And again, you can make your own training data. So it's not that we have a shortage of data. It's that some of that has to be switched around and moved around a little bit. And this is interesting right here too. If you look at the precision, we're getting it on number 2, and yet we had 0 on everything else. So for some reason, it's not seeing the different variables in here. So it'd be something else to look in and try to track down. And that probably has to do with the input. But you can see right here, we have a really good solid 0.48 up here. And that's where I'd really go with, is starting with this model. And then we look at this model and find out, why are these numbers not coming up better? Is it the data coming in? Where's the setup on there? And that is the art of data science right there, is finding out which models work better and why. And we went through the very basics of convolutional neural networks, along with the VGG16 import, and how you can get started with that. And again, the art is the data going in and learning to play with it, find out what works.
Thank you all for watching this full course video on neural network tutorial by Simplilearn. I hope it was useful and informative. If you have any queries, please feel free to put them in the comment section of the video. Thank you for watching.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.